All about mechanical flight. The manual UKNRLF compiled by the staff of ISA Special Illustrations. Page 2, Page 3, Page 4. Everything Aviation Aerolite Petrol Motor BHP the aerial motor reversing. Highest class workmanship, greatest possible power 4-weight, aluminum base, total weight 6 Oz, takes I ampere at 4 volts. Price 17, 6D, postage 3D. Specially designed for driving model aeroplanes, racing boats, etc. Bore Ifen stroke, weight 8 Ibs, 1 Oz, piston dome top with 2 rings, connecting rod phosphor bronze. Cranks Yuba steel in, diam. Bearings phosphor bronze in, diam X1 in and 5 in, diam X in. Long, crankcase aluminium alloy, water jacket copper welded to cast iron cylinder by special process. Flywheel 4 fin, diam, weight 33 Ibs, dimensions overall height 10 in, width 5 in. Speed 2000 revs per min. Ignition electric. Catalogs post free 6 Enitfink U asterisk. QT Eepsider. H. Lancaster MIAE NAMIME Consulting Engineer 1 Albemarle Cent Piccadilly W. Specialist on engine S for aeroplanes, designs for motor vehicles, and C. Telephone 567 Gerarchal. Telegrams, Lankamoto, London. Drop IT now, just a PC with your address. Wessender's full 100-page list. Post free. New Aero motor weight, including PR Kaler under 3 Oz. This motor is self-starting, low current consumption, 2 amps. Powerful, silent, well-balanced. Size Lin diam, 2-inch long, each 7/6 post 2D, NBR full particulars, C-lists, Wright for it. Established 1896, aluminum castings. RW Cone 219, Goswell Road, EC Markham and Prance, RGL Markham MI Mech E, MIAE, H. Weymouth Prance AIEE AMIAE. Consulting motor engineers, land, marine, and aeronautical. All types of aeroplanes supplied, including Farman, Wright, REP. Blériot and Antoinette machines, specified flights guaranteed. Instruction off clients arranged for, dirigible balloon suppleed. K expert advice concerning engine installations, tests and trials supervised, reports made. All makes off motors, gliders, and accessories and fittings supplied. 143 Strand, London WC Telephone, 3439 Gerard. Telegrams, Mountaineers, London. North British Aeroplane and Balloon Fabrics, the first British able to for arrange off scientifically produced fabrics suitable for aeronautical purposes. These fabrics have been thoroughly tested and are unequaled for the purpose. Manufactured by the North British Rubber Co., LD, lists free in application. 280. See Aero Manual, own experiment with ignition apparatus. There is no need. Just order your engine S fitted with Bosch Special Aeroplane Magneto, Write for particulars the Bosch Magneto Co., Limited. V23 Store Cent, London WC Telephone, Telegrams, 8610 Gerard 2 lines. Bomag, London. Page 11. Tightening screws, right and left threads, all sizes stocked. Tubes, rods, and castings in all metals. Steel tension wires H. Rowlett & Co., 12 and 13, Colduth Square, Rose 1, Cry Avenue. Telephone, 4674, Holbury, London. E.g. Telegrams, Interior, London. 11th edition. T. Jotter Amiel, 130,000. Up-to-date and keeping abreast with the motor car itself. Asterisk the referee. Motor mechanism and analysis details described in non-technical language. Pages and 200 illustrations. Every motorist should keep a copy off the motor manual on the car. One day or alter it is bound tobe very useful and save time and temper. The Motor Offices 7-15 Rosebery Ave, London. E.g. Wholesale E.J. Larby 1, Paternoster Ave, London. E.C. Aero Manual Manual off mechanically propelled human flight, covering the history off the work of Farley investigators, and off the pioneer work off the last century. Recent successes and the reasons therefore are dealt with together with full constructive details concerning GE airships, aeroplanes, gliders et tilde, compiled by the staff of the Motor, 1st edition. London Temple Press Limited, 7, 9, 11, 13, and 15 Rosebery Avenue, EC. 1909, News Journal Often. Automobile World, the Motor is first out with all the news off the having representatives in all most important centers at home and abroad. It is published every Tuesday morning and contains news items received as late as 3 p.m. on Mondays. The circulation of the Motor, which is certified by Chartered Accountants, is, in round figures, 43,000 copies weekly. The sale of the Motor is claimed to exceed the combined sales of all other motorcar papers. It circulates in the farthest corners off Earth and finds its way every week in the hands of the leading men in every branch of automobilism. The trend of events in mechanical flight and aeronautics is thoroughly dealt with and illustrated in the Motor. Offices of the Motor, 7-15, Rosebery Avenue, T. London, E.g. England, Index, Frontispiece, 50 years hence. Introduction Preface, Aeroplane Design and Construction, Professor Chatley, Human Flight, The Solved Problem, 13, The Gliding Experiments off the Wright Brothers. A33, The Man and Machine. 34, The Principles Underlying Human Flight. 3,540 The History of Human Flight Early History. 4,143 in England, 4,448 in Germany, 4,952 in America, 5,356 in France, 5,773 Human Flight from the Military Point of View, 7,482 The Flying Figure on the Tomb of Ramesses Roman III, 82 Dirigible Balloons, 8,388 How to Pilot a Voice in Aeroplane, 8,991 Constructional, Streamline Form 9,294, The Dipping Front Edge 9,598, The Sport Off Gliding, and How to Construct a Glider 99,105. Modern Aeroplanes, the Wright 106,115 Voice in 115R, E, P119 Henry Farman HI, 120, Aeroplane, 120 Antoinette 122 Cody 123 Howard Wright 124 Blériot 125 Silver Dart 126 Short Bros 126 Rigging Ice and Cables 127,130 Plane Materials 131 Propellers 132,134 Aerial Engines 135,153 Light Ignition Apparatus 154,155 The Cycloplane 156 Table of Wind Pressures 157.44 G 833. Ignition is as important as design perfection in both is essential before successful flight can be accomplished. For years, Sims magnetos have been written on and recommended by all well-known experts. Therefore, aeroplane experimenters should write four-particulars off Sims Special Aero Magneto Thesim's Magneto CO. Limited. Welbeck Works, Kimberley Road, Kilburn, London, N.W. Tell. 3,843 Paddington Tells, Expansible, London. And at 95-97 Liberty Street, New York, USA, Representatives Midlands H.J. Baker, Godova Street, Coventry, Ireland C. E. Jacob 17 Bachelor's Walk, Dublin, Scotland, Jas. Thompson & Son, Lady Lawson Street, Edinburgh, and 15 Renfield Street, Glasgow. Frank Asterisk, Baudot and Paz, 22 Avenue de la Grande Armée, Paris. Belgium, Maurice Wanson, 84 Rue du Marais. Brussels, Italy, Bussolati & Co., Turin. Switzerland, A. Carfagny, Geneva. Introduction. At first thought, Themen in the street would probably be inclined to assert that, in connection with thought of human flight, Virilil indeed had been written. And although would Bainera, would paradoxically be justified in his assertion. As amateur off-act, an immense amount has been written concerning aviation. From the earliest times the subject has appealed to the imagination and has inflamed the desires of man. Condemned toin habit thelois dipped soften ocean of air, and has never ceased tone the theability off the birds rise off the solid bottom, and float in the elastic medium that encloses them. And it has never ceased to study Themians employed by them, or to investigate the possibilities of imitating them. And although Thedvent's thinker along this line, oft thought haste for had to bar Thesneers off his contemporaries, not a little office work has been placed on record to observe some pose more or less useful in the elucidation of the problem. As a complete library of that has been written on the subject of aviation would equal in bulk the contents of many an average bookcase. But and it is every big but, the literature of aviation is in many languages and considerably scattered, and much of it, in the light of latter-day knowledge, is mere chaff. Thean lie difficulty about the sifting off the heat from it being that wearingly just learning to distinguish between the grain and the husk. Europe of experimenters in every first decade of the 20th century has already provided us with some power of differentiation, and it is in the exercise of this power admittedly imperfect that the Aero Manual has been prepared. The scheme underlying its compilation has been first every severe winnowing off the heat from the chaff and that present, meant off the work off those investigators off the past whose work would no appear to count. And it has been found that much off the work that, had Thai's manual been prepared 10 years ago, would have been dealt with therein, cano be disregarded. A previous decade has for permitted off such extensive and useful weeding out. The importance of this lies in the fact that beer mistakes well earn and beer ability to ability and disregard, that which is useless so to progress. This vain off-thought has dominated the preparation of the historical section of the Aero Manual in order that it may usefully contribute to further investigation of the subject. The work of the brothers Wilbur and Orville Wright is dealt with fully and in their own words, because of its immense value. Their achievements have set the seal on the work of the school which, starting with Lilienthal, has attained the success that, and has sought through many centuries. The Wrights have told us personally that gliding is the bosses of aviation and that, to first gain, perfection in gliding will materially quicken the attainment of tartoflying. For this reason, we have devote space to the subject of gliding and have prepared science for answerable machine, based upon practical experience of men who have actually glided with them. Information given in manual concerning airships is not carried so far as that dealing with aeroplanes and gliders for the obvious reason that the airship is less likely to interest either the student or the sportsman, its function being almost entirely different that off the heavier than air machine. The information about existing aeroplanes, engines suitable for aviation, component parts, constructional details, etc., has been very carefully written and revised up to the last moment. For improvement is always going on naturally. Our frontispiece, seen, as observed from the pilot seat off an aeroplane, 50 years hence, will show great departures from present-day methods of locomotion. The difficulty of the aeronaut in ascertaining his whereabouts has been overcome by the artist. To meet the many difficulties, the highways have been considerably widened, the broad road for motor traffic being bordered on either side by great green swords, which serve as landing places for flying machines. For these great trackways flying machines may travel, and to facilitate night traveling, each trackway is bordered with a broad band of white chalk so that the searchlights off the flying machines may pick out the road boundaries. Each road is given a distinguishing symbol, the great national roads being ordered and band-numbered. Thus the aeroplane ain't the picture race traveling over NR71, the Great North Road between London and York, whilst branching to the left is CR3, the county road to Peterborough. The names Anthocyncer or laid in white chalk set in the green grass, and the name Ofachplasi similarly shown as clearly aspicible. The artist has assumed that navigation in Thea will be governed by the Same rules that control the navigation of ships at sea. Ein regulation is needed only for the variation of altitude. It can be defined by a parody on the verse that refers to ships crossing. If beneath you planes appear, it is here due to toe kept clear, toe test judgment says proper. Top or tor starboard rise, or driffer. Flying clubs can be seen in the picture read a couple of points, and the Aero Hotel at Norman Cross has made ample provision in the way of lending space and machine storage. Preface, Aeroplane Design and Construction, by Professor Herbert Chatley, B.Sc., AMICE, Imperial Engineering College, North China. There are quite a number of books on the subject of aviation which profess to the reader how to construct a machine, arid, doubtless by the exercise of considerable mental effort. Useful information can be obtained from them, but the average man who has a bent for mechanical invention and is drawn into the glamour of the subject wants to know a few particular things and it much more. He is probably aware that very few people know much about the subject and thinks that, by breaking out in a new direction, he made something fresh. Within limits, this is probably true. What then Aretha Point wants told of? He hears a lot about gliding angles, skin friction, etc. But the features that interest him most are sizes, shapes, and weights. To start with, what size must a carrying machine be? Well, for every pound weight, including that off itself and the load, there must be nearly a square foot off supporting surface, so that, when the machine is being designed, the inventor must figure out whether there is enough surface to support weight. This means that there is a considerable width and length. As may be recognized from the numerous photographs of machines now accessible, the surfaces may be superposed, i.e., subdivided and placed in sheets one over another. In lie precaution necessary is that the vertical distance between the planes must be equal to the smaller dimension thereof. Thus, two surfaces 4ft. Wide must be 4ft, at least apart. Furthermore, the surfaces must be narrow in the direction of motion, breadth across the machine being 10 or 12 times the length. Next, how shall we arrange these surfaces well, as far as present information is concerned, they may be arranged just as one pleases, provided that rules are observed. First is that the center of gravity, i.e., the place where the whole weight can be supported without earning, should lie between the surfaces so that lift on those surfaces shall balance about the center of gravity. The second is similar to the first, and is that the surfaces must be symmetrically placed about the center line. What shape should the surfaces be? In section they should be curved if possible in this way. As the curvature should be quite small, about L12 or less off width. In plan, they should taper away from the center line. The surfaces should be fixed in open frames made of some tough timber with metal joints and good piano wire stays. Coupling nuts should be used for tightening the latter. The frame should be arranged torsten and under frames supported by springs on light wheels. The springs should have added stiffness equal to at least twice the weight. During is performed by surfaces which can be rotated about axes parallel to the length of the machine, perpendicular to the length of the machine, and parallel to the breadth of the machine. These surfaces should also be balanced about the center of gravity. As an alternative, the main surfaces may be warped, the joints of the frames being able to turn in suitable directions, and the planes pulled to the required shape with controlling wires. Before the inventor thinks off a motor, I should try the machine down a slight slope against the wind and see if it will glide stably. At a lorbalancer will probably be necessary at there are off the machine. If it finds the machine will glide a certain number of feet from a given height, then the gliding height of glide angle for his machine is measured by length of glide multiply this fraction in Tothuate, and the result is the head resistance off the machine. This should be cut down as much as possible by carefully shaping out the exposed parts with easily curved sections so that the units not grip on them. Now a Stothy motor. The propeller is properly designed, the motor should carry about 50 ib. per brake horsepower, so that a machine weighing 1000 ib requires 20 bhp. This assumes, however, that the propeller is a good one, and that both it and the motor are running at the best speeds. It will be wisest for an amateur to purchase his propeller, since there is considerable knowledge required in the correct formation, to ascertain what torque is required to drive it at the specified speed of advance and revolutions. He should then see that the motor is working with high efficiency, and when direct coupled to the propeller, it has same number of revolutions and with the same torque. If the propeller is driven through gearing, then the torque and revolutions at head driving shaft should be the same as that of the propeller. This matter is most important. No good results can be expected unless the motor, propeller, and aeroplane are in harmony. This involves a further equality between the propeller thrust and the aeroplane assist, ants at his specified speed of advance. Resistance will rather higher than that mentioned above us. Head resist ants on account off the surface off the motor and accessories, and perhaps a rather higher speed butane and a cassethethra should be upwards off on quarter the total weight. The propeller should run a tailwheel between the superposed surfaces, so that the head resistance on these is balanced. Well-designed, moderate-speed propellers are preferable to high-speed small ones. Unless one has thoroughly studied the subject, the Makinga Fat propeller should note when be emptied. For those whose knowledge of mechanics is fairly advanced, there is plenty of scope for acquiring a fund of preliminary information. It must, however, be realized that no book knowledge is comparable with experiment, but the books may help on to avoid unnecessary repetition of work, and also to concentrate research on the lines of known error and doubt. Human flight, the solved problem. Man, the great adventurer, has a topnet retain to every domain, top oriented habits and methods awful author living creatures, and to imitate and adopt such off their methods as would prove interesting and useful to him. And at last, after many centuries, he has evolved a machine which shall give him the mastery of the Eurasius machines have already given him the mastery of the Lindanthesia. He has always envied the bird and its freedom and sense of perfect motion, and he has wondered and thought and experimented and tried, never daunted by failure 1,000 times repeated, until the first decade of the 20th century session rise a victor in this struggle. He has compared the human skeleton with that of the bird and marked the likeness, and he has seen in the bones of a bird's wing a resemblance to those of the human arm, all of which has made him think that the need only discover the secret of flight hope the qual of the bird at least in some measure. With all his study, the goal of winged flight is not yet within man's reach. He knows better than headed, thanks to modern high-speed recording photographic apparatus, what the bird when it flips its wings, but to devise a mechanical appliance or to develop the power to lift himself by means of his own arms seems far beyond his present skill. The flapping mode of flight may therefore be said to have few, if any, advocates. Orman has gained his successes, the small preliminary successes and the greater achievements of the past year wo solely in high sport to soar. He has watched the albatross, the buzzard, the gull and the kite, and a cersault, his toys, his models, and his man-lifting glider shave all being soaring machines and fig. L. The human skeleton and Thuhen have finally found skeleton of a bird, the latter drawn to the forms that more in large scale, nearly complied with. The conditions laic, DCF, /VJ Binature, Enterprise and author Dirk Tion had prepared Joy him a source of power light enough for his purpose, and so with the Petrol engine, used his adaptation of the reciprocating action of the tail and fins, of the fish and the wingsoft bird the rotary pro P11 and his flying Gapara tus was complete, and almost a marvel lose his thighs fig. 2. A comparison of the bones of achieve manana the wing bones of a bird. The latter meant is the drawn tone enlarged scale. Fact that, whereas 5 years ago, man had not a single flying machine, today he possesses a little handful of types quite different, each of which is capable of successful free flight. Success first began to come to man when he definitely ceased to it off the flying machine by chance, and instead, devoted himself to the study of the principles underlying and governing Thar. Then vanished his theories of so mystery auspower that permitted a bird, like the albatross, for instance, to sweep 400s off miles across the ocean apparently effortless, gliding without wing motion and steering with delight felice. There can be not out that the soaring bird, and also the flapping bird, has developed extraordinary skill in the discovery of rising gear currents. One has in little watched the movements of a number of seagulls in windy and gusty weather to secure innumerable proofs of the existence of thissence, and also of the skill with which the birds counteract the influence of so new air current that incidentally entered. The air does not flow along said 8-link currents parallel with the Earth's surface. Except in rare instances could we observe the movements of a body of air we should see that, whilst as a whole it moved forward, in itself it was a maze of whirling eddies, currents of warm air flowing upward and currents of fig. 3. The successive positions of the wings of a pigeon in flight, photographed in 1890 by Professor Mary. FZ. 4. TVZE success positions off thewings off a sagal flying, with the trajectory off a fixed point on its wing on a horizontal plane, at on a vertical plane parallel to the line of flight, and at con a vertical plane obliquo the line of flight. Cooled air flowing downward to fill the space. Obstructions, such as sacklift face, will deflect the current upward, leaving a partial void at Hessamit, in tow-hitch airwillinter and a whirling mass oftes. By taking advantage of rising currents, the soaring bird isable tall-lift, itself at such intervals, as will allow it to maintain the elevation desired by it. If we regard the bird as being in a constant state off-falling by gravity towards the ground, off-utilizing this tendency to secure forward motion, and off-opposing it by taking advantage of rising current off-air to maintain or increase its elevation, we get a much clearer idea of the work which the bird has stodo, and we see that its soaring flights are not so effortless as they appear. In fact, there is the same deceptiveness about the walk offman, or high sports to maintain a balance are not noticeable, although they are constantly at work. That man will never approach the birds in skill is as obvious as is already the fact that they cannot emulate the feats officient their own element. He has squipped himself to move at moderate speeds on the surface off theaters, and is content therewith, and he will equip himself with mechanism that in theory will enable him to attain a certain level of proficiency and equally content. That the problem of human flight has been solved is no beyond need of argument. Feats and performances of past 18 months in 1907, 1908, and 1909 amply support the contention that man has at last planted his foot firmly upon the ladder of human flight, and from this time forward advancement in design and methods of construction will be rapid. A2. Wright brothers' first gliding experiments. As related by Mr. Wilbur Wright before the Society of Western Engineers of Chicago on September 18, 1901. The difficulties which obstruct the pathway to success in flying machine construction are of three general classes. 1. Those which relate to the construction of the sustaining wings. 2. Those which relate to the generation and application of power required to drive the machine through the air. 3. Those relating to the balancing and steering of the machine after it is actually in flight. Of the set difficulties, two are already to a certain extent solved. Men already know how to construct wing-soar airplanes, which when driven through the air at sufficient speed, will neatly sustain the weight of the wings themselves, butyl so that off the engine and off the engineer as well. Men also know how to build engines and screws off sufficient lightness and power to drive the seplanes at sustaining speed. As long ago as 1893 a machine weighing 8,001 b. Asterisk demonstrated its power both to lift itself from the ground and to maintain a speed of from 30 to 40 miles per hour. But it came to grief in an accidental free flight, owing to the inability operator to balance and steer it properly. This inability balance and steer still confronts students off the flying problem, although nearly 10 years have passed. This own feature has been worked out. The flying machines will have arrived. For a lot of difficulties of minor importance. The person who merely watches the flight of a bird gathers the impression that the bird has nothing to think of but flapping off its wings. As a matter of fact, this is a very small part of its mental labor. To have mentioned all the things the bird must constantly keep in mind, in order to fly securely through the air, pulled take a considerable time. It take a piece of paper, and after placing it parallel with the ground, quickly let it fall. It will not settle steadily down a sastade, sensible piece of paper or todo, but it insists on contravening every recognized rule of decorum, turning over and darting hither and thither in the most erratic manner, much after the style of an untrained horse. Yet thise is the style of steed that man must earn to an age before flying can become everyday sport. The bird has learned this art of equilibrium, and learned it so thoroughly that its skill is not apparent to her sight. We only learn to appreciate it when we're to imitate it. Now, there are on the ways of learning how to ride a fractious horse, one is to him and learn by actual practice how each motion and trick may be best met. The other is asterisk made by maxim. 4. Ossiton fence and watch the beast a while, and then retire to the house and at lesser figure out the best way of overcoming his jumps and kicks. The latter system is the safer, but the former, on the whole, turns out the larger proportion of good riders. It is very much the same in learning to ride a flying machine. If you are looking for perfect safety, you will dowell Ossiton fence and watch the birds, but if you really wish to learn, you must mount a machine and become acquainted with its tricks by actual trial. Lilienthal and balancing. Herr Otto Lilienthal seemed to have been the first man who really comprehended that balancing was the first, instead of the last, of the great problems in connection with human flight. He began where others left off, and this saved the many thousands of dollars that it had thought for being customarido spend in building and fitting expensive engine machines which were uncontrollable when tried. He built a pair of wings suitable to sustain his own weight, and made use of gravity as his motor. This motor not only cost him nothing to begin with, but it required no expensive fuel while in operation, and never had to send a ship for repairs. It had own serious drawback, however, in that it always insisted on fixing the conditions under which it would work. These were that the man should first betake himself and machine toth it upon a hill and fly with a downward as well as a forward motion. Unless the conditions were complied with, gravity served no better than a bulky horse it would not work at all. Although Lilienthal must have thought the conditions were rather hard, he nevertheless accepted them till something better should turn up, and in this manner he made some 1,000 flights, in a few cases landing at a point more than 1,000 feet distant from his place off starting. Other men gnawed out long before had the toftering such chaplain. Lilienthal not only thought but acted, and in so doing probably made the greatest contribution to the solution of flying problem that is for being made by any omen, demonstrated the feasibility of actual practice in the air, without which success is impossible. Herr Lilienthal was followed by Mr. Pilcher, a young English engineer, and b. Mr. Chanute, a distinguished member of Society of Western Engineers of Chicago. A few others have built machines, but nearly all that isofreal value is to the experiments conducted under the direction of the three men just mentioned. The difficulty of balancing. The balancing of fag lighting, or fly machine is very simple in theory. It merely consists in causing the center of pressure to coincide with the center of gravity. But in actual practice, there seems to be almost boundless incompatibility often which prevents their remaining peaceably together for a single instant, so that the operator, who in this case acts as peacemaker, often suffers injury to himself while attempting. 5. I'll bring them to there. If a wind strikes a vertical plane, the pressure on that platoon side off the center will exactly balance that on the other side, and the part above the center will balance that below. This point weckle the center of pressure. But if the plane be slightly inclined, the pressure on the part nearest the wind is increased, and the pressure on the other part decreased, so that the center of pressure is no located, note in the center of the surface, but a little towards the side which is in advance. The plane be still further inclined, the center of pressure will move still further forward. And if the wind blow a little to side, it will also move over a sift omitted. Now, since neither the nor the machine, for an instant, maintains exactly the same direction and velocity, it is evident that the man how would trace the course off the center of Fig. 5. Wright brothers pressure must be very quick off first of 1900. Mine. You how would attempt to move his at that spot every change, must be very active indeed. That is what Herr Lilienthal attempted to do, and did with most remarkable skill, ashest 1,000 glided sufficiently attest. However, headed notescape being overturned by wind gusts several times and finally lost his life through a breakage off his machine, due to defective construction. The Pilcher machine was similar to that of Lilienthal, and like it, seems to have been structurally weak, for on any occasion, while exhibiting the flight of his machine to several members of Aeronautical Society of Great Britain, it suddenly collapsed and fell to the ground, causing injuries to the operator, which proved sadly fatal. The method of management of this machine differed in no important respect from that of Lilienthal, the operator shifting his body to make the centers of pressure and gravity coincide. Though the fatalities which befell the designers of these machines were due to the lack of structural strength, rather than to lack of control, nevertheless, it had become clear to the students of the problem that a more perfect method of control must be evolved. The Chanute machines marked a great advance in both respects. In the multiple wing machine, the tips folded slightly backward under the pressure of wind gusts, so that the travel off the center of pressure was thus largely counterbalanced. The guiding off the machine was to be a slight movement of the operator's body toward the direction in which it was desired that the machine should go. The double-deck machine, built and tried at a some time, marked a very great structural advance, as it was first in which the principles of the modern truss bridges were fully applied to flying machine construction. This machine, in addition to its greatly improved construction and general design of parts, also differed from the machine of 6. Lilienthal in the operation of its tail. In the Lilienthal machine, the tail, instead of being fixed in one position, was prevented by a stop from folding downward beyond a certain point, but was free to fold upward without any hindrance. In the Chanute machine, the tail was sat first rigid, but afterward at his suggestion of Mr. Herring, it was held in place by a spring that allowed it to move slightly either upward or downward with reference to its normal position, thus modifying the action of the wind gusts upon it, very much to its advantage. The guiding off the machine was affected by slight movements of the operator's body, as in the multiple wing machines. Both these machines were much more manageable than the Lilienthal type, and their structural strength, notwithstanding their extreme lightness, were such that no fatalities or even accidents marked the glides made with them, although winds were successfully encountered much greater in violence than any which previous experimenters had told him. The Wright's first interest in flight, a young active interest in aeronautical problems, dates back to the death of Lilienthal in 1896. The brief notice of his death, which appeared in the telegraphic news at that time, aroused a passive interest which had existed from a childhood, and old Meadow take down from the shelves of her home library a book on animal mechanism. by Prof. Mary, which I had already read several times. From this, it was led to read more modern works, and Smibrothers soon became equally interested with myself, wepast from their rating Totha thinking, and finally, Toth Yorking stage. It seemed Taus that the main reason with the problem had remained so long unsolved was that noon had been able to obtain any adequate practice. We figured that Lilienthal in 5-year soft time had spent only about 5 hours in actual gliding through the air. The wonder was not that he had owned so little, but that he had accomplished so much. It would not be considered safe for a bicycle rider to attempt to ride through Ackroud Street after only 5 hours practice, spread out timbits often seconds each over a period of hours. Yet Lilienthal, with this brief practice, was remarkably successful in meeting the fluctuations and it is of wind gusts. We thought that if so method could be found by which it would be possible to practice by the hour instead of by the second, there would be hope of advancing the solution of a very difficult problem. It seemed feasible to this be building a machine which would be sustained at a speed of 18 miles per hour, and then finding a locality where winds of this velocity were common. With these conditions, Aeropatach Tokipit from floating backward would answer very nearly the same purpose as a propeller driven by a motor, and it would be possible to practice by the hour, and without any serious danger, as it would not be necessary to rise far from the ground, and the machine would not have any forward motion at all. We found, according to the accepted tables of pressurescent curved surfaces, that a machine spreading 200 square feet of 7-inch surface would be sufficient for a purpose, and that places could easily be found along the Atlantic coast where winds of 16 to 25 miles were noted at common. When the winds were low, it was our plan to glide from the tops of sandhills, and when they were sufficiently strong, Tausi rope for a motor and fly over on spot. Our next work was to draw up the plans for a suitable machine. After much study, we finally concluded that tails were a source of trouble rather than of assistance. Therefore, we decided to dispense with them altogether. It seemed reasonable that, if the body of the operator could be placed in a horizontal position instead of the upright, as in the machines of Lilienthal, Pilcher, and Chanute, the wind resistance could be very materially reduced, since only on square foot instead of would be exposed. A saffle half horsepower could be saved by the change, where to treat at least the horizontal position. And the method of control used by Lilienthal, which consisted in shifting the body, didn't seem quite as quick or effective as Thecus required. So, after long study, we contrived a system consisting of 12 large surfaces on Chanute double-deck plan, and a smaller surface placed a short distance in front of the main surfaces in such a position that the action of the wind upon it would counterbalance the effect of the travel of the center of pressure on the main surfaces. Thus, changes in the direction and velocity of the wind would have little disturbing effect, and the operator would be required to tend only to the steering of the machine, which was to be affected by curving the forward surface up or down. The lateral equilibrium and the steering to right or left were to be attained by a peculiar torsion of the main surfaces, which was equivalent presenting one and off viewing at a greater angle than the other. In the main frame one, a few changes were also made in the details of construction and trussing employed by Mr. Chanute. Most important of these were 1. The moving off the forward main crosspiece off the frame to the extreme front edge. 2. Thinkasing and thecloth offal crosspieces and ribs off surfaces. 3. Rearrangement of the wires used in trussing 2 surfaces together, which rendered it possible to tighten the wires by simply shortening 2 of them. With these plans, we proceeded in the summer of 1900 to Kitty Hawk, North Carolina, a little settlement located on strip of land that separates Albemarle Sound from the Atlantic Ocean. Owing to the impossibility of obtaining suitable material for a 200-square-foot machine, we were compelled to make it only 165 sq ft, an area which, according to the Lilienthal tables, would be supported at an angle of 3 degrees in a wind of about 21 miles per hour. On the day that the machine was completed, the wind blew from 25 to 30 miles per hour, and we took 8 out 4 trial a sackite. We found that, while it was supported with ammonite in a wind of about 25 miles, its angle was much nearer 20 degrees than 3 degrees. Even in gusts off 30 miles, the off incidence didn't get as low as 3 degrees, although the wind at his speed has more than twice the lifting power of a 21-mile wind. As winds of 38 miles per hour are not plentiful on clear days, it was at once evident that our plan of practicing by the hour, day after day, would have to postponed. Our system of distinct the surfaces to regulate the lateral balance Wasterdan found to much more effective than shifting the operator's body. On subsequent days, when the wind was too light to support the machine with ammonite wetted itasakite, working the rudders bicords reaching to the ground. Their results were very satisfactory, yet we were well aware that this method of testing is never wholly convincing until their results are confirmed by actual gliding experience. Lift and drift experiments. We then turned our attention to making a series of actual measurements of lift and drift off the machine under various loads. So far as we were aware, this had never previously been done with an full-size machine. Results obtained were most astonishing, for it appeared that the total horizontal pull off the machine, while sustaining OITOF 521B, Wassenly S. Alb, which was less than had previously been estimated for head resistance off the framingallon. Making allowance for the weight carried, it appeared that head resistance off the framing was little more than 50%, off the amount which Mr. Chanute had estimated as head resistance off the framing of his machine. On the other hand, it appeared sadly deficient in lifting power as compared with the calculated lift of curved surfaces off its size. This deficiency was supposed might be due to one or more of the following causes. 1. That the depth of the curvature of our surfaces was insufficient, being only about 1 in 22 instead of 1 in 12. 2. That the cloth used in our wings was not sufficiently airtight. 3. That the Lilienthal tables might themselves be somewhat in error. We decided to arrange our machine for the following year so that the depth of curvature of its surfaces could be varied at will and its covering airproof. Our attention was next in tog gliding, but no hill suitable for the purpose could be found near our camp at Kitty Hawk. This compelled us to take the machine tow point for miles south, where the Kill Devil Sandhill rise from the flats end to a height of more than 100 ft. Its main slope is toward the northeast and has an inclination of 10 degrees. On the day at our arrival, the wind blew about 25 miles an hour, and as we had had no experience addling gliding, we deemed it unsafe to him to leave the ground. On the day following, the wind having subsided to 14 miles per hour, we made about a dozen glides. It had been the original intention that the operator should run with the machine to obtain initial velocity and assume the horizontal position only after the machine was in free flight. When it came time, Tolland Hughes resumed the upright position and alight in his feet, after the style of previous gliding experimenters. But on actual trial, we found it much better to employ the help of assistance in starting, which the peculiar form of our machine enabled us readily to do. And in landing, we found that it was entirely practicable. 9. Roland while still reclining in a horizontal position upon the machine. Although the landings were made while moving at speeds off more than 20 miles an hour, neither machine nor operator suffered any injury. The slope off the hill was 9.5 degrees or a drop off 1 ft. In 6 ft. We found that, after attaining a speed off about 25 or 30 miles with reference to the wind, or 10 to 15 miles over the ground, the machine not only glided parallel to the slope off the hill, but greatly increased its speed, thus indicating its ability to glide on a somewhat less angle than 9.5 degrees, when we should feel its a rise higher from the surface. The control off the machine proved even better than we had top expect, responding quickly to the slightest motion off the rudder. The conclusions of 1900. With the Seglides, our experiments for the AR 1900 closed. Though the hours and hours off practice we had hoped to obtain finally dwindled down to about 2 minutes, we were ever much pleased with the general results off the trip. For, setting out a suited, with almost revolutionary theories on many points and an entire unitary form off machine, we considered it quite a point-obable to return without having our pet theories completely knocked on the head with the hard logic of experience, and our own brains dashed out in the bargain. Everything seemed to confirm the correctness of our original opinions. 1. That practices the secret of flying. 2. That it is practicable to assume the horizontal position. 3. That a smaller surface set a negative angle in front off the main bearing surfaces orings will largely counteract the effect of the foreign daft travel off the center of pressure. 4. That steering up and down can be attained with rudder without moving the position off the operator's body. 5. That twisting the wing so stop present there and toth you and at different angles is a more prompt and efficient way of maintaining lateral equilibrium than shifting the body off the operator. 1901, a memorable year. When the time came to sign Ernu machine for 1901, we decided to make exactly like the previous machine in theory and method of operation. But as the former machine was not able to support the weight of the operator when flown a sakai, except in very high winds and at very large angles of incidence, we decided to increase its lifting power. Accordingly, the curvature off the surfaces was increased to 1 in 12 to conform to the shape on which Lilienthal's table was based, and to be on the safe side, we decided also to increase the area off the machine from 165 sq ft to 308 sq ft. Although so large a machine had never before been deemed controllable, the Lilienthal machine had an area of 151 sq ft, that of Pilcher 165 sq ft, and the Chanute double-decker 134 sq ft. A sour system of control consisted in a manipulation of the surfaces themselves instead of shifting the operator's body, we hoped that the new machine would be controllable notwithstanding its great size. According, 10, or calculations, it would obtain support in a wind of 17 miles per hour with an angle of incidence of only 3 degrees. Our experience of the previous year having shown the necessity of a suitable building for housing the machine, we erected a cheap frame building 16 ft. wide, 25 ft. long, and 7 ft. Hayat Thieves. A sour machine was 22 ft, wide 14 ft, long including thirudder and about 6 ft. Was not necessary to take the machine apart in any way in order to house it. Both ends off the building except the gable parts were made into doors, which hinged above, saw that when opened they formed an awning gate at end, and left an entrance the full width off the building. We went in Tawkemp about the middle of July, and were soon joined by Mr. E.C. Huffaker, of Tennessee, an experienced aeronautical investigator and employee of Mr. Cha New, by whom his services were kindly loaned, and be Dr. G. A. Spratt of Pennsylvania, a young man who has made some valuable investigations off the properties of variously curved surfaces and the travel off the center of pressure thereon. Early in August, Mr. Chanuk came down from Chicago to witness our experiments and spent a week in camp with us. The machine was completed and treated for the first time in July 27th in Nowend, blowing about 13 miles an hour. The operator having taken a position where the center of pressure was supposed to, an attempt at gliding was made. But the machine turned downward and landed after going only a few yards. This indicated that the center of gravity was too far in front of the center of pressure. In the second attempt, the operator took a position several inches further back, but the result was much the same. He kept moving further and further back with each trial, till finally he occupied a position nearly a foot back off that at which we expected to find the center of pressure. The machine then sailed off, and made an angulet in flight of a little more than 300 ft. To the onlookers, this flight seemed very successful, but to the operator, it was known that the full power off the rudder had been required to keep the machine from either running into the ground or icing so high as stallos all headway. In 1900 machine, 1/4 as much rudder action had been sufficient to give a much better control. It was apparent that something was radically wrong, though we were for some time unable to locate the trouble. In one glide, the machine rose higher and higher till it lost all headway. This was the position from which Lilienthal had always found difficulty extricating himself. Ash's machine then, in spite of his greatest exertions, manifested a tendency to dive downward almost vertically and strike the ground head-on with frightful velocity. In this case, a warning cry from the ground caused the operator to return the rudder to its full extent, and also to move his body slightly forward. The machine then settled slowly to the ground, maintaining its horizontal position almost perfectly, and landed without any injury at all. This was very encouraging, as it showed that on off the very greatest dangers in machines with horizontal tail should be overcome by the off a front rudder. Several glides later, the same experience was repeated with the same result. In J.R. 6, Wright Brothers Experiments of 1900, 1 a high glide, 2 a low glide, 3 landing ladder case, the machine had been commenced to move backward, but was nevertheless brought safely to the ground in a horizontal position. On the whole, this day's experiments were encouraging, for while thiction off the rudder didn't seem 12 at like that off our 1900 machine, yet we had escaped without difficulty from positions which had proved very dangerous to preceding experimenters, and after less than 1 minute's actual practice, had made a gliddy off more than 300 feet, at an angle of descent of 10 degrees, and with a machine near it was as large as had previously been considered safe. The trouble with its control, which has been mentioned, we believed could be corrected when we should have located its cause. Several possible explanations occurred too, but we finally concluded that the trouble was due to reversal off the direction off the travel off the center of pressure at small angles. In deeply curved surfaces, the center of pressure at 90 degrees is not the center off the surface, but moves forward as the angle becomes less, till a certain point is reached, varying with the depth of curvature. After this point is passed, the center of pressure, instead of continuing to move forward with the decreasing angle, turns and moves rapidly towards their R. The phenomena are due to the effect that, at small angles, Thewin strikes the forward part of the surface on the upper side instead of the lower, and thus, this part altitude there ceases to lift, instead of being the most effective part of all, as in the case of the plane. Lilienthal had called attention to the danger of using surfaces with a curvature as great as shown in 8, on account of this action on the upper side. But seems never to have investigated the curvature and angle which the phenomenon says. My brother and I had never made any original investigation off the matter, but assumed that a curvature of 1 in 12 would be safe, as this was the curvature on which Lilienthal based his tables. However, to be on the safe side, instead of using the arcofascicle, we had made the curve off our machine very abrupt at Heffron, so as to expose the least possible area to this downward pressure. While the machine was building, Messrs. Huffaker and Spratt had suggested that we would find this reversal off the center of pressure, but we believed it sufficiently guarded against. Accordingly, we were not at first disposed to believe that this reversal actually existed in our machine, although it offered a perfect explanation of thiction we had noticed in gliding. Our peculiar plan of control by forward surfaces, instead of tools, was based on the assumption that Fig. 7. C. Chord, PR center of pressure, G. center of gravity, 13. Center off pressure would continue to move farther and farther forward, as the off incidence became less, and it will readily perceive that it would make quite a difference if the front surface, instead of counteracting this assumed forward travel, should in reality be expediting an actual backward movement. For several days we were in a state of indecision, but were finally convinced, by observing the following phenomena, Fig. 7. We had removed the upper surface from the machine and were flying it now and to see what angles it would be supported in winds of different strengths. We noticed that, in light winds, it flew in the upper position, X shown in the figure, with a strong upward pull on the cord, C. As the wind became stronger, the off incidence became less, and the surface flew in the position shown in the middle of the figure, with a slight horizontal pull. But when the wind became still stronger, it took the lower position shown in the figure, with a strong downward pull. It attons occurred to that here was the answer to a problem, for it is evident that in the first case, the center of pressure was in front of the center of gravity and then pushed up the front edge. In the second case, they were in coincidence and the surface in equilibrium, while in the third case, the center of pressure had reached a point even behind the center of gravity, and there was therefore a downward pull on the cord. This point having been definitely settled, we proceeded to trace down the ribs off the whole machine, so to Fig. 8. The changes effected in the curvature of the plane as the result of experience, reduce the depth of curvature. In Fig. 8, line 1 shows the original curvature, line 2 the curvature when supporting the operator's weight, and line 3 the curvature after trussing. Complete success obtained. On resuming our gliding, we found that the conditions of the preceding year had returned, and after a few trials made a glide off 366 ft, and soon after one off 389 ft. The machine, with its new curvature, never failed to respond promptly to Evans' small movements off the rudder. The operator could cause it to almost skim the ground, following the undulations off its surface, or he could cause it to sail out almost o'neill with the starting point, and passing high above the foot off the hill, gradually settle down to the ground. The wind on this day was blowing 11 to 14 miles per hour. The next day, the conditions being 14 favorable, the machine was again taken out for trial. This time, the velocity off the wind was 18 to 22 miles per hour. At first, we felt some doubt as to the safety of attempting free flight in so strong a wind, with a machine off over 300 ft, and a practice off less than 5 minutes spent in actual flight. But after several preliminary experiments, we decided to try glide. The control off the machine seemed so good that we then felt no apprehension in sailing boldly forth. And thereafter, we made glide after glide, sometimes following the ground closely, and sometimes sailing high in the air. Mr. Chanute had his camera with him, and took pictures of some off the glides. We made glides on subsequent days, whenever the conditions were favorable. The highest wind use experimented in was a little over 12 meters per second, nearly 27 miles per hour. It'd been our intention, when building the machine, to do the larger part of the experimenting in the following manner. When the wind blew 17 miles an hour or more, we would attach a rope to the machine and let it try to sack height with the operator up in it. When it should reach a proper height, the operator would cast off the rope and glide down to the ground just as from the top of a hill. In this way, we would be saved the trouble of carrying the machine uphill after each glide, and could make at least 10 glides in the time required for owning the other way. But when we came to try it, we found that a wind of 17 miles, as measured by Richard's anemometer, instead of sustaining the machine with its operator, a total weight of 2,401 b, at an angle of incidence of 3 degrees, in reality would not sustain the machine alone all. At high's angle, its lifting capacity seemed scarcely 1/3 off the calculated amount. In order to make sure that this was not due to the porosity of the cloth, we constructed 2 small experimental surfaces of equal size, one of which was airproofed and the other left in its natural state. But we could detect no difference in their lifting powers. For a time, were led to suspect that lift of curved surfaces little exceeded that of planes of the same size, but further investigation and experimental taught the opinion that 1. The anemometer used buse over recorded the true velocity off wind by nearly 15%. 2. That the well-known Smeaton coefficient of 0.005 v2 fourth wind pressure rate 90 degrees probably to grade by at least 20%. 3. That Lilienthal's estimate that the pressure on a curved surface having an angle off incidence of 3 degrees equals 545 off the pressure off 90 degrees is too large, being nearly 50% greater than very recent experiments of her own with a special pressure testing machine indicator. For that, the superposition of the surfaces somewhat reduced the lift per square foot, as compared with a single surface of equal area. The importance of the ratio of lift to drift. In gliding experiments, however, the amount of lift is of less relative importance than the ratio of lift to drift, as this alone decides the of gliding descent. In a plane, the pressure is always perpendicular to the surface, and the ratio of lift to 15. Drift is therefore the same as that off the cosine to the sine off angli off incidence. But in curved surfaces, a very remarkable situation is found. The pressure, instead of being uniformly normal to the chord off there, is usually inclined considerably in front off the perpendicular. The result is that the lift is greater and the drift less than if the pressure were normal. Lilienthal was first to discover this exceedingly important fact, which is fully set forth in his book, Bird Flight, Basis of Flying Art. But owing to some errors in methods used in making measurements, question was raised by other investigators not only as to the accuracy of his figures, but even as to the existence of any tangential force at all. Our experiments confirm the existence of this force, though our measurements differ considerably from those of Lilienthal. While at Kitty Hawk, we spent much time in measuring the horizontal pressure on our unloaded machine at various angles of incidence. We found that at 13 degrees, the horizontal pressure was about 231 B. This included not only the drift proper, or horizontal component of the pressure on the side of the surface, but also the head resistance of the framing gas well. The weight of the machine at head time of this test was about 1081 B. Now, if the pressure had been normal to the chord off the surface, the drift proper would have been to the lift, 1081 B. As sine of 22x 108 13 degrees is to the cosine of 13 degrees equals 24 if 97, but this slightly exceeds the total pull of 231 B on our scales. Therefore, it is evident that the average pressure on the surface, instead of being normal to the chord, was so far inclined toward the front that old head resistance off framing and wires used in the construction was more than overcome. In a wind of 14 miles per hour, resistance is by no means a negligible factor. So the tangential force is evidently a force of considerable value. Now higher wind, which sustained the machine at an angle of 10 degrees, the pull on the scales was 181 B. The pressure normal to the chord, the drift proper would have 17x 98 been equals 171 B. So that although the higher wind, 98 velocity must have caused an increase in head resistance, the tangential force still came within lib, off overcoming it. Pressures on curved surfaces. After our return from Kitty Hawk, I began a series of experiments to accurately determine the amount and direction of the pressure produced on curved surfaces when acted upon by winds at various angles from 0 to 90 degrees. These experiments are not yet concluded, but in general, they support Lilienthal and the claim that the curves give pressures more favorable in amount and direction than planes. But we find marked differences in the exact values, especially at angles below 10 degrees. We were unable to obtain direct measurements of 16 Big 9 the machine of 1900 showing forward elevation plane. Horizontal pressure is off the machine with the operator on board, but by comparing the distance traveled in gliding with the vertical fall, it was easily calculated that, at a speed of 24 miles per hour, the total horizontal resistances off our machine when bearing the operator amounted to 401 B, which is equivalent to about 2 HP. It must not be supposed, however, that a motor developing this power would be sufficient to drive a bearing machine. The extra of the motor would require either a larger machine, higher speed, or a greater angle of incidence in order to support it, and therefore more power. It is probable, however, that an engine of 6 HP, weighing LO would answer the purpose. Such an engine is entirely practicable. Indeed, working motors of 1/2 this weight per horsepower, 91 B, or horsepower, have been constructed by several different builders. Increasing the speed of our machine from 24 to about 33 miles per hour reduced the total horizontal pressure from 40 to about 351 B. This was quite an advantage in gliding as it made it possible to sail about 15%, further with a given drop. However, it would be of little or no advantage in reducing the size of the motor in a power-driven machine, because the lessened thrust would be counterbalanced by the increased speed per minute. Some years ago, Prof. Langley called attention to the great economy of thrust which might be obtained by using very high speeds, and from this many were led to suppose that a speed was essential to success in a motor-driven machine. But economy to which Prof. Langley called attention was in foot-pounds per mile off travel, note in foot-pounds per minute. It is the foot-pounds per minute that fixes the size of the motor. The probability is that the first flying machines will have a 17 B, relatively low speed, perhaps not much exceeding 20 miles per hour, but the problem of increasing the speed will be much simpler in some respects than that of increasing the speed of a steamboat. For whereas in the latter case the size of the engine must increase as the cube of the speed in the flying machine until extremely high speeds are reached, the capacity of motor increases in less than simpler ratio, and there is then a decrease in the fuel consumption per mile off travel. In other words, audible the speed of a steamship, and the same is true of the balloon type of airship. 8 times the engine and boiler capacity would be required, and 4 times the fuel consumption per mile off travel, while a flying machine would require engines of less than double the size, and there would be an actual decrease in the fuel consumption per mile off travel. the relative efficiency of the flying machine. Looking at the matter conversely, the great disadvantage of the flying machine is apparent. For in the latter, no flight at all is possible unless the proportion of horsepower to flying capacity is very high. But on the other hand, a steamship is a fig. 10. The 1900 machine, under view. Mechanical success if its ratio of horsepower to tonnage is insignificant. A flying machine that would fly at a speed of 50 miles an hour with engine s-awful 000 h.p. would not be felled by its wing saddle at a speed of less than 25 miles an hour, and nothing less than 500 h.p. could drive it at this speed. Butte a boat which could make 40 miles per hour with engine s-awful 000 h.p. would still move 4 miles per hour even if 18 engines were reduced to I.p. The problems of land and water travel were solved in the 19th century, because it was possible to begin with small achievements and gradually work up to a present success. The flying problem was left over to the 20th century, because in this case, thought must be highly developed before any flight of any considerable duration can be obtained. However, there is another way of flying which requires no artificial motor, and many workers believe that success will first come by this road. I are for the soaring flight by which the machine is permanently sustained in the same means that are employed by soaring birds. They spread their wings to the wind and sail by the hour with no perceptible exertion beyond that required toe balance and steer themselves. What sustains them isn't definitely known, though it is almost sur fig. 11. A soaring flight, the machine being practically at a standstill. Tain't that it is a rising current off-air. Whether it be a rising current or something else, it is as well able to support a flying machine as a bird, if man once learns thought of utilizing it. In gliding experiments it has long been known that the rate of vertical descent is very much retarded and the duration of the flight greatly prolonged if a strong wind blows up the face of the Hilperallo Teucherfiss. Our machine, wing gliding in still air, has a rate of vertical descent of nearly 6 ft per second. While now in blowing 26 miles per hour up a stiefel were made glides in which the rate of descent was less than 2 ft per second. And during the larger part of this time, 19b2, Big 12. The 1900 machine soaring in a wind of 35 mph. While the machine remained exactly in the rising current, there was nodes in all beauty and a slight rise. If the operator had had sufficient skill to keep himself from passing beyond the rising current, he would have been sustained indefinitely at a higher point than that from which he started. The illustration shows one of these very slow glides at a time when the machine was practically at a standstill. These slow glides in rising currents probably hold out greater hope of extensive practice than any other method within man's reach, but they have the disadvantage of requiring rather strong winds or very large supporting surfaces. However, wing gliding operators have attained greater skill. They can, with comparative safety, maintain themselves in 3 or 4 hours at a time in this way, and thus by constant practice so increase their knowledge and skill that they can rise into the higher and search out thicker rents which enable the soaring birds to transport themselves to any desired point by first rising in a circle and then sailing off at a descending angle. The illustration, Fig. 12 shows the machine alone, lying in a wind of 35 miles per hour on, face off a stiefel 100 ft high. It will be seen that the machine not only pulls upward, but also pulls forward in the direction from which the wind blows, the use overcoming both gravity and the speed of the wind. Wet read the same experiment with a man in it, but found danger that the forward pull would become so strong that the men holding the ropes would be dragged from their insecure foothold on the slope of the hill. Sothai's form of experimenting was discontinued after 4 or 5 minutes trial. Conclusions of 1901. In looking over our experiments of the past years with models and full-size machines, the following points stand out with clearness. 1. That the lifting power of a large machine held stationary and now and at a small distance from the earth is much less than the Lilienthal table and our own laboratory experiments would lead us to expect. When the machine is moved through the air, as in gliding, the discrepancy seems much less marked. 2. That the ratio of drift to lift in well-shaped surfaces is less at angles of incidence of 5 degrees to 12 degrees than at an angle of 3 degrees. 3. That, in arch shed surfaces, the center of pressure at 90 degrees is near the center of the surface, but moves slowly forward as the angle becomes less, till a critical angle varying with the shape and depth of the curve is reached, after which it moves rapidly toward there are till the angle of no lift is found. Or that, with similar conditions, large surfaces may be controlled with not much greater difficulty than small ones, if the control is effected by manipulation of the surface themselves, rather than by a movement of the body of the operator. 5. That the head resistances of the framing can be brought to a point much below that usually estimated as necessary. 6. That ails, both vertical and horizontal, may with safety be eliminated in gliding and other flying experiments. 7. The horizontal position of the operator's body may be assumed without excessive anger, and this head resistance reduced to about 1/5 that of the upright position. 8. that a pair of superposed or tandem surfaces has less lift in proportion to drift than either surface separately, even after making allowance for weight and head resistance off the connections. Fig. 13. The manner in which thewings offer Wright aeroplane adwar. The left and soft thewings are raised and the right and step rest for return to the left, drawn from one off the latest machines. 21. Later experiments off the Wright brothers in soaring flight. Related by Wilbur Wright before the Society of Western Engineers of Chicago, June 1, 1903. In Thedress, which I delivered before the Society of Western Engineers in September 1901, some account was given of the gliding experiments made by my brother Orville Wright and myself in Thayers 1900 and 1901. Afterwards, laboratory experiments were undertaken for the purpose of determining for ourselves the amount and direction of the pressures produced by thewing upon plane and dark surface exposed at various angles of incidence. Their sulchiving indicated the possibility of a gliding machine capable of much better performance than in a previously built piece. Westatab out designing 1902 season, and in August, repaired 2-year-old camp at Heck-Kill Devil Hills. The 1902 pattern was a double-deck machine having 2 surfaces, each 32 ft. From tip to pan 5 ft. From front to rear. The total area off the main surfaces was about 305 sq. ft. The front rudder spread 15 sq. ft. Additional and the vertical tail about 12 sq. ft, which was subsequently reduced to 6 sq. ft. Thew weight was 116 b, including the apparator. The total weight was from 2,501 b to 2,601 b. It was built to withstand hard usage and nearly 1,000 glides was injured butants. It repeatedly withstood without damage the immense strains arising from landing at full speed in a slight hollow where only the tip-off thewings touched the earth. The entire weight, machine and operator being suspended between. The practice ground at Heck-Kill Devil Hills consists of oval plain of bare sand, from which rises a group of detached hills or mounds formed off sand heaped up bituins. These hills are constantly changing in height and slow, according to the direction and force of the prevailing winds. The 3YH Wusa gliding experiments are known as Big Hill, the Little Hill and the West Hill, and have heights of 100 ft, 30 ft, and 60 ft, respectively. In accordance with our custom of ginning operations with the greatest possible caution, we selected the Little Hill as field of our first experiments, and began by flying the machine a sackite. The object of this was to determine whether or not it would be capable of soaring Gina wind having an upward trend of a trifle over 7 degrees, which was the slope of hill up which the current was flowing. When is speak of soaring a mean not in lith at the weight of the machine is fully sustained, but also that the direction of the pressure upon the wings is such that the propelling and 22 retarding forces are exactly in balance. In other words, the resultant oval pressure is exactly vertical, and therefore, without any unbalanced horizontal component. A kite is soaring when the string stands exactly vertical, this showing that there is no backward pull. The phenomenon is exhibited only when the kite is flown in a rising current of air. In principle, soaring is exactly equivalent to gliding, the practical difference being that in one case thewing moves with an upward trend against a motionless surface, while in the other the surface moves with a downward trend against motionless air. The reactions are identical. The soaring of birds consists in gliding downwards through a rising current of air, which has a rate of ascent equal to the bird's relative rate of descent. Testing a gliding machine a sackite on a suitable slope, with just enough wind to sustain the machine at its most favorable angle of incidence. I saw off the most satisfactory methods of determining its efficiency. Soaring, the kite must fly steadily with the string vertical or a little to the front. Merely darting up to this position for an instant isn't soaring. On trail, we found that the machine would soar on the side off a hill having a slope off about 7 degrees, whenever the wind was off proper force to keep thingly off incidence between 4 and 8 degrees. If the wind became too strong or too weak, the ropes would incline toluid. The companion illustration, Fig. 14 was taken when thewing was too weak for real soaring. The surfaces are inclined 4 degrees above the horizon, which is marked by the ocean level and distance. Since the wind had an upward trend of 7 degrees, the total angle of incidence was 11 degrees, which is outside the limits specified. On steeper slopes, the ropes inclined to windward quite strongly. Next, experimenting in this planet is essential that a uniform slope be found which will give a the current rising trend just sufficient to cause the Fig. 14. The 1902 machine flown a sackite string to kite an allied wind. Stand vertical, and both gravity and the pull on this string, which together provide the force counteracting thewing pressure on the surfaces, area split in a single direction. It is, therefore, not material what proportion of the total counteracting force is due to watch off the several components, nor even what is their total amount, because the experiment is exclusively for the purpose of determining the direction of the pressure on the surfaces by observing the direction off the Rikshan. And the kite string inclines toeindward, the slope is too steep. If lured, not steep enough. But it is not advisable to determine how much the slope varies from the proper amount by observing thingly off the string from the vertical. For, when the pull off the string differs in direction from that of gravity, it becomes necessary to know not in the thingle, butyl so the exact amount off the pull in the proportion which it bears to off the kite. It is, therefore, advisable to find a better slope rather than attempt to make so many observations. Fig. 15. A glide with the double tail machine. The kit experiments having shown that iter bepo sibyl to glide on 7-degree slope, when proceeded to it. Although, on Thai's first day, it was not considered advisable to venture up on any absolutely free flights, the machine soon demonstrated its ability to glide with this angle of descent. At a latter period we made more than 100 flights the full length off this low pan landed a short distance out on the level ground. On the second day the machine was taken to the big hill and regular gliding was commenced. The wind was somewhat brisk. In one flight Thuen struck the machine from the left and began lifting the left wing in a decidedly alarming manner. Owing to the fact that, in the new machine, changes had been made in the mechanisms operating the rudders, so that the movements were exactly reversed, it was necessary to think. 24. A moment before proceeding to make the proper adjustment. But meanwhile the left wing was rising higher and higher. I therefore decided to bring the machine to the ground as quickly as possible, but in my confusion forgot the change that had been made in the front rudder, and instinctively turned it the wrong way. Almost instantly it reared up as though bent on a mad attempt to pierce the heavens. But after a moment, seemed to perceive the folly of such undertaking and gradually slowed up till it came almost toast up with the front off the machine still pointing heavenward. By this time I had recovered myself and reversed the rudder to its full extent, at the same time climbing upward toward the front so to bring my weight over on the part that was too high. Under this heroic treatment the machine turned downward and soon began to gather headway again. By the time the ground was reached, it was under fair control. Sonwing touched it first. It swung around inlanding and came towards with the wind blowing in from there. There was now unusual shock inlanding and no damage resulted. Fig. 16. Rear view of machine with single tail. In several other glides there were the disturbances off lateral equilibrium more marked than we had been accustomed to experience with the former machines, and we were at a loss to know what the cause might. The new machine had a much greater tip-to-tip dimension than our former machines. It also had a vertical tail, while the earlier ones were tailless, and the wing tips were on a line with the center, while the old machines had the tips drawn down like a gull's wings. The trouble might be due to either off these differences. We decided to begin alterations at hewing tips, and the next day made the nieces Sarah change synthetracing, thus bringing the tips gin lower than the center. For several days thereafter the Aviather was not suitable for gliding on account off-ran, but finally Theski cleared and the machine was taken out again. As the anemometer indicated our velocity off more than 11 meters a second, it was thought best to make use off Little Hill in 25, testing the effect off the changes that had been made. But later in the day, when the velocity fell to about 9 meters a second, the big hill was straight again. On this day my brother Orville did most off the gliding. After a few preliminary flights, to custom himself taught the new method of operating the front rudder, Hefel himself for ditto, undertake the management of the lateral control also. Shortly afterwards he started on a flight with onewing slightly higher than the other. This caused the machine to veer to the left. Hewitt at a moment to see whether it would right itself, but finding that it did not, then decided to play the control. At the very instant he did this, however, the right wing most unexpectedly rose much higher than before and led him to think that possibly he had made a mistake. A moment off that was required to assure himself that he had made the right motion and another to increase the movement. Meanwhile he had neglected the front rudder, by which the fore and aft balance was maintained. The machine turned up in front more and more till it assumed a most dangerous attitude. We who were on the ground noticed this in advance off the aviator, who was thoroughly absorbed in the attempt to restore the lateral balance. Buter shouts off alarm were drowned by the howling off Thuen. It was only when the machine came toast up and started backward that the realized the true situation. From the height of nearly 30 ft, the machine sailed diagonally backward till it struck the ground. Unlucky aeronaut had time for own hasty glance behind him and the next instant found himself the center of a mass of littering wreckage. How he escaped injury I do not know, but afterwards he was unable to show a scratch or bruise anywhere, though his clothes were torn in one place. This little misadventure, which occurred almost at every beginning golfer practice with the new machine, was the only thing approaching an accident that happened during these experiments, and was the only occasion on which the machine suffered any injury. A letter was made as good as newbie for day's labor, and was not again broken in any of the many hundred slides which were subsequently made with it. By long practice, the management of a flying machine should become as instinctive as the balancing movements Ammon unconsciously employs with every step in walking. But in the early days, it is as to make blunders. for the purpose of reducing the danger to the lowest possible point, usually kept close to the ground. Often, gliding off several hundred feet would be made at a height of 50 feet or even of winches sometimes. It was themed to avoid unnecessary risk. While the high flights were more spectacular, the low ones were fully as valuable for training purposes. Skill comes by the constant repetition of familiar feats, rather than be over bold attempts at feats for which the performer is yet really prepared. It had been noticed during the day that, when a side gust struck the machine, its effect was at first partly counteracted by the vertical tail. But after a time when the machine had acquired a lateral motion, the tail made matters worse instead. 26. Bitter, although the change that had been made in the wingtips made some improvement, the lateral control still remained somewhat unsatisfactory. The tail was useful at times and at others was seriously in the way. It was finally concluded that the best way of overcoming the difficulty was by making the tail movable like a rudder. As originally built, the fixed vertical tail or vane was double, but in changing to a movable rudder, it was made single, as the smaller area was believed to be sufficient. So reconstructed, it spread a little less than 6 square feet. With this improvement, our serious troubles ended, and thereafter we devoted ourselves to the work of gaining skill by continued practice. When properly applied, the means of control proved to possess a mastery over the forces tending to disturb the equilibrium. Since balancing was affected by adjustments off the surfaces, instead of the movements off weight, the controlling forces increased in power in the same ratio as these turbing forces. When the machine was suddenly struck by a wind gust, or this reason, why didn't it seem to experience the same difficulty in managing the machine in high winds that Lilienthal, whilst a different system, seems to have met. Fully half offer glides were made in winds of 10 meters a second, over 20 miles an hour. One day we stopped gliding for a moment, towed a canometer reading and found that it indicated 16.7 meters a second, 37 miles an hour. Of course, such high winds require much greater readiness on the part of the operator than the low winds, since everything happens much more quickly, but otherwise, the difference is not so very marked. In those machines which are controlled by the shifting off weight, the disturbing influences increases the square off velocity, while the controlling factor remains a constant quantity. For this reason, a limit to in velocity which it is possible to safely encounter with such machines is soon reached, regardless of skill of the operator. With the method we have been using, the capacity of control is evidently very great. The machine seems to have reached a higher state of development than the operators. As yet, we consider ourselves little more than novices in management. 1,000 glides is equivalent to about 4 hours of steady practice, far too little to give anyone a complete mastery of the art of flying. Progress is very slow in the preliminary stages, but when once it becomes possible to undertake continuous soaring, advancement should be rapid. Under special conditions, it is possible that this point is not so far away as might be supposed. Since a soaring is merely glid in generalizing current, it would be as he to soar in front of an hill off suitable slope, whenever the wind blew with sufficient force to furnish support, provided the wind were steady. But by reason of change in wind velocity, there is more support at times than is needed, while at others there is too little, so that a considerable degree of skill, experience, and sound judgment are required in order to keep the machine exactly in the rising current. So far, our only attempts at soaring have been made on the little hill, which, 27, has a slope of only 7 degrees. In our wind blowing from 11 to 16 meters a second, we frequently made glides of 8 to 15 seconds duration with very little forward motion. A sway kept within 5 ft, or 6 ft, off the ground, a momentary lessening of the in speed, or a slight error in management, was sufficient to bring about a landing in a short time. The wind had too little rising trend to make soaring easy. The buzzards themselves were balked when they attempted to soar on this hill, as we observed more than oyas. It would be well within the power of the machine to soar on big hill which has steeper slopes, but we have not felt that our few hours of practice is sufficient to justify ambitious attempts too hastily. Before a train to rise to any dangerous height an asterisk. Asterisk 5 I fig. 17. Starting gafflight. Ought know that, in an emergency, his mind and muscles win work by instinct rather than by conscious effort. There isn't time to think. During a period of 5 weeks, glides were made whenever the wind conditions were favorable. Many days were lost in account off rain. Still more were lost in account off light winds. Whenever the breeze fell below 6 miles an hour, very hard running was required to the machine started, and the task of carrying it back up the hill was real labor. A relative speed of at least 18 miles an hour was required for gliding, while to obtain a speed of 12 miles by running required very for exertion. Consequently, unless the wind blew in our faces with a speed of at least 6 miles, we did not usually attempt to practice. But when the wind rose to 20 miles an hour, gliding was real sport. For starting, Wasasi and the labor of carrying machine back a hill was performed by the wind. On the day when the wind rose to over 16 meters a second, we made more than 100 glides with much less physical exhaustion then resulted from 20 or 30 glides ondays when the wind was slight. 28. La completa record waskip the glides made during the season. In the last 6 days of experiment, we made more than 375, but these included our varibus days. The total number for the season was probably between 700 and 1,000. The longest glide was 622 ft, and the time 26 sec. The prime object in these experiments was to obtain practice in the management of a carrying machine. Utin object of scarce importance was to obtain data for the study of scientific problems involved in flight. Observations real most constantly being made for the purpose of determining the amount and direction of the pressures upon the sustaining wings, the minimum speed required for support, the speed and angle of incidence at which the horizontal resistance became least, and the minimum angle of descent at which it was possible to glide. To determine any of these points with exactness was found to be very difficult indeed. But by careful observations under test conditions, it was possible to obtain reasonably close approximations. It was found that a speed of about 16 miles an hour would produce a sufficient to support machine and operator, but the angle of incidence was too great for general gliding purposes. At 18 miles, the angle of incidence was about 8 degrees, and the machine would glide on little hill, descending at an angle of a little over 7 degrees. Although Thewing and Fig. 18, making a turn to the right, were inclined slightly above the horizon, the machine continued to glide without loss of velocity. With a speed of 22 miles an hour, the angle of incidence required for support was 4 or 5 degrees, and the angle of descent a little less than 7 degrees. At his speed, the surfaces were inclined several degrees below the horizon. As the speed became greater, the angle of incidence continued to grow less, but the angle of descent became greater again, thus showing that the point of minimum resistance had been passed. Scores of glides were made at angles of descent under 6 degrees, and in a few cases were at 5 degrees. On the last day of experiment, we made a Wadham's at records. A line was drawn a short distance up the slope as starting 29. Arc and for trials were made. Twice the machine landed on the same spot. The distance was 156 ft, and the angle of descent exactly 5 degrees, time 6 sec. From a point higher up the slope, the best angle was 5 degrees and 25 min. For a glide of 225 ft, time LO sec. The wind was blowing about 9 miles an hour. The glides were made directly to windward and straight down the slope. King 7 degrees as a conservative estimate off the normal angle of descent, the horizontal resistance off the machine was 301 b, as computed by multiplying total weight, 2,501 b, by the tangent off the angle of descent. This resistance remained nearly constant at speeds between 18 and 25 miles an hour. Above or below these limits, there was a somewhat rapid increase. At 18 miles, the power consumed wassail HP. At 25 miles, 2 HP. At lower speed, 1,661 B, was sustained 4 horsepower consumed. At higher speed, 1,251 B per horsepower. Between 18 and 25 miles, the horsepower increased almost inexact ratio and the increase in speed. But above or below these limits, the power increased rapidly, and with a constantly accelerating ratio. On 2 occasions, we observed a phenomenon whose nature we were notable to determine with certainty. One day me brother noticed, in several glides, a peculiar tapping, as if some part off the machine were loosing flapping. Careful examination failed to disclose anything about the machine which could possibly cause it. Some weeks later, while he was making a glide, the same peculiar tapping began again amidst of a wind gust. It felt like little waves striking the bottom of a flat-bottomed rowboat. While he was wondering what the cause could be, the machine suddenly, but without any notice able change in its inclination to the horizon, drop at a distance off nearly 10 ft, and in that winkling of fane was flat on the ground. I am certain that the gust went out with a downward trend, which struck the surfaces on the upper side. The descent was at first more rapid than that due to gravity, for my body apparently rose off the machine till my hands and feet touched it. Toward the descent was slower. It may be that upping was caused by the wind rapidly striking the surface alternately on the upper and the lower sides. It is a rule most universal that gusts come on with a rising trend and out with a descending trend. But on these particular occasions, it must have been a most unusual turmoil during the continuance of the gust which would have exhibited a very interesting spectacle had it been visible to the eye. Irregularities of the wind at most noticeable when the wind ishai, on account of the greater power then exhibited, but light winds show almost equal relative variations. An aviator must expect to encounter in every flight variations in velocity, in direction, and an upward or downward trend. These variations not only give rise to those disturbances off the equilibrium, which result from the travel off the center of pressure due to that changed angle of incidence, but also, by reason of the fact that the wind changes do not occur simultaneously or uniformly over the entire machine, give rise to a second series of disturbances often more troublesome character. Thus, a 30. As coming on very suddenly will strike the front off the machine and throw it up before Thebak, parsacted up and at all. Or the right wing may encounter a wind off a different velocity and trend. From the left wing and the machine will tend totter and over sideways. The problem of overcoming these disturbances by automatic means has engaged the attention of many very ingenious minds. But Tomabrother and myself, it has seemed preferable to depend entirely on intelligent control. In all offer machines, the maintenance of the equilibrium has been dependent on skill and constant vigilance of aviators. In addition to work with the machine, we also made many observations on the flight of soaring and 19. Skimming the ground, birds, which were very abundant in the vicinity of our camp. Bald eagles, ospreys, hawks, and buzzards gave us daily exhibitions of their powers. The buzzards were the most numerous and were the most persistent soarers. Apparently never napped except when it was absolutely necessary, while the eagles and hawks usually soared only when they were at leisure. Two methods of soaring were employed. When the weather was cold and damp and the wind strong, the buzzards would be seen soaring back and forth along the hills, or at the jafaklampoff trees. They were evidently taking advantage of the current of air flowing upward over these obstructions. On such days they were often utterly unable to soar except in these special places. Butin warm, clear days when thew and was light, they would be seen high in the air soaring in great circles. Usually, however, it seemed to be necessary to reach a height of several 100 feet beflapping before this style of soaring became possible. Frequently a great number of them would begin circling in one spot, rising together higher and higher till finally they would disperse, each gliding off in avhatever direction it wished to go. At such times, other buzzards only a short distance away found it necessary to flap frequently in order to maintain themselves. But when they reached a point beneath the circling flock, they began to rise in motionless wings. This seemed to indicate that rising columns offered on exist everywhere, but that the birds must find them. They evidently watch each other, and when one finds a rising current, the others quickly make their way to it. One day, when scarce a breath of wind was stirring on the ground, we noticed two bald eagles sailing in circling sweeps at a height of probably 500 ft. 31. After our attention was attracted to the hashing of some object considerably lower down. Examination with a hilgeless proved it to be a feather which one of the birds evidently cast. As it seemed apparent that it would come towards only a short distance away, some offer parties started towards it. But in a little while it was noticed that the feather was no longer falling, but on the contrary was rising rapidly. It finally went out of sight upward. It apparently was drawn into the samarizing current in which the eagles were soaring, and was carried up like the birds. Today's hen thew and blue horizontally gave us the most satisfactory observations, as then the birds were compelled to make use of the currents flowing up the sides of the hills, and it was possible for us to measure the velocity and trend of the wind in which the soaring was performed. One day 4 buzzards began soaring on the northeast slope of the big hill at a height of only 10 ft, or 12 ft, from the surface. We took a position to windward and about 200 ft distant. The clinometer showed that they were 4 to 5 degrees above our horizon. We could see them distinctly with a fieldglass. When facing us, the underside off their wings made a broad band on sky, but when, encircling, they faced from us, we could no longer see the underside off their /wings. Though thewings then made a little more than a line in Thesky, the glass showed clearly that it was not the underside that we saw. It was evident that the buzzards were soaring with their wings constantly inclined about 5 degrees above the horizon. They were attempting to gain sufficient altitude to enable them to glide to the Asian beach 3/4 of a mile distant, but after reaching a height of about 75 ft. Above the top of the hill, they seemed to be unable to rise higher, though they treat a long time. At last they started to glide toward the Asian, but were compelled to begin flapping almost immediately. We'd also measured the slope and the wind. The former was 12 degrees, the latter was 6 to 8 meters per second. Since Fig. 20, one of the most satisfactory flights. 32. The newings were inclined 5 degrees above the horizon and the wind had a rising trend, often 12 degrees. The Inglia inside dense was about 17 degrees. Thewen didn't average more than 7 meters 15 miles an hour. For the most part, birds faced the wind steadily. Butin hills they were compelled to circle or glide back and forth in order to obtain speed sufficient to provide support. A buzzard weighs about 81 b per square foot off-wing area. A lifting power off Thewen at 17 degrees angly off incidence was apparently as great as it would have been had it been blowing straight upward with equal velocity. The pressure was inclined 5 degrees in front of the normal, and thingly off the descent was 12 degrees. On another day, I stood on a poff, West Hill, directly behind a buzzard which was soaring on the steep southern slope. It was just an oval with me and not more than 75 ft. distant. For some time it remained almost motionless. Although thewings were inclined about 5 degrees above the horizon, it was not driven backward by Thewen. This bird is specially adapted to soaring at large angles off incidence in strongly rising currents. Its wings are deeply curved. Unless the upward trend amounts totally state degrees, it seems tobunable to maintain itself. One day we watched a flock attempting to soar on through a slope off Big Hill, which hasades sent off nearly 9 degrees. The birds would start near the top and glide down along the slope very much as we did with the machine. But we noticed that whenever they glided parallel with the slope, their speed diminished, and when their speed was maintained, the if descent was greater than that off the hill. In every case they found it necessary to flip before they had gone 200 ft. They tried time and again, butyl ways with the same results. Finally, they resorted to hard flapping until a height of about 150 ft above the top of the hill was reached, after which they were able to soar in circles without difficulty. On another day, they finally succeeded in rising on almost the same slope, from which it was concluded that the buzzard's best angle of descent could not be far from 8 degrees. There isn't a question in my mind that man can build wings having as little as or less relative resistance than that of the best soaring birds. The bird swings are undoubtedly very well designed indeed. It is not the extraordinary efficiency that strikes with astonishment, but rather the marvelous skill with which they arrost. It is true that I have seen birds perform soaring feats of most incredible nature in positions where it was not possible to measure the speed and trend off the wind. But whenever it was possible to determine, by actual measurement, the conditions under which the soaring was performed, it was to see to count for it on the basis of results obtained with artificial wings. The soaring problem is apparently not so much one of bitter wings as of bitter operators. 33. The Man and Machine, caricature of Wilbur Wright by Mitch. Setting by the motor artist. 34. The principles underlying human flight. There are 3 stages in which the study of the principles of aviation must be taken, whether the investigation be experimental or theoretical. It is necessary first to discover means whereby the which is to be carried can be supported in the air. Secondly, the machine must be so designed that, when in the air, it will not capsize if its direction is altered slightly or if the velocity of the wind changes. Lastly, when an efficient glider has been evolved, action of a suitable propelling agency has to be considered, or in the words of Lilienthal, stability first, propulsion afterward. Everyone is aware of the force with which the wind can blow and off the pressure that it can exert on buildings and walls exposed to the fury of its blast. To utilize this force for lifting any weight into the air, some sort of exposed surface must be employed in such a manner that the wind, in blowing against it, exerts an upward supporting force. An ordinary kite is an example of the way in which this brings simplest put into practicalus, that the kite be represented as in Fig. 21 with the wind blowing as shown by the rows in direction AB, and with the string by which the kite is flown being pulled into direction CD. If the weight be fair enough back in the string properly fixed, the kite will be inclined at an angle to the wind, which, blowing upon the surface, will then exert a lifting force upon the kite. A diagram of forces acting on the kite is given in Fig. 22. There are a downward pull on the string in direction DC, the upward pressure of the wind, which may be considered as acting at center of pressure off the kite surface, and the weight of the kite. The force due to the latter acts downward at his center of gravity. When the kite is being flown in the air, these 3 forces are balanced, the tail supplying the steadying effect. As far, it is action of a wind blowing against a stationary surface that is being considered, but a similar lifting effect can be obtained if the air be still in the surface be moved through it. The inline condition is that the air must meet the surface at such an angle that a downward velocity be given to it after the plane has passed over it. The actual velocity of light that is required will depend on the 35 C2 mount off with that the stobe carried, and on the supporting surface that is used. The greater the toward less surface, the greater must be the speed of the machine, and vice versa. Just as in flying a kite in theory, a considerable pull must be exerted on the string by which it is flown, so in an aeroplane or glider which is in flight there must be force exerted to push it through air. This force has to overcome the resistance caused by pushing the framework, etc., off the machine through the air. And is similar in effect to that which has to be exerted to drive a car at high speeds. It is usually termed the drift, as distinguished from the upward or lifting force called the lift. Both lift and drift will vary considerably with different types of machines, with the loads carried and with the speeds off light. However, the area off supporting surface and the weight that the stobe carried both be limited. It is evident that, by triangulum off shapes off plane with varying cross sections and thicknesses, different values for the drift will be obtained, supposing that in each case theory were sufficient to support the weight. The most efficient shape would be that requiring the least force to push it through the air, that is, it would have the least drift. For this planet, the ratio of lift/drift would be the highest. The aim in designing an airplane is to make this value as high as possible, provide that it does not involve every high speed of light. It is well to investigate the factors on which the efficiency depends. iPhone could see the aeroplane meets it when gliding. It would be apparent that the air does not flow closely round the contour of the plane but forms a dead water region at back of the plane. The plane inclined at a large angle, the effect is much more pronounced, usually resulting in turbulence, i.e., a churning upov theor around the surface off plane. This turbulent effect requires energydosted in motion, so that iPhone obtains a certain lift with a plane thedrift will be much less if the turbulence can be eliminated. This is effected by making the cross-section off the plane is such that itis of streamlined form, so that theor flows evenly around with a minimum disturbance. The pioneer work in the experimental investigation of the best form toe-bust foreplane cross-section was carried out by Horatio Phillips, whose dipping front edge forms are treated in a separate chapter in the book. Phillips also advocates the off wood foreplane surfaces, because it forms a hard polished surface, offering much less resistance than a surface formed off canvas stretched over a frame. For Phillips' machine, described on page 46, wood was not out the best substance, but for the modern aeroplane, its weight would probably be excessive. In addition to the cross-section off the planes there is still planform tobe considered, and this, too, has a considerable effect on the efficiency. The ratio off the spread off the plane stow the fore and aft dip this usually termed the aspect ratio of the plane. It has been found experimentally with a planning 36. The span or spread is large compared with the fore and aft depth, or in other words, with where the aspect ratio is large, that the efficiency is much greater than where the span is smaller and the depth greater. Their asin for these will be easily understood from a consideration of figs 23 and 24, where there are shown planes of small and large span. SB of figs 23 and 24 showing aspect ratios. The air meets the cutting edge above the large span plane fig 23 and is deflected downwards at angle at which the plane is placed, causing a difference of air pressure between the upper and lower surface off the plane. This pressure difference between the above and below the plane tends to up a flow of air from below to above, with a greater loss of energy in the case of the small span plane with its wide ends than in the case of the narrow plane. In addition, practically the whole of the narrow plane surfaces is effective in acting on the, whereas with the wide plane their air just to a certain extent shielded by the front and exerts very little effect on the air, to which a downward velocity has already been imparted. Many of the modern aeroplanes have 1, 2, 3, and sometimes more surfaces or varied ways according to the inventor's design. Fig. 25. Superposed biplane. The single surface or monoplane acts upon air which is undisturbed both above and below the plane, where two planes are superposed as in Fig. 25. Even if the best based a good distance apart, the lifting effect is not was that off the single one, for the both act to certain extent on the some cushion off air. With atroplane or multiplane this relative diminution of lifting effort is even more pronounced. Instead of fitting the plane so now both the other they may be placed in tandem, as shown in Fig. 26. Fig. 27 shows themed view and how the air would flow round such an arrangement. The back plane would bane thuash off the front plane, and if placed addle close to the first stone, would have tobe inclined at a much greater angle to have any effect at all. It is doubtful if 37. Ed tilde figs. 26 and 27. Tandem biplane. The efficiency of the system is as high as the previous one, in which the planes are superposed. There are many combinations of the above two systems, such as saddle biplane, quadruplane, etc. In most machines, planes for steering and balancing are used in addition to the main planes, but they are small in comparison with the main ones, and do not need tobe considered in regard to their lifting effect. The stability of the machine when in theor depends on the movement off, center off pressure, off the supporting surface, and it will be well to consider this factor which has already been mentioned above. If as in Fig. 28 there is a wall of exposed to the force off the wind which is blowing in the direction dA, a certain pressure is exerted on the altending to blow it over. Instead of supposing the air robe rushing against the whole surface off the wall, it can be imagined to concentrate in one strong jet. By choosing the point on the surface where this jet should then act, there could be obtained just the same tendency for the wall toe blown over us with wind blowing over the whole surface. For the sake of clearness, the pressure due to wind is imagined tobe concentrated thus at a point. This point is termed the center of pressure. Turning to the study of an airplane, air. There are two forces acting up in it, the upward lift due to the air and the force due to it acting downward. The upward lift will act at center of pressure and the other force at the center of gravity. Fig. 29 represents this diagrammatically. A bysteam view of the aeroplane is the direction of the upward force, acting at the center of pressure C and D fifth weight acting downward at his center of gravity D. MC Fig. 29. Fig. 30. 38. Neglecting texture of propulsion for the moment. These are the inlet forces that need be considered, and if they are balanced there will be no tendency for the machine to capsize. As shown in Fig. 29, the center of pressure is ahead of the center of gravity, and if the state of affairs were allowed to continue the front of the machine would to pry it over. Some means must therefore be employed whereby if the machine is balanced when the aeroplane is inclined at a certain angle. The aeroplane will come back to the correct angle if the letter is altered. There are two ways of affecting this, one being by hand control as in the right machine and the other being more or less automatic. In the Wright machine, the tips off the planes are flexible, and their angli off incidence tathier conbelted by a controlling device operated by the aeronaut. This, in conjunction with the rudders, is continually in operation by the aviator. So that the center off pressure off the planes is made always to coincide with the center off gravity. Fig. 31. Fig. 32. Automatic stability depends for its action upon the movement off the position off the center off pressure when thingle off incidence varies. Asterisk, it is found that, as thingle off incidence decreases, the position off the center off pressure moves forward towards the frontage off the plane, and vice versa. This does not hold good for onort shapes off planes if thingle is less than 10 degrees, as will be explained later. When the angli off incidence increases, their verse takes place, the center off pressure moving backward away from the front edge. Let it be supposed that there is a plane A, B, C Fig. 30, moving through the in the direction C, D shown by the row. Let it also be supposed that the whole arrangement is balanced for the speed at which it is traveling, i.e., the positions off centers off pressure and gravity coincide. At any moment it is possible that the speed off thewin may suddenly increase, and at hat instant the machine, which will still be traveling at has same speed relatively to the earth, will meet the errata greater velocity. Lifting effect is increased and the nose off the machine will rise in the air. Thingle at which the surface meets the air is no greater and the center off pressure will move back to some point. See as shown in Fig. 31. From this diagram it will be seen that the force due to the weight of string topple the nose down and the upward pressure is string to push the tail up. The result is that thingle off incidence will beltered until it takes the original value as indicated in Fig. 30, where the positions off the centers of pressure and gravity coincide. The opposite effect is shown in Fig. 32, if a wind were 39. Fig. 33, blowing when the machine was traveling in a balanced state and then suddenly dropped, the speed of the machine relatively to the air would not be sufficient for support. The frontage would drop, the machine tending to div towards the necessary speed. Thingle off incidence is diminished and the center off pressure moves forward. There is then the upward pressure acting at some point, seat tending to push the nose up, while the weight is tending to pull tail down. The net result is that the machine, having got up speed, resumes the position of equilibrium shown in Fig. 30. It is evident that, in a wind which is constantly changing and gusty, some auxiliary device is necessary to damp any oscillations that may take place in the line off light due to the change in the position off the center off pressure. This is to a large extent affected by making their edge off the plane flexible, but hand operation off the steering devices and RNST also used to trim the machine occasionally. This is based upon the assumption that the center off pressure will always move towards the front edges thingle off incidence decreases. This, however, isn't the case with every type of plane. It has been found experimentally that, off the planes with cross-sections as shown in Fig. 33, this engine position off the center off pressure only occurs with those off sections similar to A, B, and D. If the planes are off the cross-section C, or E, the center off pressure moves forward until a certain critical angle off incidence is reached, and after this it moves backward. iPhone wish to make the plane stable without any auxiliary device, its cross-section must be shaped similar to A, B, or D. The lateral balance off the machine in the direction offline off flight can be made to certain extent automatic by inclining thetwo sides off the planetadahedral angles in Fig. 34. A. Fig. 34. Or by turning up the tips off viewing SAS at B or C. The addition off a keel also improves this stability. The proper shaping off cross-section off the plane so as to make them of streamline form greatly increases the efficiency, and every part should be torpedo-shaped, which allows the air to flow round the body with a minimum disturbance. It is also necessary to have the surface of all exposed parts as taut as possible. Wherever there is a looseness, the covering will bag and little pockets will be formed, all tending to increase their assistance off the machine. 40. Brief history of the aeroplane movement. Early history. To Leonardo da Vinci, the versatile Italian genius, famed equally for his work in painting, sculpture, music, architecture, mathematics, and physical science, belongs the honor of having first set on paper some rational notions of human flight. Several remarkable principles are found in Da Vinci's manuscript. He shows very clearly that he understood their relation between the center of pressure and the center of gravity. Or he states that a bird which finds itself in equilibrium with the center of resistance of thewings more forward than the center of gravity will descend with head inclined downwards. This she wrote after Anodian, the kite and other birds which beat their wings little, go seeking the course off thewend. And when the wind prevails on high, then will they be seen at a great height, and if it prevails low they will hold themselves low. When thewin does not prevail at all, then the kite beats its wings several times in its flight in such a way that it raises itself high and acquires a star, sending afterwards a little and progressing without beating its wings, repeating the same performance time after time. Even clearer exposition of the principles of flight is shown by his note that the bird that wishes to rise will raise its shoulders so that the air may press between its sides and tip off thewings, so that the air will be condensed and will give the bird the movement towards the descent, and will produce a momentum in the which will push the bird upward. Further, this remarkable genius of 15th century states that one, without the help of the wind, the bird remains in the without flipping its wings. This shows that the center of its resistance coincides with its mass center. In referring to his classical illustration of him in a flapping wing machine, he foresaw that the chief difficulty in gliding or soaring is to keep the center of gravity at all times in the right place. In one of his notes, he wrote that the man in the flying machine should be free from the waist upwards in order that he might keep himself in equilibrium as in a boat. Saw that the center of his gravity and that of the apparatus makes it itself in equilibrium and change, when needful, as the center of resistance changes. Leonardo da Vinci, born in 1452, died in 1519, and there can be no doubt that the extraordinary man was the first to cognize, as you are certainly the first to enunciate, the elementary principles of flight, and he should be given foremost rank in the annals of aeronautics. The lie picture of him which, 41, exists is a peculiar proof of his versatility, the picture having been drawn by himself in red chalk. It now hangs in the Royal Library at Turin. The Italian master's work is generally prefaced by reference to the legends of Daedalus, Icarus, and others, which merely show how the problem of human flight captivated the imagina tion often from the earliest times of which records exist. In every country also, the folklore is rich in tales of fleeing men, Butin on more than in Scandinavian countries. These tales Itishard Toxiptas well founded. There may perhaps be truth in the legend of Simon the magician, who during the reign of the Emperor Nero tempted Fig. 35, a page o Farley history. 42, towards towards heaven. The legend recounts that Simon rose in the air through the assistance of Beelzebub, but that St. Peter offered up a prayer. The power of the demon was crushed and the magician fell to earth and was killed by the fall. It is possible that Theman used a large plane surface and that discovered, by accident or otherwise, that it could in that manner be lifted from the earth if it made use for rising current off air. In the southern countries, the vertical air currents are ever much more frequent than they are in this country, for which reason the soaring birds are in those regions far more common. An English Benedictine monk, Elmerus or Oliver of Malmesbury, appears to have used wings, whether flapping or fixed the tradition does not state, and to have sprung from Thetop off a tower against Thewin. He is said to have actually glided for some distance and then to have experienced a sudden fall, which broke his legs, preventing further experiments. That was in 12th century, and the flight may just as well have taken place as that, off Saracen hot awards themed off 12th century glided from the top of Tower in Constantinople. The account given in the history of Constantinople by Cousin very clearly describes the apparatus used. The man was clothed in a white robe, the folds off which were stiffened by willow wands, toes of a sails forthhewn. Evidently he was making use of rigid surfaces in place of flapping wings which earlier legends record. In the presence of Emperor the Saracen waited until he caught a favorable wind, and then rose in the air like a bird. But like most of the early investigators of flight, Heffelin broke his bones, the accident causing considerable merriment, so the historian relates. Towards the end of the 14th century, Dante, the Italian mathematician, is recorded to have flown with artificial wings over Lake Trasimene. Later, Hetrid to improve up in this experiment by jumping from the top of the highest tower in High's native city of Perugia, sailed over the crowd in the public square beneath, and was supported for a long time stationary in the air, but their on forging which controlled his liftwing is it have broken and to have been the cause of his unchecked drop upon the roof of a neighboring church. Having broken one leg in the experiment, he bent in high sports to solve the problem of fleeing. There is, until the beginning of the 19th century, no further interesting history or late. The numerous attempts at flight that were made in France, especially at the courts of Louis Roman XIV and Louis Roman XV, showing no proof of any great genius. Old investigators of whom those that did not kill themselves were at least seriously injured, being men of ambition who sought the favor of French kings. Most of them used forewings, some operated respectively by the hands and feet, as that of Besnier. 43. Omen 2 in England, from Calido Maxim and Pilcher. At the commencement of the 19th century, there arose another great student of flight, Sir George Cayley, whose writings might be read with benefit by many at the present day, for he certainly had very clear notions of what was required and how it had to be done. Sir George Cayley was the first to point out that planes at a dihedral angle form a basis of stability. For if the machine heel over, the side which is required to rise gains resistance by its new position, and that which is required to sink loses it, the operation very much resembling what takes place in an ordinary boat. In dealing with the principally of stability in the direction off the path of the machine, he pointed out that experiments showed that in very acute angles with the current the center of resistance in a plane does not coincide with the center of its surface, but is considerably in front of it. As the obliquity of the current decreases, these centers approach and coincide, When the current becometh perpendicular to the sail, hence any heel off the machine backward or forward, removes the center off support behind or before the point of suspension, and operates to restore the original position by a power equal to the whole weight off the machine acting upon a lever equal in length to the distance the center has moved. To render the machine perfectly steady and tonable, it ascend and descend, in its path it becometh necessary. Hugh wrote, towed arator in a similar position to the tail in birds. 1809 high made a machine with a surface of 300 sq. ft, which was accidentally broken before there was an opportunity of distinct defect of its propelling apparatus. Its steerage and steadiness were perfectly proved, so he relates, and when any person ran forward with it at full speed, taking advantage of a gentle breeze in front, it would frequently lift the mupand, convey him several yards. Or his motive power he endeavored to obtain a steam engine working at a much higher prise, sure than the couple of pounds per square inch which was usual in those days. And he also invented a gunpowder engine. It's probable that it was simply owing to the fact that there was at that time no light prime mover that high experiments didn't lead him further. Fully recognized the importance of eliminating every possible rib or strut that could offer any resistance to the air, the poles that were used in his wings being covered with thick cloth that formed the plane. He was also aware that the shape of the part of anybody offering resistance to motion through there was of as much importance as that of different portion. It is said that some 10 years later he succeeded with mechanical power in raising a man from the ground with his apparatus, but the chasnet being properly authenticated. From that time most of the serious work connected with human flight in heavier-than-air machines was carried out in England until Lilienthal made his famous experiments in Germany. 44. About 30 years after Sir George Cayley first made public his researches into the problem of flight, there came Henson, who patented a large aeroplane of canvas, stretched upon a rigidly trussed frame and propelled by screws operated from a steam engine. In his patent specification, he gave the surface off planes as measuring 500 sq. ft, that off tail being 500 sq. ft, extra and with a total weight of 30001 b. I intended Towseen engine of 25 hp. His drawings show the main surface tow been about 150 ft, and spread by about 32 ft, in Fig. 36. Henson's projected aeroplane of 1,814 length, but Henson never completed such a machine. With his friend Stringfellow, he completed in 1,845 a model of 70 sq. ft, weighing just under 301 b. It is evident from the counts of these experiments that the machine lacked stability and was never able to make any flight. Stringfellow later, on his own account, made a much more stable model, which he found was able to sustain itself in an enclosed space, but not out off-doors. Most important contribution to aeronautical knowledge before the modern array of flight commenced was asserted by Mr. Fig. 37, Phillips' whirling machine for distinct lifting power off planes. 45. When in 1866, U.S. first to point out that the supporting surface of an aeroplane could be best utilized by these post-engine in such a manner that I'd offered a broad spread with little fore and aft depth, instead of arranging it with considerable depth. He entirely repudiated the limitations of natural wings, but considered that a successful flying apparatus could be constructed. Actually made a large model of a kite or glitter sufficient to carry the weight of Farman, the supporting surface being a Dinsix narrow plane seft, the fashion of a Venetian blind. His diagram shows the intended per tordo liprone, just as Wright brothers did in theory experiments. He found that when Thewand approached 15 or 20 miles per hour, the lifting power off this apparatus was all that was required. But the capricious nature off the ground currents was a perpetual source of trouble. When Ham is also notable for having forstuced the hyperbolofa manskating over thinness, Thesa not being deflected in any way so long as rapid motion is maintained. Same illustration was later used at B. Langley. Wenham, like most other capable students of flight, based all his theories upon thesaurine power soft birds, and his great theory was published in this form. Having remarked how T hinostratum off air is displaced between the wings of a bird in rapid flight, it follows that, in order to obtain the Nice's Lilienthal plane for supporting heavy weights, the surfaces may be superposed or placed in parallel rows with an interval between them. Dozen pelicans may fly on above the other without mutual impediment, as if framed together, and it is thus shown how 2 CWT may be supported in a transverse distance of only 10 ft. Phillips, who in 1884 patented the dipping edge section of planes, expended a considerable amount of time and money with a peculiar form of flying machine previous to 1893. The apparatus had the appearance of a huge Venetian blind with the slats open, the total number of slats or sustainers being 50. Fig. 38. Phillips's steam-driven multiple-plane captive flying machine. 46. Fig. 39. Maxim's aeroplane of 1893, each L in. wide end 22 ft, long fitted 2 in. Apart, the total supporting area use obtained was 136 ft. The frame holding these slats was fitted on a light carriage mounted on 3 wheels, each 1 ft. In diameter, 1 in front and 12 rear. A small boiler and compound engine. Atwo-bladed screw turning at 400 revolutions per minute, waste employed for the motive power. The machine followed a circular path off wood of 200 ft. diameter, and wires were carried from different parts off the Aerosto Central Pole in order to prevent erratic flights. This notion Forestinga machine originated with Tatton in 1879. The forward wheel was a balance that it would never leave Thetrek and served, therefore, a sagite, carrying less than 201 b. Off the weight, the remainder being on the hind wheels, with 721 b. Dead weight added, the hind wheels off the machine rose a couple off clear off the track when the apparatus was set in motion. Else, therefore, the ability off the machine to raise itself from the ground was amply demonstrated. Then it results off the experiments were off little value, for no provision was made for maintaining equilibrium on such a machine in free flight. About this time, Sir Hiram Maxim was carrying out high experiments on a full-sized machine. The total lifting surface of his apparatus was 6,000 sq. ft. And the total weight with 6,001 b. Of water in the tank and boiler, and with naphtha and 3 men on board was no less than 8,001 b. 2 compound engines were specially designed for the work. One of these is Tobesine at the present day in South Kensington Museum, weighing only 3,101 b. They each developed ISO P using steam at 3,201 b, to the square inch. A lifting effect of 3,001 b to 4,001 b. Was obtained at a speed of about 40 miles an hour. The apparatus was natallowed to rise from the ground, but ran over a track. U-heels on which the machine was car redrun over steel rails of 9 ft. Gauge and the safety track of 3 in by 9 in. Georgia pine placed about 2 ft. Above the steel rails was 30 ft. Gauge. Maxim calculated that the lifting effect upon the machine on the occasion when it got off the rails and was badly smashed could not have been less than 10,001 b. Maxim's experiments with the large machine extended from 1890 to 1893 and were abandoned only owing to their costly nature. The main aeroplane was 50 ft. Wide end 47 ft. Long in the direction in which the machine traveled. Fiva long end 47. Aeroplanes projected from each side. Those that were attached to the sides off the main airplane were 27 ft. Long, the total width off the machine thus being 104 ft. The machine was also provided with a forward and an after rudder made on the same general plan as the main airplane. Lawrence Hargraves, the inventor of the well-known Chelu Larabox kite, was for some years engaged upon the subject of mechanical flight. In 1892 he constructed a very successful model. He employed at first compressed air, but later adopted steam. The general idea of the model was that fixed wings were carried at a very obtuse angle on the main keel, while in front were 2 flapping wings which afforded the propelling power. The wings were driven by a little engine. One of the models, when compressed air was used, flew 343 ft. in 23 seconds. These experiments were apparently discontinued. A clever young engineer, Pilcher by name, commenced in 1895 tow work on Lilienthal PS system. His first glider, with which he made many flights between 50 ft. and 350 ft. in length, weighed 501 b, and gave a sustaining surface of 150 sq. ft. A larger machine, double-decked, which he constructed in the following year, he found difficult to control. A third and somewhat lighter machine in 1896 made many good flights. It was equipped with wheels for grounding. In gentle winds, his method was to rise in the air like kakite, the glider for this purpose being towed by a horse. The tow rope passing over a pulley block which made the glider travel 5 times as fast as the horse. At a desired altitude, Pilcher cast off and glide toward. Had assigned in 1899 an airplanetoba driven by a 4 P. Petrol motor off his own design, Butarabafone off the wings of his glider broke during Gatriel in the same year, and falling from a height of 30 ft. He broke his collarbone and succumbed within 24 hours. Fig. 40. Pilcher making a gliding flight in 1895. 48. In Germany, Lilienthal, the founder of the modern school. Otto Lilienthal has undoubtedly inspired all the modern efforts which have finally led up to the conquest of air. As a boy of 15, this distinguished engineer, who for so many years spent the spare time in the study of aviation, showed a gnarly desire to investigate the mysterious of bird flight. His name appears first in Aeronautical Annals in 1889. He published his famous book, Bird Flight as a Basis of Flying Art. In this treatise, he gave the world the practical result of 25 years' research and study. Much of his early attention was devoted to the flight of seabirds. Otto Lilienthal in the course of his work having been occupied on sea work. Hewis the inventor off a foghorn adopted for German lighthouses. Later he spent a great deal off time in following the movements of storks, which Aerotobe found in great numbers in the south of Germany, where their soaring feats are regarded as scam mon place. And much of this work Otto Lilienthal was headed by his brother Gustav, but the brother's help was probably seldom sought, for the 1889 book Borithene Monly off Otto Lilienthal. When he satisfied himself that curved surfaces, such as birds apparently use would be essential to human flight, he was still uncertain about the ability of Mentalif himself by flapping wings. This problem he solved in an interesting manner. He suspended himself by a rope counterpoised over a pulley supported from a beam projecting from a house. He equipped himself with 3 pairs of wings operated by his own muscular efforts, using both hands and feet, with thewings opening and closing like Venetian blinds. The total weight of thewings and of Lilienthal himself amounted to 1,761 b. And after a few experiments, he employed a counterweight of 881 b. And with considerable effort lifted himself in this wise 30 ft from the ground. This satisfied him that flapping flight was Fig. 41. Lilienthal gliding in 1891 with his first model. 49d. Fig. 42. Lilienthal starting tower. Out of Textchen, Buthuas encouraged to proceed further, and for the investigation of the supporting power of curved surfaces, he made almost countless experiments with a whirling table, the invention of which, though often attributed to him, seems rightly due to Professor Mary, who employed such a device about the year 1870. Lilienthal enumerated in his book a number of conclusions which he drew from his 25 years' experience. Most important of these were that, 1. The construction of machines for practical operation is independent of the development of a light and powerful motor. 2. Hovering flight is impossible by means unaided strength, but can be attained by means of proper surfaces in winds of 22 miles per hour or more. 3. The application of an additional bearing surface, for example, aerial ice of minor importance. 4. Wings must be curved in transverse section and concave on the underside. 5. The dipthoflexure should bell 12th width. 6. A sharp cutting edge should be used at front edge off the supporting surface if possible. 7. Flexure should be parabolic with the greater curvature in front and the flatter surface to the rear. Fig. 43. Trajectories of 3 of Lilienthal's flights. 50. 1890 Lilienthal commenced a series of experiments that must and will forever regarded as classical. In the following year he made his first trials with gliders, and in 1893 with a glider weighing 441 b and measuring 150 sq. ft. He went cautious little work to lift this own weight freely in the air. He see asterisk. Fig. 44. Trajectories off wo Lilienthal flights from his later artificial hill with shed at summit. Started in his garden by jumping from a springboard 3 ft high, and gradually increasing the height off the board to 8 ft, and taking bounds from it, he satisfied himself they could commence a flit o'er. He then built a load or own a hill, and from the top of this made many successful glides. Later Hewis led to construct an artificial hill 50 ft in height near Groß Lichterfelde, near Berlin. In 1895 had opted 2 superimposed planes, each 18 ft broad and of 100 sq. ft area, the upper surface being about 3/4 soft breadth of the lower. He wanted to fly in a wind of 10 meters per second. Previously he flew nearly horizontally in winds measuring from 6-7 meters per second. In a strong wind he Fig. 45. Lilienthal S glider of 1893 made twofold for portability. Fig. 46. Lilienthal's double-deck glider of 1895 frequently allowed himself to be lifted from the top off the hill without the necessity for running down the slope, and oftentimes he found himself higher than the top off the hill. To take longer glides, he went in 1896 to the Rhine Hills, where he had been in 1893 for a fair time. From the top off some hills there 250 ft. He glided sometimes 750 ft or more. Unfortunately, in the search for that soaring flight which seemed to fascinate him, he was caught in an awkward current, and the machine, losing its equilibrium, carried him plumb to the ground, breaking his collarbone, from which injury it within 24 hours. With him, study of flight had always been hobby. Gliding with him tilde became a CX sport. How much further Hew'd have pro had Fig. 47. The model arrived at B. Lilienthal just before his death. Had been spared from that accident on August 12, 1896. It is impossible to say, but from his work has proceeded out great and important success, which has within the last few years been attained in thought and science of human flight. From his pupils Herring, Pilcher, and Ferber have grown the schools of America, England, and France, respectively. 4. In America, Langley and Chanute. The history of the American aeroplane resolves itself in popular mind to the doings of Thetwo writes. However, it must be borne in mind that, thought he's 2 clever inventors accomplished the feat of flying before anyone else, they had a vast amount of work already done for them. Langley, with whom was associated Dr. Graham Bell Chanute and Herring, were first in the field. Langley and Bell, Howard working on their own lines, had been cooperating for 2 years before Chanute came on scene. For Langley started in 1893. Chanute began with the assistance of Herring, who had been a pupil of Lilienthal, and while in no wise discounting the Americans' achievements, Wessey and Lilienthal the groundwork of Chanute's success. But Langley and his advisor Bell, Chanute and Heiss engineer Herring were all handicapped by Thiepsen's off-light motive power such as that of Petrol engine. They all stopped because the progress was impossible until the day of the light-efficient engines. Langley is recognized as being one of first to make an aeroplane that would actually fly. In making his report on the subject, Langley modestly stated that, "To prevent misapprehension, let me state at the outset that I'd not undertake to explain any art of mechanic half-light, but I'd demonstrate experimental ascertained propositions in aerodynamics, which prove that such flight under proper directions is possible." Langley recognized that to imitate thiction of a bird was useless. In Heiss endeavor to master the problem of flight, he employed an aeroplane, or as she called it, aerodrome, to assist him in his pioneer work used through hurling table. With this US able to prove that the figures prepared Fig. 48. Langley's mode devised in 1893 and first flown in 1896. 53. By all known French mathematician Wheron, likewise Newton's rule for finding their assistance towed vents through air. Otherwise, Ashe pointed asterisk out, the swallow would have to beni arly astrongas and intonable it travel at 60 miles per hour. Since Heffer's propounded his famous theory, well known as Langley's law, he has qualified their marks to the extent that, though it still reads as it did at first, of the effect that less power spent in making a plane's surface travel fast through their than would be spent in making it travel slowly, that statement applied on the toth ideal condition of a frictionless plane and an actual flying machine. Fig. 49. The Langley model in actual flight, May 6, 1896. Undoubtedly, Langley would have furthered that art of fleeing if it could have had the assistance off the petrol motor. He experimented with compressed air, carbonic acid gas, electricity and other means of obtaining power. Finally, he settled upon steam, though he stated that he thought the gas engine would be the motive power of the future, using steam huastrably handicapped, fourth engine, generator, etc. Weighed 7.1 per HP, and his water supply wouldn't last long enough for a flight off 1 minute. The innumerable difficulties that they had to overcome can be gauged from the fact that it was not until May 1, 1896, that his machine actually flew, although it was 3 years previously that he first started his experimental work. As the illustration shows, Langley's aerodrome was shaped like a butterfly and consists of a main girder ling in direction of flight, to which the foreplane surfaces are attached fore and aft, the power unit and propellers being placed immediately behind the front pair of wings. Langley claimed that with this model he had proved flight possible. Herring and Chanute were very closely in aeroplane work, though together they never got beyond the experimental. 54. Fig. 50. Chanute's experimental multiplane glider. Stage end gliders. Herring was a pupil of Lilienthal, but soon broke away from the lines of the German engineer. He brought Chanute's notice the German inventor's discoveries, and appears to have really started the latter's interest in gliding experiments as a means towards the conquest of the air. Saw that in 1895 he and Chanute constructed a glider like Lilienthal's, though slightly modified. This glider was shaped like the outstretched wings of a bird, the top surface being concave and Fig. 51. Chanute's final form without vertical planes. 55. Under convex. With this machine, which had a sustaining surface of 168 sq. ft. and weighed 361 h, he made a number of experiments. His longest glide was 168 ft. Chanute found that this type of glider was quite safe and longently, but it would not travel any real distance unless the experimental hill wasty pass will last long. In other words, it dropped too much in gliding. His next machine had 8 separate planes, placed in pairs above one another. That point to notice with this glider, which had the position of the planes definitely altered 7 times, irrespective of adjustment, is thighs, it had the planes curved from the front view though flat from the side aspect. This glider gave longer flights. Chanute then abandoned this glider and constructed aeroplane with planes flat. Fig. 52. Chanute's penultimate form of double-deck gliding machine, the side planes were finally abandoned. From the front aspect, viewed arc from the side, this was a most important step. The result was that he immediately doubled the length of his flights. The biplane had a certain amount of unsteadiness that they hadn't previously experienced, and which he does not account for. However, he overcame that by attaching a vertical rudder to his glider some distance at her end on the same level as Thelode. Chanute was of the opinion that not much was to learn from studying thiction of fleeing creatures, because they be on the mount off their supporting surface. He thinks that his most valuable discovery was when he found that a plane presenting a flat appearance from the front and arced from the side had the greatest lifting capacity. 56. Omen 4. In France, from Ader to Wright. Although theorenautical research work undertaken in France seems to have been very migrant the last half of 19th century, thework of Tatin and Penaud with models in the 70s and 80s wasn't insignificant. It is necessary to go further back than that first flight off Santos Dumont, made at Bagatelle on the afternoon of October 23, 1906, and popularly regarded as the starting point of Aeroplane in France, told at that beginning of this revolutionizing movement. Before that first soar could be made, years of patient experimenting had been carried out, and Santos Dumont should be more correctly regarded as Thehapian Stru meant than the originator of first real flight made in France. The rapid rate of progress since that October afternoon, and the immense enthusiasm in France proved that there was a wealth of activity unknown to the ordinary observer, ignoring the small army of inventors, who dreamed of these covering the secret of the birds and work towards Thetanto received no other reward than the title of fools. The first person in France directly connected with the present movement is Ader, who, in 1892, started practical experiments with flying machines, and in 1897 made the first known flight in Europe. Ader had succeeded in interesting the government. Fig. 53. The Ader, the first power-propelled aeroplane. 57. Fig. 54. Experiments at issue with Aglater in 1900, power being obtained by towing the glider with a car. And after every short flight on October 12, 1897, on Saturday ground, in the presence of General Messnier, a demonstration was ordered to be made the following day before a military commission. October 14th, which was later fixed as the date of trial, was Augusti autumnal day most unfavorable for aeronautical experiments, and although Ader was able to rise from the ground, his machine was incapable of struggling against the strong wind, and made such a poor display that the government lost interest in the matter. Ader was abandoned, and discouraged after 40 years' labor and the expenditure of 2 million francs, he commenced the destruction of his machines. One of them, however, was saved, and no figurescent arts at Médier's Museum, at Paris, by the side of the biplane with which Wright first flew in France. M. Tatin, one of the most distinguished of French explorers in their realms of aeronautics, built Amadel flying machine in 1896 for M. Richet. The machine flew, but during one of the experiments Nerthisia traveled for a distance of 150 yards, capsized and disappeared in water. As the little experiment had cost nearly £1,000 sterling, the supporter lost all interest in flying with the disappearance of the machine. It was in 1899 that Captain Ferber began a long series of experiments with gliders, endeavoring to take up the work that had been carried on with so much success by the German Lilienthal, but was unable to make the least gliding flight until 1901. Like Lilienthal, he'd etched himself to the apparatus by the shoulders and arms, steering bikering his legs ahead, to there are Ordolf Tandreit, but was notable to glide on the layers of Rashid bin Don by his German master. In 1901, hesitantly perceived that flights of this nature could only be made with an ascending wind. It was not sufficient to run down a gentle slope, for the speed of 3 ft to 6 ft. A second these obtained would beltoge their insufficient to support Amanonsachan unbuoyant element as air. A horizontal headwind was altoge there, unfavorable, for if it caught thewings on the upper surface, the effect would be to hold the apparatus down to earth. On the other hand, if the apparatus were at such an angle that the wind struck the under surface, the apparatus would be raised, but would not be able to advance in the face off the wind, and after a flutter in the air, would be driven backwards towards the ground. With the wind blowing up the slope, it was possible for the aviator torn down, with the front of his apparatus inclined towards the ground, and what would appear to have been the face off the wind. The upward current of air, however, would have a lifting effect which would allow the experimenter to glide ahead, gradually descending all the time. Captain Ferber in France kept in touch with the work being done in America by Chanute, Herring, and Avery, as well as with the earlier experiments of the Wright brothers with their assault Fig. 55. Experiments in Glittingen 1900-1902 by M. Ernest Archdeacon and Gabriel Voisin. That progress was being made simultaneously one each side of the Atlantic. Ferber No. 5. Off the Chanute and Wright type, after a unsuccessful initial attempts, made satisfactory gliding flights at Buell in 1902. The experiments were continued the following year at Conque in Finisterre, with equal success. The apparatus, which had then every strong resemblance to the ine being used on the other side. Off the Atlantic by Wilbur and Orville Wright, making numerous gliding flights with perfect stability, was considered so satisfactory that the problem of driving it mechanically was taken into consideration. Captain Ferber estimated that the engine he could put on the machine was 2,201 B. In 1903, all the power he could obtain for this weight was 6 HP, delivered by a budget petrol motor. Aeroplane known as No. 6 was built on same lines as the preceding one, fitted with the budget engine, 59. Big 56, the Voisin float-borne glider, driving two large propellers in opposite directions by means of a kind off differential, and arrangements made for a tobe tested in 1903 on an aerodrome at Nice. Hengthis Froman arm 100 ft, in-length pivoted onator 60 ft. High and drove the machine round, but the power avail able was not sufficient to sustain the machine in the centrifugal force prevented a high initial speed, and further. Propellers were much too large for the engine. Afterwards experiments were made with the aeroplane hung on a cable and running upon it, tobe released and shot in the air, but the aeroplane merely glided, the motor failing to keep it aloft. A larger motor was ordered, but before further work could be attempted the government required theft in which the aeroplane was housed, and the experiments came to an end. Captain Ferber went on half-pay immediately after this, and was notable to build his apparatus until the spring of 1908. In July of that year, it wasted at Issy-les-Moulineaux, flying the full length off the ground after a few slight adjustments. This result, which might have been obtained in 1905 but for the lack of War Office sympathy, passed unnoticed, for in the meantime Farman, de Lagrange, Blériot, and Santos Dumont had all made flights. While Captain Ferber was carrying out most important experimental work in France, Ernest Archdeacon was no less active in the capacity of aeronautical evangelist, seeking to arouse enthusiasm in the subject of flight by lectures in various parts of the country, and by financial and moral encouragement to experimenters in this field. Mr. Chanute, having visited France in 1903, and given particulars of the wonderful success achieved by the Wright brothers with gliders during the years 1900, 1901, and 1902, Archdeacon had a machine of a similar type constructed at Chalais-Meudon. The possession of machine, however, was not sufficient, and in view of the lack 60 of experience in its handling, as well as the different conditions under which it had to operate there, nothing practical was done in this line. Gabriel Voisin was introduced to Archdeacon in January 1904, and less than 3 months later the two were making gliding nights towards the Rat-Berg-sur-Mer. Gabriel Voisin, who mounted the apparatus, was at first unable to make a flight. It was only after Captain Ferber had been brought from Nice to explain that the must operate in an ascending wind that practical results were obtained. Berg-sur-Mer was not an ideal spot for gliding experiments, and in order to near their workshops, the party returned to Paris, where, for want of a hill in which to make glides, the aeroplane was stowed by a motor car across the military ground at Issy-les-Moulineaux. The method of operation was to place the aeroplane without motor, but with a pilot on board on suitable rails, attach it by means of a tow rope to the motor car, and pull it until it rose in the same way as a kite. Was not a very satisfactory arrangement, and after an accident on March 25, 1905, when the machine flopped to the ground and was completely destroyed, these experiments were abandoned. Fortunately, on this day the pilot had been replaced by a sack of sand. Believing there was less danger in theater, the aviators abandoned Issy and took up their headquarters at Hesse Surcouf establishment at Billancourt, on the River Seine. Most remarkable performance was made on June 8, 1905, when the aeroplane, mounted onto long floats, piloted by Gabriel Voisin and towed by the motorboat Rapier, rose to height of 55 ft, and covered a distance in the air of not less than 160 yards. The apparatus had then very closely approached the form tobe adopted later by the aeroplane with which Farman was so fig. 57. Gabriel Voisin in his glider towed over the Seine by a fast motorboat. 61. Successful, it had two main superimposed planes about 60 in, apart, united by four vertical planes to give a lateral stability. In their arwasadale composed in the same manner, but of much smaller dimensions than the main bearing surfaces. In the front was a single horizontal plane forming the functions of elevation rudder. It was not long before experiments on water were proved to be even more dangerous than those on land. 6 weeks after the experiment just mentioned, Voisin again tested the Arch Fig. 58. Blériot 9 bis running over the ground in 1906. Deacon aeroplane on Seine with but moderate results, and a few hours later took out Tainou apparatus which had built for Louis Blériot. While being towed by the motor Bipat, Antoinette, the aeroplane suddenly dived under the water, taking Voisin with it. The aviator only succeeded in extracting himself from under the planes at Hindorf 20 seconds, which appeared to 20 minutes to the anxious spectators. A little later, Archdeacon removed to the Lake of Geneva, hoping there towed a powerful motorboat which would tow him constantly head on to the end, a thing which was practically imposed Sibley on Sechenero River as the Seine. A suitable boat could not be found, and the only practical result of the visit was a little experiment made by Gabriel Voisin when the aeroplane was lingat anchor on the lake. Very strong wind Voisin discovered that they could cause the aeroplane to rise from the surface of the water merely by operating the elevation rudder, and remain in the air, struggling gatitskable until a lull wind orthomanipulation off the rudder caused Aerodsen. The year 1906 opened with tremendous activity among French 62, Vig 59, so, Entostum, on S famous aeroplane 14 bis coming up for the /start off its first flight. The elevation planes are carried at forward end of the body. Aeronauts and a firm belief on the part of enthusiastic inventors that the day was verinar when aimed mechanically driven machine would rise from the ground and maintain itself in the air, a feat which had never been accomplished in Europe, the exception of the brief and almost forgotten soar of a Dur in 1897. The Wright brothers claimed to have made flights the previous year varying from 25 to 38 minutes duration, and although their statements were far from being generally accepted in France, the merepsibility of the Americans, having made a flight incited every own to increased efforts on thy side, off the Atlantic. Gabriel Voisin had joined Louis Blériot in business as aeroplane constructors, and together, the Aeroplanes NOS. 3 and 4 were built and experimented with on the lake at Enghien, near Paris, and at Issy-les-Moulineaux. Antos Dumont's first idea avastable helicopter. Several technical advisors persuaded him that this would be waste of time and energy, and in consequence, an airplane off Hargreave boxsky type was constructed and shown to the members of the Aero Club in July 1906. The first Santos Dumont aeroplane, known as 14 bis, was attached to No. 14 dirigible balloon. A young Brazilian sportsman had not having sufficient confidence in heavier-than-air type offling machine towed him to flight from the ground in the generally accepted manner. It was immediate license that the dirigible balloon was more of a hindrance than a help, and other aids were looked for. After various experiments with an inclined cable, and later with an inclined wooden track, the machine was sent away over the Bagatelle ground on its 4 wheels, and under Thiefert off its 24 h.p. Antoinette motor, 63, Vig 60, the starting point off the aeroplane movement in France. The flight of Santos Dumont's 14 bis at Bagatelle October 23, 1906. There was an immediate improvement, and it was not many days before the apparatus was running about in all directions. The motor was changed for a larger one developing 50 h.p. While longitudinal stability having proved to perfect, the 2 rear wheels were abandoned, leaving the front only. July to October had been spent in experiments, but so rapid was progress that, on the 23rd of that month, Santos Dumont called together the Aviation Commission of Aero Club of France, and at 4:45 in the afternoon won the Archdeacon Prize for the first flight off net less than 25 meters. Excitement was at such a high pitch when this huge motor-driven boxkite rose from the ground, that the Commission forgot to measure the distance covered in the air. Although officially given as 25 meters, it was generally recognized that the actual distance was not less than 70 yards. First flight ended with the breaking off the wheels off the aeroplane. For the apparatus having set to pass low lateral roll while in the air, Santos Dumont switched off the ignition and allowed his machine toadsend abruptly, instead of guiding it down gently. A month later, the flying record had been carried to 220 meters, and enthusiasm in French aero circles had reached its height. Among the general public, however, the belief was prevalent that the so-called flights were on the jumps, comparable to the leaps that could be made by a man running at high speed, or even by a motor car when driven fast. Santos Dumont's first success was nutritionally followed up, and after various unsuccessful attempts with small-area high-speed flyers, the young Brazilian abandoned the aeroplane to endeavor to construct an apparatus to travel at 100 kilometers an hour on water. 64. Vig 61. Henry Farman wins the Archdeacon Deutsch Prize of 2000 by covering a triangular course off 1 kilometer on January 13, 1908. Gabriel Voisin, who during 1906 had solved his partnership with Blériot and been joined by his brother Charles, had developed his own type of airplane while working out the ideas of his customers. Had discovered, however, that inventors who were willing to pay for airplanes wished to have them according to their own ideas. It was not until the Parisian sculptor Léon de Lagrange came forward in the early part of 1907 that they could find anybody to accept the machine produced as the result of the gliding flights at Berck-sur-Mer and the experiments on the Seine and Ilseur. The first Voisin machine, known as the de Lagrange No. 1, was tested at Vincennes on February 28, 1907, Charles Voisin mounting it. It was so lightly constructed that the backbone of the machine broke. Fortnight later it was out again at Bagatelle but failed for lack of lateral balance. Finally, on March 30th, still on Bagatelle ground, the machine went in the air for a magnificent flight off 60 yards. Instead of continuing his training after this satisfactory debut, Léon de Lagrange abandoned the Voisin machine to carry out experiments with M. Archdeacon on the Lake of Enghien. In June, Henry Farman came forward with a request for a machine, and Henry Farman No. 1, differing from the de Lagrange No. 1 in the method of attachment off, wheels only was sharply to him, with true Anglo-Saxon thoroughness, for Henry Farman is of British parentage. The new recruit set to work for a thorough training. Ashid was built on Thege off, issy less mooley no ground, the first of its kind, and for a whole month Farman scurried over the ground, thoroughly familiarizing himself with the handling of the machine. The first flight was made on September 30th, when a distance off about 90 yards was covered in a straight line. For almost a month very little progress was made, the aeroplane never being able to remain in air for a greater distance than 100 to 150 yards. The fault was that the levitation was scurried at too great an angle from the horizontal, and as the machine rose in the air, itless speed and //L *T *RM *M *N tilde KEN *F9 FF SFF T tilde MM Fig. 62. Kapfer's aeroplane, built by Voisin Frears at issy in 1907. Fell. This was soon remedied, and on October 26 Farman made another record by a flight off 843 yards. On every possible occasion during the months of November and December Farman trained on issy les Moulino ground, making numerous modifications in the machine and familiarizing himself with the handling of it. By January he was sufficiently skilled to attempt a complete turn, and on 13th of that month called together the commission of Aero Club of France, in view of an attempt to Deutsche Archdeacon Prize of 2,000 for a circular flight of 1 kilometer. The conditions of the flight were that the machine should fly over a given line, 50 yards in length, follow an imaginary line at right angles to the starting line, rounding a flagpost 546 yards ahead, then return and recross the starting line. Obviously it was much more than a kilometer that must be covered, for the distance from the starting point to the flagpost and return alone equaled that distance. It was a perfectly calm January morning when Farman started up his Antoinette engine, and after a preliminary soar, shot over the line, rounded the flagpost, and in a min. 28 sec. Was back again at the starting point, Thuner off the Deutsche Archdeacon Prize. It was an epoch-making day, for those skeptics who had previously maintained that aeroplanes were huge jumping, 66 machines capable of making wild leaps in the air, but were altogether incapable of aerial flight, were silenced forever. That circular night of roughly a mile had proved to the world that the aeroplane was a practical machine. Soon after the winning of the Deutsche Archdeacon Prize, Leon de Lagrange returned to the Voisin and commenced training with such ardor that on March 14th he covered 328 yards. 2 days later he had covered twice that distance. Towards the end of the month he began to attempt circles, and in April LL won the Archdeacon Cup a circular flight of nearly 2 miles. The first half of the year 1908 was a period of friendly rivalry between Farman and de Lagrange, first over very short distances, then for comparatively long periods. Farman, whose long experience as a motorist stood him in good stead, and who also owed much to his regular methods of training, at first had the advantage, being able on several occasions during the month of May to make short flights with M. Archdeacon on board. While giving demonstrations in Rome, de Lagrange took the lead by making a flight lasting 25 sec, and in June 22nd at Milan remained in the air for 16 min. 30 sec. Had the SEF flights been made in France, he would have been entitled to the Armand God prize of 400 for the first machine remaining in the air not less than a quarter of an hour, which had been coveted by both aviators for several months. It remained, however, Farman to secure this prize, and at the same time to break the flying record by a flight lasting 19 min. On the evening of July 6th on issy les Moulino ground. Up to this time the only other aeronaut in France who had made flights off any important was Louis Blériot. Several types of machines had been constructed, but it was no. 5. A monoplane modeled after Professor Langley's machine, which first proved successful. After Thish had made several short flights and been the cause of a sensational fall, it was abandoned for another type of monoplane, the Blériot No. 8. Embodying Fig. 63. Blériot's double-winged aeroplane of 1907. The angle of the forward planes canbeltered. 67. E2. Ig 64. Capt. Ferber's latter experiments at issy in July 1908. Many of the ideas of M. Tatin, which proved Tobes the most successful monoplane then known in France. The morning that Farman won the Arming God Prize, Blériot made a flight off 8 min. 24 sec. His progress only being stopped by the failure of the pressure in the petrol tank. Activity, however, wasn't confined to these 3, but the score or so Howard devouring to fly hadn't it been able to realize anything more important than trips lasting a few seconds. In 1906, Vuillet had left the ground on a monoplane for a distance off of your 6 yards, lengthened a year later to flight off 60 yards. Robert Esnault Peltery flew as early as October 1907. Comte de la Volx flew 60 yards in November off the same year. De Piscoff flew a kilometer on a biplane in December 1907, and Gaston Bedmengen made his first flights with an Antoinette monoplane in February 1908. Paul Cornu's helicopter man aged Torice from the ground to height of about 16 in, on Fig. 65. Blériot no Roman II, at Issy, 68, March 16, 1908, and the Breguet gyroplane in Julioff the same year had attained a height of 14 ft. and traveled a horizontal distance off about 20 yards. The success off the leaders had already attracted a host of experimenters and imitators. With their salt that flying machines were being built and tested on all sides, not always with an degree of success. The situation in France was entirely changed by the arrival of Wilbur Wright during the month of July, 1908, with the object of fulfilling conditions imposed by a syndicate of which M. Lazare Weiler was head. The syndicate undertook to pay to Wilbur Wright the sum of 500,000 francs on condition that they made 2 flights off not less than 50 kilometers, 31 miles, each with a passenger on board, and sufficient petrol for a flight of 200 kilometers. The syndicate secured the sole Wright to construct and sell the Wright type of airplane in France and Hercules. Wilbur Wright made his first flight on the Honeydeer's race course at Le Mans on August 8, 1908. Was the first time the machine had been brought out since May of the previous year, and in view of his lack of training, the American aeronaut was content to remain in the in 45 sec. It would have been atrium forest at Rector's but for the fact that during those 105 seconds the machine rose to height of 36 ft. and described acaply of circles in manner that ways altoj thur known to Europe. The flights were continued on the following days, and gradu ally lengthened until on August 13th the machine remained in the 8 min. 13 sec. Naturally, these experiments had Fig. 66, one-off Blériot's innumerable flights, attracted enormous crowds of spectators, much to the annoyance of Wright, who had innocently imagined that, after the first 2 or 3 flights, he would be left to work alone. Air removal was therefore made to the Camp Dovers, Avis pine-bordered plain about 7 miles out off down, difficult off access and unused except for military maneuvers. Almost immediately after the arrival at Heck Camp Dovers, the flights were lengthened, Wilbur Wright remaining in the 19 min. 48 f sec. On September 5th, almost equaling the distance covered by de Lagrange and Farman in the previous month. But there were still more important flights in store, and after a soar of 2 min. 20 sec. with M. Ernest Zenz as passenger on Fig. 67. La Demoiselle Santos de Tamont's miniature flying Mo Ch. in E at St. Cyrinthium of 1908. September 16. Wilbur Wrightson in Heisentriforth Michelin Cup and the Prextella commissioned Aviation off A.C. F. The afternoon of September 21st, after 3 false starts, due to the rail being badly placed, Wilbur Wright remained in Thier for Iher. Esselman, 25 F sec, thus creating our world's record for both time and distance, and provisionally securing the Michelin Cup and commissioned Aviation's prize. Ash stepped from the machine amid the tremendous excitement of Themas off spectators gathered on the ground. Here mark. That will cheer up Orville Abbott. The conditions off that will prizes were that the flight should take place before sunset. Thus, 70. It Wasson liquidated with 19 rounds off the triangle or a total distance of 23 miles. The actual distance covered, however, was more than 55 miles, equal to 3 times the crossing off the channel from Calais to Dover. That this could have been considerably lengthened was shown by the fact that only 4 gallons of petrol out of a total of 11 had been used, and but 3 pints of water had been lost out off the radiator containing 2 gallons. On September 24th, another attempt was made for the Michelin Trophy, with their result that the official distance was carried from 38 to 39 kilometers, 243-10 miles. The total distance, however, was less than on the previous occasion, the flight having to be arrested owing to the rising wind and the invasion off the ground by overeager spectators. 4 days later, the distance for the Michelin Cup and Aviation Commission's prize was increased to 48 kilometers 120 meters, 30 miles, this latter being won outright, and on the same day Wilbur of Wright took a passenger for the second time, flying foreman, 30 sec, with M. Paul Tissandier by his side. Finally, a flight off 7 min, 45 sec, was made with Comte de Lambert. On October 3rd, after certain modifications to the asterisk machine and interesting demonstrations off-flying Salothet Thurunners touched the top off the heather and course grass off the military ground, Wilbur Wright invited Franz Reichel, their presentative of Figaro, to fly with him. Although the sun had set when the flight began, the machine didn't settle down again until 55 min, 321 sec, later thus creating a record 4 flights with a passenger on board. On October 4, this record was broken by a flight off Iher, 4 min, 26 F sec, with M. Fordyce on board, and on October 5 this record in turn was beaten by Owen of Iher, 9 min, 45 F sec, the passenger being M. Painlev. View off the remarkable results obtained by Wilbur Wright, French aeronauts had almost ceased to exist for the general public, and it needed their remarkably daring trip off Henry Farman on October 30th to prove that the American was not the Limenhock knew how to fly. Farman ho had been Fig. 68, The snow-covered plain at Issy in the winter of 1908-9, when Santos Dumont continued high experiments with La Demoiselle. 71. Vig 69. The REP Aeroplane 2 bis. Mr. Esnault Peltier is an advocate off the monoplane. J training for some time in the plane near Chalons, started a little before 4 o'clock on a cross-country flight, his destination being Reims, about 17 miles away. The machine, which had won Deutscharchdeacon Prize in January, was immediately carried up to height of over 130 ft. Norder Tobe absolute certain off-clearing tall poplar trees, telegraph wires, and other obstacles. In a few minutes the aeroplane was lost to sight, and was not long clear away from the motor cars which attempted to follow it. Exactly 20 minutes from the time he started, Henry Farman descended on the military ground just outside the city of Reims, having made the first cross-country flight at a speed of 45 miles an hour, and at an average height of 130 ft. It had been intended to return in the same manner, but, owing to certain adjustments being necessary, this idea had to be abandoned. Following day, Farman competed for the height prize of the Aero Club of France, and succeeded in passing over a couple of balloons placed 80 ft. above the ground. Louis Blériot Wolon had been devoting attention to the monoplane type of Lear, wasn't to about done by the Farman exploit, and on October 31st set out on a round trip from Tury to Artenay and return, a distance of about 19 miles. The machine used was Blériot Roman 8, equipped with a 50 HP, 8-cylinder Antoinette engine. Inelman, the machine passed over Artenay, Butte-Fuskin's ladder had to send owing to irregularities in thurking off the magneto. After I heard 30 min, spent in making adjustments, the monoplane went in Tothier again, homeward bound. After covering about 3 miles, a second descent had Tobe made. This time, however, the stop was only of a minute's duration and ongoing UPA game. The machine flew remarkably well until it reached its starting point, where a descent was made. The first round trip across, 72, tree had begun at 10:05 a.m. and ended at 5 p.m. A few days later, while McIntyre's near Tury, the Blériot monoplane was smashed through Strickingay hillock when running over the ground at high speed. The pilot, who had had more tumbles than any other aeronaut in France, fortunately escaped with his usual good luck. The last flying competition in 1908 was for the Michelin Cup. Tobe boarded Tothy Viator making the longest flight during the year. In his cross-country flight, Henry Farman had considerably modified his machine, with Aviation Tobe beating Wright's record for the Michelin Prize. Several different makes-off motors were tried, whilst the structure of the aeroplane was also changed, the most important modification being Teddy Tion off another plane making the machine aeroplane. It was impossible, however, to make the aeroplane as satisfactory as the Wright apparatus. Although Henry Farman made some clever flights towards themed off they are, he never seriously threatened Wilbur Wright's supremacy. Early in January, Farman sold his aeroplane to an Austrian syndicate, and having broken with Voisin Freers, commenced business as an aeroplane constructor on his own account. Although Wilbur Wright practically had the field to himself, he did not in the least relax heist for to make aerocord flight. On December 18, he covered an official distance round Atry angular course of 99 kilometers, 61 miles, his time in the being 59 fsec. The actual distance covered was not less than 75 miles, and his actual time 54 min fsec. On the same day, Wilbur Wright competed for the height prize off the Aero Club of France, the minimum for which was 328 ft. Although a strong wind was blowing, this was won with ease, his small balloons being passed with a good margin, the actual Lehite being Gavina's 377 ft. Even this didn't satisfy the American aeronaut, and he declared huge again the next day, but was prevented by rain. If afraid that the Michelin trophy would escape from him at a last moment, Wilbur Wright made another attempt to beat his own record on the last day off they are, and admirably succeeded. Well wrapped up to withstand the biting breeze, for the thermometer was at freezing point, the aeroplane left its rail just after 2 o'clock, and did not settle down again until sunset, having remained in the air 2 hr. 20 min. 23 Isaac. His official distance for the Michelin Cup was 123 kilometers 200 meters, 76 miles, while the actual distance covered was estimated at 93 miles. 73. The military value of airships and aeroplanes. Imagination necessarily playing the chief part in criticism of any new and untested force. Wheelways get extremes. That truth is the potentialities of the airship and airplane warpro babeless midway between the popular novellas chai-colored picturesque of uncontrolled and uncontrollable carnage and vastation, and the unimaginative, placid citizens' belief that comparatively little danger can come from theater at least for many years. The latter issuing the lessons of the motor's remarkable progress and modern military utility, the equally rapid developments in aircraft and the significant competition among continental military powers for machines. The former is ignoring the lesson taught by history that new weapons of destruction aerialways curbed by nearly corresponding improvements in defensive armaments. Brain combats brain, thus Fig. 70. Baby. The War Office dirigible made in spring of 1909. 74. Equalizing matters. The future will probably prove the Aeroplanes propensities for death dealing to escapable off limita tion as torpedoes. It will also prove that all such appliances are edged. Whatever happens, a nation's war strength will continue to be measured by its financial resources, its capacity to ahead of its rivals in regard to the number and quality of new destructive engines, or could only reach the height of unrestrained holocaust portrayed by the novelist if a nation were powerful and rich enough to make a corner in any new and secret murderous machine, though it is more probable that this would mean themed off bloodshed, either because any such country could englace diabolical invention, like the sword of Damocles, over the heads of its rivals and exact any terms it chose, or because all other nations would combine to prevent using of such or upon. The alarmist may rest assured that the airship and aeroplane do not come within this category. Probably the greatest misconception exists in regard to invasion via the air. A German counselor has as a Farasto state in public that a fleet of airships could land an army of 100,000 men on the Kentish coast in half an hour. Some 30 Mencken carried on a Zeppelin airship, south at over 3000 Fig. 71. Dirigible No. 1. The ill-fated Nully Secundus of the British Army. 75. Fig. 72. Their built and enlarged dirigible No. 1. The latter would be required to transport the bow force. The construction of such a number could scarcely be kept secret, and we would thus save time in which to make adequate preparations, whilst it is doubtful whether even Germany possesses their sources, financial and chemical, to build, equip and supply with sufficient gas in a short time somni machines. The last named, indeed, should prove an almost insoluble problem, being that one airship of the above type requires anything from 350,000 to 400,000 cubic feet of gas. But a more important point is that an airship of such size is to be most unmanageable in bedweather could take heavy supplies and munitions, organ size, and without ample cavalry or artillery. Fig. 73. The Ville de Paris attached to the French army. 76. Fig. 74. La Patrie, the dirigible which in 1907 was blown away into the Atlantic. An infantry force off the strength mentioned would be dangerously handicapped in a strange country if not comparatively useless. Machine guns might be brought over. Indeed, one of the latest French airships is fitted with Twagensoft Hotch Kistype, but the lack the ranging moral effectiveness to cover thedvents off infantry. Invasion by airship would. Fig. 75. Then Parseval dirigible. 77. In short, proved obso stupendous an undertaking, and attended by so many risks, contingencies, and almost prohibi type cost that on can agree with the Han. C.S. rolls that it is quite out of texture. The main drawback to the airship from the military point of view is that it cannot be implicitly rallied up in all weathers and under all circumstances. This terrible uncertainty would, to some extent, pudel commander's own evil. Military genius becomes amicary when one is at the mercy of one's instruments. There could be no dependence on an airship turning up at a finite spot within a given time. A commander whose main strength lay in airships might be suddenly crippled in violent weather and compelled to capitulate to force, strong only in the field. Military commanders might shun such machines, preferring to put their trust in the unmatchable resource, adaptability and intelligentsia of human beings. Aircraft will be indispensable adjunct to an army, but of secondary importance only. The construction of carriages that will admit off-fire almost up to zenith isenly acquisition off time, and properly equipped in this respect, our forts and naval bases would be able to bring such a sustained bombardment to bar on any hovering airships as to make the latter's position absolutely untenable. The failure of recent experiments of this kind at Gibraltar need cause now uneasiness. For much better results. Fig. 76. The Baldwin dirigible attached to the American War Department. 78. Fig. 77. The Zeppelin airship maneuvering before the Kaiser. Have been obtained in France and Germany, and Rear Admiral Sir Percy Scott is said to have all but solved textion. For serious offensive purposes, the airship can rely on no greater degree of accuracy than istobat aimed in thedrop pingo explosives, which needs no little practice. But building thoroughfares cannot be readily recognized from a height, and to him with certainty an airship would have to approach comparatively close to the earth and hover above its objective for a few moments, which might prove fatal if picked marksmen were on the lookout in favorable positions. There is a doubt, moreover, whether an airship can always be getting a position exactly over any comparatively small span at necessary height, and as magazines are usually situated in obscure and desolate spots, it would be not only difficult to locate them, but their destruction would involve little more than a monetary loss. Forward on its station, soldiers in magazines, and the chief constituent in the latter, cordite, merely burns away with a sword office. So long as it is not trigger house confined. Sir Hiram Maxim has pointed out that an added danger for those on land will be from the falling shells fired at airships, But oh balance this we have Captain Tulloch's ver-appointed reminder in the 19th century that explosives exert their force upwards, thus constituting a real danger to the airship that drops them. It is doubtful, however, whether our garrison gunners will ever to exhibit the mathematical accuracy, 79, towards the traveling aeroplane which characterizes their firing at rapidly moving battleships, simply because the flight off the former may be both vertical and horizontal in direction, making off a most baffling target. The possibilities of the airship on-night maneuvers have been it could place not check on enemies move fig, 78, the Zeppelin over Lake Constance. Mence, seeing that in the darkest nights are chosen for surprise attacks. Under such circumstances, it would neither be able to observe and report the operations nor to make a counter-attack. If a lights on land were extinguished it would have nothing but a compastorlian. On the other hand, it would be clearly visibly against the sky on a moonlight night, and this a positive source of danger to its main force. The great disadvantage of the airship in actual campaigning is that it would disclose the whereabouts of an opposing force and the direction it was taking. Even on the blackest nights, powerful electric searchlights could sweep Thesky and disclose the position of any hovering airships. And certain developments have taken place in regard to the former. Another check will have been placed on the destructiveness of airships. The latter will supplement railways for the more direct conveyance of these patches, members of the staff, special supplies, and soon, but will never supplant them. For airships will be unavailable for heavy goods, and they will be too dependent on weather conditions, and for this reason they can never equal the railways or motor, when therapid concentration of troops at any given point is desired. Nun will dispute for a moment the airship's utility for a connaissance work, observing the effects of artillery fire, photographing positions, making rough maps of the country, and soon. But the military captive balloon has answered all these purpose for over 100 years, and the airship has the same limitations, namely, fairly calm weather is essential for making careful observations, and in a mountainous country the range of outlook is restricted. Or if the river slopes off hills be steep, they can effectually conceal an enemy's position. The difficulty of communication has also it satisfactorily solved, for unless airships can be lead onto kept in direct touch with headquarters, and perhaps more important, with one another, the commander must leave them entirely out of his calculations as being irresponsible and useless. Wireless telegraphy will in due time doubtless step in her with complete success, though it is claimed that the aeroplane is not so well adapted for the installation as the airship, and Thatven in latter case there is some risk of fire. The latter's superiority over the aeroplane and yet another military requisite is worthy of note, for it can in certain circumstances rise direct from an enclosed space, descend at an desired spot, and maneuver more easily. The airship and airplane bid fair revolutionize gunnery, musketry, and even uses of cavalry in the future. There can be no forecasting the composition of the army of the future, supposing such things are still in existence. Nor, apparently, would the present-day rules of strategy answer, or commanders will have to take the weather into consideration, as being an additional weapon to use against airships, to an extent hitherto undreamed of. Campaigning may consist of protracted maneuvering, merely dallying so stronger that battles are fought on days when the climatic conditions place the enemy's airships at a grave disadvantage. As no storm, which will practically kill an airship, will be on off the occasions when contending armies will have equal chance. The real war value of airships lies, as Captain Tulloch has graphically portrayed, in their unlimited capacity for incendiarism. With everything carefully mapped out beforehand, they could operate over dense commercial districts and harbors where untold stores of combustibles, such as soil, timber, and gassy could be found. These are also, in regard to population, the most congested centers, and it needs little imagination topic to wreath a black ruin, desolation, and mad, reckless, fatal panic that might be brought about in a few short hours by a group of airships in skillful, determined hands. Mr. H.G. Wells has driven this truth home with ghastly realism in his vivid description of the destruction of New York in The War in the Air. As the airship sailed along, they smashed up the city as a kiled Wilshire its cities off brick and card. Below, they left ruins and blazing conflagrations and heaped and scattered dead. In the same book he anticipates, too, their sent remark made by Lord Montague of Beaulieu at Hem Mansion House, to the effect that the little island in the Silver Seas is near theme to its immunity, its insularity. To make that, 81F, would be the establishment of atwo power, standard in airships is the endless solution of the problem for politicians. There is only one way in which a great city can hope to escape wholesale destruction under Thebo circumstances, namely, by leveling all its fortifications and withdrawing its troops. For according to the law of nations, noun fortified and indefended towns should be bombarded. But history proves that rather than suffer such a blow to their patriotism and pride, the inhabitants of a beleaguered town will endure anything. In conclusion, it may be said that airships will probably prove of greater assistance in naval than in military warfare. For it is common knowledge that when one ice over Thessie at some altitude, With the water smooth, it is usually possible to see the bottom. Anthus the presence of mines and submarines could be detected and reported. Airships could serve assays and signal stations to fleet, as guides in long-range bombardments and as pilots in low-lying fogs. A figure carved on the tomb of Ramesses Roman III. In the Louvre Museum, Paris. 82. Dirigible balloons. The Zeppelin airship. The Zeppelin airship comes within the category of dirigibles. No matter whether deprived of the lifting gas or not, its contour remains unaltered, determined ascites by an aluminium framework or skeleton covered by an outer skin. Apparently cylindrical in form with obtuse cones fore and aft, the airship is really a 16-side prism, the framework consisting of a series of polygonal rings, trussed from stem to stern, kept severally expanded by steel wires, which, starting from each angle of the polygon, converge on a small central ring just as the spokes of a heel concentrate in the hub. Each polygonal ring, therefore, possesses 16 converging stays or, to preserve the heel metaphor, as many spokes. From the inside ends off the longitudinal trusses, which also number 16, cords off rami stretch from rintering, and form an network separating the lifting power from the uter skin. Source of lifting energy is hydrogen gas, enclosed within 16 separate cells, 12 in the cylindrical section and 12 in each of the forward and after cones that constitute the stem and stern respectively of the airship. This separate cell system is a distinctive characteristic of the Zeppelin. The count, it may be observed, was first to place separate gas bags inside a rigid frame. Destruction of an ion cell, consequently, does not necessarily involve the collapse of the airship. Between gas cells and outer scintillaries, as stated above, an air space, which plays an important part in the system, namely, to counteract the effects of freeing temperature on the gas. Air, as every student of physics knows, being an extremely poor conductor of heat. Naturally, the counteraction is in Leonov degree. The Zeppelin, with its metallic framework and more or less rigid skin, always presents a good steering surface, its form being altogether independent of the state of the gas cells, a point noted in the appending sentence. The weight of the framework and interconnections makes it absolutely necessary that the airship should have large dimensions. Zeppelin I measures 446 ft in length and a diameter exceeding 38 ft, the volume working out at some 12,000 cubic meters or 211,900 cubic feet. On the other hand, thanks to the low conductivity of the airspace between the cells and frame cover, the density of the gas is less affected than in case of dirigibles constructed on other principles. Hence, the aeronauts need less ballast as such, all that disadvantage becomes neutralized by the airship's huge dimensions, which necessitate the carrying of more fuel. With the objective stiffening the frame, Zeppelin has added a keel of triangular cross-section and covered with rubbered 83 F2. KTIG 8, F15T and Chi GONCth torjuice resistance. About a fourth off the whole length from each keel is interrupted towed mid-off attachments, fort or boat-shaped cars of aluminium and steel tubing, connected by a gangway containing, amongst other things, a wagon, which runs on rails and can behold toned frobby wire cable, for preserving equilibrium. The car-shaped pneumatic shock absorbers underneath. Each car is over 26 ft length and hangs within 7 ft of the uter skin, approximately tube V8 oscillation. Zeppelin I. Hastewo sets of horizontal steering planes fixed high up towards the middle of the stern cone at her end off two laterally placed steadying planes and operate from the cars through an ingenious arrangement of gear, wire, and wheel. Each set consists of 3 parallel planes of about 43 sq. ft, hanging like ship's rudders, almost perpendicular to the large steadying planes, each over 300 sq. ft. In area, frames of steering sets and other planes are composed of aluminium rods, over which canvas is stretched, wires holding the surfaces in position. Change of altitude is effected by means of 2 pairs of plane sets, the in a forward and the other astern, each set being made up of 4 parallel planes, attached laterally just over the keel to the first ring off the cylindrical section. Of course, their planes off position are identical with that off the airship's axis, or a tangent with the body. As each of the parallel planes terminates outwardly in a line with the others off the SOM set, they differ in length, being shorter according as they approach the center of the balloon's transverse curvature. The pairs can be worked alone or together. They have severally an area of about 240 ft, turned, slant, they act like a kite, the airship gliding upwards or downwards as their position may determine. With these altitudinal planes, in fact, the ship can rise dynamically under the power of its propellers. In other words, it can rise in spite of being at the time somewhat heavier than air like an aeroplane. 2 4-cylinder engines of 85 HP, each supplied propelling power, which gives the monster an independent velocity of over 30 miles an hour. Its propellers are in number, resting on supports fixed to the framework of the cylindrical section and high above Thetwo cars, one on each side. They are 3-bladed about 10 ft in diameter and act at a point where they can most effective, Power is transmitted from the motor through bevelgear, propeller sand motors corresponding in revolutions per minute. The French airships. First really successful airship in France was appropriately named La France, and was designed and constructed by the late Colonel Renard and Commandant Krebs. Starting from the military establishment of Chalais-Meudon in the suburbs of Paris on August 9, 1884. La France sailed at a distance of several miles to the intersection off Versailles and Choisy-le-Roi Road, described a circle, reversed, and went through various maneuvers, and returned to its starting point in Safety, the return journey of 5 miles being made in 23 minutes. Santos Dumont was first in France towed up the Petrol motor tow balloon. Hisarly attempts may be passed over, for it was not until No. 5 was produced that anything like success was achieved. This weighs a long, small diameter balloon LLLFT. In length, beautifully 19,000 cubic feet capacity, tow hitch was Fig. 80. A loss of symmetry. Deflation of La Ville de Paris. 85. Fig. 81. Clement Bayard. Avery successful ship. Attached a rough sort off platform receiving gaffer cylinder 16 HP. Petrol motor driving gallage propeller. The commoda tion fourth the pilotois varimian, there being knocker properly speaking, but merely abyssical saddle with twop del Sassona motorcycle, allowing Thinganetob started up. It was a delicate construction and needed Thodisidiofa Santos Dumont to mount it. First important experiment was made on July 12, 1901, when the airship went up from St. Cloud, crossed over the Seine, and came down on Longchamps race course less than a mile away. On October 19th off the same year, Dumont successfully rounded the Eiffel Tower on highs No. 6, returning Gitsafatito his starting point at St. Cloud, Thuner off the Deutsche de la Mueth prize off 100,000 francs. There was a paralysis back to the airship movement by the fatal accidents the following Euro Pax, piloted by the Brazilian Severe and Toth Bradsky airship. Pax was badly designed in respect to the position of its motors, the exhaust valve off the envelope being sonar tuning off the motors that a mass of gas formed outside the balloon and was fired. Baron Bradsky, whilst a non-rigid type of airship, met his death together with his companion, the car breaking away from the balloon when sailing over the suburbs of Paris. Like a Swass they are 1902, it was nevertheless the starting point of the practical airship movement in France, for at end of that year the Le Body dirigible was produced, and made more than 50 journeys between October 1902 and November 1, 903, when it was wrecked by colliding with Atri England in operations in a heavy wind. This was followed by Le Body I, even more successful than the first one, and which served as a model for future military airships, among others the famous 86 Patrie, La République, no placed at a station on the eastern frontier, was the direct successor of La Patrie. The French have never favored the rigid type of balloon, all their present airships being either the semi-rigid or off non-rigid type. La Patrie, La République / and La Démocratique belonging to the former class, and La Ville de Paris and Clement Bayard to the latter. The semi-rigid type is stiffened by thusi off a metal keel. Jittisam at times serves as an attachment for the car that carries thin Janine passengers. In the non-rigid type, the shape-off balloon is maintained entirely by the pressure off the gas within the envelope, known to being employed. The objection put forth against the semi-rigid type is that the long keel makes a descent difficult, if not impossible, except under favorable conditions. The pilots off La Patrie, for instance, it is said, hesitated to the gas out off their balloon when it was in danger merely because it was off the semi-rigid type. Had it been non-rigid, it might still have been in existence. Big 82, forward framing and tractor screw of Clement Bayard. One of the best examples of the non-rigid type of balloon is Clement Bayard, a description of which will suffice also for La Vie Paris, La Ville de Bordeaux, La Ville de Nancy, etc., being 185 ft, in length 35 ft, greatest diameter with a cubic capacity of 124,000 ft. Clement Bayard is a big balloon, though small in comparison with the huge Zeppelin. The envelope, or gas bag, isofrubbered cloth, the qualities of which must be lightweight with the greatest strength, together with an ability to hold such a light gaseous hydrogen for the greatest possible length of time. Within the outer envelope is a small second bag, or ballonnet, which is filled with pure air maintained at a certain pressure by means of a pump worked by the engine. Both the main gas bag and the ballonnet are fitted with automatic valves opening. 87. A certain pressure is attained. T&E valve is allowing the hydrogentoscapariat thurier off the balloon in order to prevent any danger of this gas accumulating in the region of the motors. The valves in the ballonnet open under a much lower pressure than those off the gas bag proper. When the balloon mounts in the expending gas, being unable to stretch the envelope, seeks an escape. The same applies to the air in the ballonnet, and under the pressure the automatic valve opens, allowing some off the air to escape, decreasing the size of the ballonnet, and giving greater space for the hydrogen gas. When the ship descends, the contrary takes place. The hydrogen gas contracting to such extent that the balloon isn't danger offlosing its rigidity. This is prevented, however, by more air being pumped into the ballonet, thus constantly maintaining the rigidity and form of the balloon. This contraction and expansion with difference in volume of the ballonet is constantly going on, the volume of the gas being affected not merely by altitude but by the condition of the weather, as sun expanding the gases, while passing under clouds causes contraction. Inclement Bayard, the balloon valves open under a pressure of 40 millimeters off water, the ballonet valves opening under a pressure of 30. The valves can also be controlled by hand. Tail of Clement Bayard aerofer cylindrical gas bags, two attached side, one above and on bellow, and all communicating with the main gas bag. The object of these additions is to give a longitudinal and horizontal stability. It will notice that the greatest diameter of the balloon is not at center of its length, but some distance further forward. This is necessary because of the fact that under the pull of the propeller, the balloon hazel weighs 8 to lift its nose in the air. This tendency being capable of increasing until the machine capsized. A science happened with Henry Gifford. Four cigar-shaped additions assure stability to the inertiability directions, correcting the tendency for the balloon to lift its nose in the air and at the some at time suppressing gow roll. The Carana modern balloon is generally a steel structure, the size depending on the work for which the ship has been built. Thus on Clement Bayard, an aerial pleasure craft, it is much longer than on La République, a fast war cruiser. The engine of Clement Bayard is a 120 HP passing car model carried on a chassis which is attached to the framework by semi-elliptic springs in order to reduce vibration to minimum. The propeller is placed at front, as in practically all modern French balloons, and is geared to turn at 300 revolutions with the engine running at 200 revolutions. The vertical rudder is composed of two parallel steel planes having a total surface of 172 sq ft. The ship has, in addition, a horizontal rudder composed of 3 superimposed planes at the front of this steel car. A type of dirigible balloon that has recently become popular in France is known as Zodiac. It is a small airship capable of carrying either 2 or 4 passengers, and so designed that it can be readily inflated and packed with much more ease than a Clement Bayard. Naturally, it is often in rigid type. 88. Piloting a voice in aeroplane. It would be an exaggeration to say that nobody can drive a voice in aeroplane, but it is not going bay and thecken finds off-truth told Claire Thatna sportsmen, especially ammon familiar with motoring, cycling, ballooning, or yachting, can learn toughtly in half an hour. The designers have made their apparatus as automatic as possible, trying to eliminate the human element, and thus giving the machine the maximum of security. Consider what happens when a flight is made. The pilot has taken his seat behind the steering wheel, the engine has been started up, and the attendants are holding the apparatus, which threatens to drag them along with it over the ground. Having given a little more gas and advanced thespar, your desire hand a signal to those in their already. The men release their hold and dewari off, running over the ground at a speed that soon increases to 30 miles an hour. Of course, there is a right and a wrong way to start, or other own a right way in many wrong ways. Correct manner is to have your machine with its nose in the wind, if a new wind is blowing, and the front edge of the elevation rudder pointing upwards, this position being obtained by pulling the steering wheel towards you. The objective racing the rudder at Hestart is not to rise in the air immediately, but to prevent the machine falling on its nose. Before the aeroplane has run out and yards over the ground, the tail will have lifted and the machine will running on its two front wheels suddenly. In such a condition, if the elevation rudder were kept in a horizontal position, the tendency would be for the tail to overbalance the front portion and bring the machine to a brusque stop before falling on its nose. Fig. 83. Mr. J.T.C. More Brabazon on high's voice in aeroplane at Issy, November 1908. The aeroplane gains speed it will rise from the ground. Yao may not know exactly what moment the heel sees touch. Beauty war of Rasunaware off every different sense of tion, anal most indescribable sensation, in which the feeling that Yao have got rid of a lot of superfluous weighty suppermost. You realize that some invisible force has lifted Yao clear off the ground, and that changes saw great that you almost imagine your leg should formerly been trailing on the ground and had no been lifted into still air. For there is also this difference, that, whereas 30 miles an hour on the ground seemed agility speed, the same rate off travel in the air is gentle motion. With the ground several feet away and objects near at hand to indicate a speed, the sense of motion is almost lost. But it is necessary to pay attention to the control of the aeroplane, or the gentle sailing motion will quickly transform itself to rough encounter with the ground. Soon as the apparatus has get clear off the earth, thingly off the front elevation rudder must be diminished, for, in its inclined position, it is offering resistance and, if maintained in this position, will diminish speed to such a degree that the aeroplane will rapidly fall. Therefore, push the steering wheel slightly forward, so that the frontage off the rudder is only slightly pointing upwards. This will still allow you to rise without offering the same resistance to forward direction as formerly. On off the difficulties awful learners is to understand that movements must be made gently, even leisurely. Unlike the motor car, which responds immediately to touch off its steering wheel, the aeroplane answers very slowly. In this respect, the control is much more like that of a sailing yacht than an automobile, alternating movement beginning gradually, increase engine strength and falling off gradually. On the ground there is a somewhat violent pull on the steering wheel, but as soon as the aeroplane gets into the air, every gentle pressure is exerted on the horizontal plane, and in consequence, the effort required off the pilot is very slight. The plane is placed in a horizontal position as soon as the desired height is attained, but even then, no attempt must be made to correct every slight oscillation off the aeroplane. Indeed, with our present no ledge, it is impossible to do so, or a manipulation off the levitation rudder to correct a slight downward dip, for instance, would certainly come too late to have any effect. The point to remember, therefore, is to operate the front elevation rudder without any brusqueness whatever. Emphasis has been laid on this because the operation off the elevation rudder is generally found to be most difficult, doubtless from the fact that sense-off movement in a vertical direction has not yet been developed. The operation off the rear vertical rudder, giving movement in a lateral direction, is a much more simple matter. Addern of the heel to the left and the aeroplane will move in that direction. Addern to the right and a curve will be made to the right. The lateral rudder is also the effect of correcting lateral balance. The machine, for instance, has a tendency to heel over to the left, caused naturally by the in striking. 90. Fig. 84. Elevation of a voice in aeroplane. Iton thurat. This would be corrected by turning the steering wheel in the direction it is desired to bring the aeroplane, in this case to the right, bringing the nose off the machine into thuend and patingaton in keel. These movements also should be made without any harshness, nor must the pilot to get heel if the aeroplane does not answer immediately. The vertical planes give us so much lateral stability that it is practically impossible, under ordinary conditions, for the aeroplanetotic such a list that it will capsize. In order to make addern, it is necessary that the machine should be inclined, and as soon as the pilot has realized that there is no more danger for him to wheel over in the earth than there is for a cyclist to be inclined when riding on a bank track, turning on an airplane will not be difficult. Having realized that the machine must be inclined, the point is to earn at a sufficient height to prevent any possibility of the inside tip-off viewing touching the ground. Making addern, there is a slight loss of speed and a certain amount of fall off the aeroplane, which must be guarded against by commencing the turning movement at various unable height. There are correct ways of settling down. 1. Generally adopted by Farman and other expert pilots, being to stop the engine when not less than 15 ft. From the ground, keep the elevation rudder horizontal, allowing the machine to advance through the air. To some at time gradually falling until the speed has decreased to such a degree that the last few inches of its flight area vertical drop, but so gently that the heels do not suffer any damage. The other method is to lower the lever to gradually until the machine is brought near the ground, with its engine still running. The ground must be struck almost horizontally, and as soon as it is felt that the wheels have touched, the front elevation rudder should be slightly raised in order to relieve the apparatus from shock. The semi-moment the engine must be stopped, and after running along for a few yards the entire apparatus will come to a standstill. An important point in connection with the descent is to attempt it, whenever possible, with thuend full ahead. It can be readily understood that, if there is merely a gentle breeze astern off the aeroplane when a descent is made, it may be driven a considerable distance before being brought to a complete stop. A side wind would tend to the machine out off the control off the pillar. Swinging get round violently, but a headwind steadies the machine, while it has some at time acting a sabrake. 91. Streamline form. All bodies that are tockled upon to move through the air should take a form which should prevent, as far as possible, the mutilation off the streamlines. It has been shown by a Fig. 85. Discontinuity offload due to Theshutter. A. Study off the form suitable for bullets and for torpedoes and submarines, although information about the latter isn't readily Fig. 86. The pressures showing the forces acting on and outward from a streamlined body. Ace the head off the body. B the shoulder, C the buttock, and D the tail. Available that addis continuous flow off fluid in which the body is moving must be voided if that motion isn't tobe Fig. 87. Discontinuity caused by removal off buttock and tail portions. 92. Fig. 88. The salmon, a fish with typical streamlined body, affected by undue resistance. If a cylindrical body, say for instance a round stay or strut, be moved rapidly through a fluid theater, for example, there will be an excessive pressure on the surface presented to the direction of motion, and as air has not time to close in round there or portion or on, there is a diminished pressure in that region. If the body takes the form of a cone, Fig. 85's theater will shoot off past the sharp edge at the shoulder at A, and behind the shoulder, the fluid will break up in toe vortex off small eddies. Maxim has found that theater in this case will have 8 indensitop rest the body at A downwards. If, however, the body in motion bay of perfect streamline form there is no resistance due to work done upon the fluid forthylate Mr. W. Froude has shown that the applied forces the pressure inward at head and at head tail and the pressure outward at fullest part off the body balance each other. Fig. 86. And there will be no resistance to its motion through the fluid. Viscosity of the fluid must, however, be load for, and it may approximate lib represented by the tangential resistance off the exposed area as determined for a flat plate off the same general proportions. If the perfect streamline body becutin half at hebeginning off thurun, shown by the vertical line in thebody in Fig. 87. The flow off the fluid will again be discontinuous, and a void will form behind the moving body, as indicated by the stippling in the figure. It is highly important in the case of a propeller blade, for example, that the cavitation is termed in that Fig. 89. The disturbance of the flow due to ace should bear a juice to minimum for the fluid becoming discontinuous, ceases to follow the surface off the blade. The body's offices and birds provide a means of studying the practical aspect of streamlined form, and the Zalman, shown in Fig. 88 is an excellent example of what Mr. Lanchester terms the fish-shaped fish. It will be observed that, whilst the entrance from the nose to the shoulders is full thurun, from the shoulders to the tail is fine Mr. Froude's assertion being that blunt tails rather than blunt noses cause eddies, thereby involving a loss of power. Losses can also accrue from thusiophoribs across the surface of a plane, Fig. 89 showing how the air is disturbed behind a cross rib. An accurate streamline form should, therefore, be depicted in connection with each constructional detail of an aeroplane. The form of the machine a sawhole should be based upon this requirement, and every item in its construction should be considered with the same end in view that offering as little resistance as possible to the air. The section off the approximately perfect plane offers a streamline aspect, the nose being blunt and the tail end fine. Stays and struts require the fullest care in designing. Not only in order that head resistance shall bear reduced to the minimum, but that the effect of a side wind upon them shall also be minimized. The body of an aeroplane generally presents a number of small surfaces to the direction of motion in the shape of struts, stays, and mechanical details, and considerable advantage can be gained by closing in a body of that character. Although care must be taken not allow the covering to form a scoop, or it will be ripped from its, generally. In secure fastenings, Fig. 90, the Jivoden aeroplane shaving the sawme off sustaining surface at an illiteral angle. 94, at a ping front edge. A fact that seems to have escaped observation until within the last quarter of a century is that the front edge of fabbirds wingus off art form ordipped. This deped front edges, according to those who have often years closely studied this peculiarity, characteristic of the form offal birds that Fig. 91. A section of a typical bird's wing showing the dipping front edge, areable to sustain a flight. A saying simply off this dipped front edge, and Chister give a section off the off herring gull Fig. 91. And assuming that the bird is making horizontal flight, thewing would take the form shown by the full lines, whilst the dotted line gives the form shortly after the bird has been killed. Fig. 92. Theirched wing sections discovered by Horatio /F. Phillips and patented by him in 1884. The dipping edge was, Sophorizal records show, first discovered by Mr. Horatio F. Phillips, who patented his discovery in 1884, patent no. 13, 768, and thewing sections which has showed in his specification are reproduced in Fig. 92, whilst his later patent of 1891, no. 13, 311 gives the modified form Fig. 93. Phillips' modified wing form patented in 1891. 95, own in Fig. 93. It is considered likely that Lilienthal, who used a anarch wing section in high experiments commencing in 1890 and continuing until 1894, didn't know of Phillips's work, whilst at about the same time Lanchester evolved the arched form achassés from theoretical considerations, and without any knowledge of the work over the Phillips or Lilienthal. Phillips assumed that a current offer striking theft forward edge e Fig. 93 at an acute angle would be deflected upwards by the forward part of the surface creating a vacuum, or partial vacuum, over the greater part of the upper surface. But Leicester considers that this theory is inadequate. Maxim explains that when a plane is curved so that it is convex on the top and concave on the underside, it encounters, as it advances, stationary air, which divides in top with streams. The top stream isn't able to fly off at a tangent when turning over the top curve, so it flows down the incline and joins the Fig. 94. Maxim believes that the air follows both surfaces, current which is flowing over the lower horizontal surface. The angle at which the combined stream of air leaves the plane is the resultant of these two angles. Thus, the plane finds the air in a stationary condition and leaves it with a downward motion, so that the plane itself must be lifted. But there is some evidence to support the theory of Horatio Phillips that a partial vacuum is created above the face off a curved plane. The PC off writing paper beheld be the finger anthem of each hand, saw that their edges presented towards the holder, and he blows horizontally on the edge and along the face. There are off the plane will be found torais. Blowing along the under surface will be found to have a much less steady effect in lifting the rear off plane. If the rear off the sheet of paper be hinged for about a quarter off its length and thin be curved downwards, blowing along the face off the plane will be found to lift the rear hinged portion almost vertically in the air and UF7 JXG action Fig. 95. The effect of blowing on the forward edge of a curved plane, seemingly right in the face off the current off air, whereas if the hinged portion be kept flat it will not lift, and if its rear end be curved upward it will morella vibrate and act as a drag upon the lifting off the plane forward off the hinge. Whatever may be theoretical explanation, however, there is no question about the superiority of a curved plane. Maxim has found in the course of a long series of experiments that if a Fig. 96, you're leaving both sides off a plane in a downward direction exerts a lifting effect on the plane. Plane, convex on the top and perfectly flat on the bottom side, but mounted in the so that the bottom side is perfectly horizontal, it will, if a current offer be passed over it, produce a lifting effect, no matter in which way it may be run. Maxim's experiments led him to assert that the practical shape and practical angle, 1 in 10, of an aeroplane area set out in Fig. 96, and he thinks that the striking the underside of the plane will not move forward ankle over the top off Fig. 97. The disturbance in the vicinity of a moving plane / according to some experimenters, plane being compressed and leaving a large eddy in the rear as in Fig. 97. He points out that the theory upon which this diagram was based does not provide that the air travels downwards after the passage off the plane, and that the lifting effect upon a plane is therefore no explained by this theory. Lanchester points out that, if the dip off the front edge be insufficient, the upward current will not strike the conform ably, and the result will be small packet of dead air just 97 g above the forward edge, whilst if the insufficiency off the dip serious, the very large pocket, practically extending over the whole off the upper surface off the plane, will occur. If the dip too great, the pocket of dead air will be below the plane and the pressure region occupying the upper surface. A condition of instability arises and the new system of low inaugurated produces a downward instead of an upward reaction. JPIG. 98. The installation of Gobron engine and the propeller on bare indicators is aeroplane. Gliding a sassport. How to construct a glider. Instructions for learning to glide. There is exhilaration about gliding which cannot be obtained in any other sport. The sense offloading through the air, off being off the earth beauty above it, off conquering a barrier that nature had for centuries drawn against man, give us a feeling of exultation and delight that can be found in neither pursuit of pleasure. There is also in gliding a splendid school for the training of quick judgment, of calm reflection but rapid decision, and of precision of movement, which stimulate the brain and develop those qualities which fledge in our modern life. And with the work that comes from the necessity of carrying the machine again and again to the top off the hill. Or, as Chanute once put it, winding up the gravity spring, there is all the exercise associated with other outdoor sports. In gliding there is nadanger, iPhone been ridiculously imprudent, and provided one is strong enough to suffer a few shocks without hurt. Thart must be learnt in easy stages, caution being thain surancy against harm, and who, entrusting himself to the element which since the beginning of the world has seemed, and evanosums, told from in skill and ingenuity, will not proceed warily. Naman ha cannot swim would throw himself into an unfordable stream, expecting to reach the other side. He would first set himself to master the ability to progress a few feet through the water, and by gradual stages learn to swim. So must it be with gliding. A few feet at first, then further and gradually further, until, with intelligent and capable control off the machine, a gliddy off 100 feet or more can be taken. From Wilbur Wright's lecture of 1901, and from the later one of 1903, both read before the Western Society of Engineers, let a lesson be to kenning caution. I further Wehrman woke exercise patience and self-restraint. They were the Wright brothers during the experiments that led them to the conquest off the air by Mchanikaflight. Impatience, rashness, and precipitation are off the very essence of peril, whilst, on the other hand, calmness, self-possession, patience, and self-restraint will carry the gliding devoted safely and unscathed through thousands of flights. Beyond those who will indulge in gliding gas nearest approach that their purse permits to controlled flight, every owner takes to aeroplaning should previously indulge in a course off glides. The present-day great masters off flight, the Wrights, Farman, and the Voisins, have learnt their elementary notions of equilibrium in theophrong gliding experiments. Chanute, with his assistant, Herring, whose work has not yet been 99G2, accomplished, capped, Ferber Archdeacon, and others have practiced thart not primarily for sport's sake, though enjoying sport, but for education and instruction. The first and ruling qualification for the sport of gliding is the accessibility to suitable slope. The ground should bay open Fig. 99. Plan of glider giving dimensions off to land width off main planes. And free from trees with knobushes or gorse heather does not matter to cause obstruction when alighting. Heather, in fact, is an advantage just to Sandy's because off, cushioning it afterwards should a glide be prematurely terminated. How smoothly the glider comes to ground at the natural termination off a flight can be gathered from the fact that the Wright's assumed apron position during their gliding trials. The slope should be from 1 in 10 to 1 in 7 and should be from 150 ft to 300 ft or 400 ft long. Such slopes are not found in many parts, and it should therefore be the first concern oft would be gliding exponent to discover a suitable ground, which should also be at least 150 ft wide. Reason the proximity do not matter if the aeroplane in regular order and if the machine does not approach them too closely. Fourth, a novice no better material will be found fourth a framework than bamboo, which can be obtained selected fourth a job. In respect of its section, it is not all that can be desired for the reduction of wind resistance, but thise is not of much importance at high speeds which the glide retains, providing strength with lightness. Bamboo possesses the additional advantage that it requires no working. It is ready for using the state in which it, 100, spot only as being required to cut it at the correct length. Owing to the fractures that Araja took during the initial glides, it will be useful to lay in some spare lengths figs, 100 and 101. Dimensioned elevation plans off glider, over and above those actually required for the frame in the first instance. The quantities and materials that must be taken into stock for the construction of the glider are 1. Bamboo, 135 yd, in lengths of 6 ft, 14 ft and 18 ft and of Idjin. Diameter, 2, piano wire 175 yd, off silver-plated 0.56 in die. No 17s WG. 3 9 dozen hope rigging ISO about 7 ft of no 20 imperial wire gauge copper tubing 3-16 in external diam. 4 calico 25 yd, off double width. 5 brass sheet 1 askew yd. 24 BW gauge 6 screws and nuts agrosoft 3-16 in. Lin long 7 a ball of cord, though variations in prices will be found in different locali ties, especially with the bamboo it may be taken that the average cost of the materials will accord with the following estimate s. D. 1. Bamboo 112.2 piano wire 126.3 copper tubing 24 calico 14.5 brass sheet 96 screws and nuts 69.7 cord 1 total 101 3,173 big 102 sheet metal is cut for making joint holders. No count is taken off the cost of labor, nor are the necessary hand tools priced, the assumption being that the glitter stove made by an amateur already possessed off the pliers, hacksaw and wood saw that form the small outfit required. Before the construction of the frame can be undertaken, a number of joint holders must be made. The simple pattern shown in Fig. 102 and juiced as in Fig. 103 will be found quite serviceable and lends itself well to the variations in the section of the bamboo. Since 3 dozen of them are required, the labor of cutting them out from the brass sheet may well be deputed to la near. It is not likely that their production will appel to the mature. In the views off glider shown in Figs, 99-101, thick lines in die-catthwood structure, thin lines representing the wire rigging. Ta make a start with the job. Take tooling soft bamboo each lift, gin, long and well matched, Huda plug to fit ends, and dipping this in white lead or varnish, use a tassadole for the butt ends off the bamboo, see Fig. 105. All that head joint could then be bound up, but turgib can be made if some bamboo splints are laid along the butted ends. The splints can be obtained by splitting a short piece off bamboo and tapping off the edges. Using 3 off these, bind the joint up with wire at 4 points, as illustrated in the diagram on next page. Ins ofach binding wire should be crossed under the off wire in the spacing between 2 splints and twisted one each other above. The binding can then be tightened by driving wedge into the spacing between the splints, means being employed to fasten the wedges. This will make a strong and workmanlike joint, neat and tiddy. If desired, the joints in the bamboos can be rasped down nearly flush without weakening the sticks. Lay out another 21 ft, lengthen the same manner, and bend a half dozen joint holders over each at intervals corresponding to the positions off 1, 2, 3, 11, 12 in the drawings, remembering to turn the lap off the joint towards the inside. Cut a dozen lengths off 5 ft, and laying that with 21 ft. Poles on the ground fit the short pieces horizontally into the joint holders. This will give a stiffened Fig. 103. Adjoint holder bent to shape and placed in position. 102. Rectangle which will form one off the main planes. Into the tops off the joint holders should next be fitted a dozen lengths off 4 ft. 9 in. On the free ends off which must be placed thuper main plane constructed in themanner just described for the lower one. At his stage the frame will present s/operancio for Fig. 104. Framework ///cage ashone off main planes of glider. Herewith, Though possessing the elements of rigidity, it will need bracing. Even for this, no great skill is required, the type of fastening chosen being of the simplest. The hope rigging I is fully described on an author Aero Manual. It asterisk may be used with great benefit iPhone desires a netly finish head job. These ice can bellush totha bamboo joints by light wire, as he's done in canoa rigging. This method has the advantage that the stays will seldom require tobe to tind, but there is the disadvantage that tow haul all the lashings up taut, when they have slacken. Takes a considerable time. An alternative method is to adopt the voicing style off rigging. The copper tube and cut it into short pieces about in. Orphan. Long. Through each off these a piece off the piano wire must be threaded and bent back so that the tube may be fig. 105. Method off making bit joints with bamboos. Fig. 106. The voicing method off making ice by passing thined off the wire twice through a piece off copper tube, leaving an eye and bending thined off the wire over. Pushed over double thickness off the wire. See Fig. 106. Twist thined of nip the wire offshore. This will give a good eye fastening which cannot slip, and which is small enough tobe clamp by the off that joint clip whilst being amply strong. A similar eye must be lashed at he author end of the length off wire necessary for the diagonal. It is not of the greatest importance to have a strong tension on the wire, but it is very advisable to have the tension offal the wire's uniform. Straining screws can be regarded as refinements for gliders. There may be little difficulty at first, but after a few attempts one can become quite an adept at getting the proper length of wire. The extent of the bracing can be gathered from figs. 100, 101, and 104, each cell being braced along gall. 103. Diagonals and the frames off the main plane stiffened, as shown in Zeppelin view. If supported at its outer ends, this skeleton structure is capable of supporting a load off about 3 cwt. In the center. In the construction off the tail, exactly the same procedure as tobe for load, the spread being 6 ft, 6 in. 4 pieces off this length must be sawn off, and there will also be required 6 lengths off 2 ft. Sin. 4 the vertical members and 6 lengths off 3 ft. Or in. Toes of us fore and aft members. The same pattern off joint holder being available as in the building off the main planes, the completion off the tail will offer no difficulties. For its attachment to the supporting planes, 4 rods 18 ft in length must be used. These interlace between the bamboo struts off the main planes and tail, as depicted in Fig. 101, and are then lashed with wire drawn tightly round the struts and main poles. By rigging diagonal wires across top and bottom and across both sides, the entire frame off the glider will be rendered quite rigid. Both the main planes have tobe covered completely with calico, except for the space between the points 9 and 10, see Fig. 100 on the lower plane. This space, which corresponds to the joints in the main poles, is required for the aviator, who supports himself on woe bearers set at the most convenient distance apart and lashed at both ends to the main poles. The calico must be turned over the bamboo members and stitched in place after it has been drawn upas tightly. As possible. Tail also needs tobe covered with the same material, butinth is cast their aerial saw 3 vertical panels tobe added, as shown in there are elevation off the glider. If necessary, the calico can be shrunk by coats off starch paste. Trials can be made in a steady wind that is strong enough to lift the glider when it is shelled beyond off the front cross poles. In the initial glide it is essential to have the assistance of 2 men. For this purpose 2 cords about 6 ft in length should be attached to the forward extremities off the lower main plane, and these should be held by the assistants, 1 attach end. Having determined the direction off the end, face it, place yourself in the glider with the supports under your arms, and Javethiater to start down the slope at a moderate pace. At hind off a few steps the glider will lift the passenger from the ground, but the assistants should continue touring right down the slope, keeping the cords in their hands. Caution is most advisable, and it should not, until at least a dozen captive glides have been made that an aviator should attempt a free glide, and even then only if he feels perfect confidence in his ability the machine. To steer to the right, throw the legs to the right. To steer to the left, throw them to the left. Toe light, bring the weight off the body further forward. At first there will be tendency to keep the body too far back. This must be strongly combated, for it is the only position that is dangerous. During the captive glides, the effect of various movements off the body must be closely watched, for upon them depends the control off machine. When these details have been mastered, a short free, 104, glide can be attempted, theater talkast off being given to the assistants almost as soon as zones feet they have left the ground. The cord should be released by the assistant simultaneously, otherwise the machine will not glide straight and evenly. The great thing to master is to bring the machine smoothly to the ground by stretching the legs forward. With these hints, it must be left to watch one's practice tube tain the skill which renders long glide sign when fairly strong winds quite safe. A few minutes in theater is worth more than the same number of weeks off theoretical study. Fig. 107, stern view off La Ville de Paris. Fig. 108, stern view off Clement Bayard. 105, aeroplanes of 1908 and 1909. The Wright aeroplane. The Wright Aeroplanes exceedingly simple apparatus, the main features of which are at large superimposed plane sustaining surfaces. Two similar planes, built of much smaller dimensions, carried in front and pivoted to form a elevation rudder, and at rear, two vertical planes orators, operating in exactly the same way as the rudder of a ship. Near the forward edge of the main lower plane, slightly out off the center linie, is a four-cylinder petrol motor, driving by means of chains, a couple of propellers in the rear, both chains running in tubes, and on off them being crossed in order that the propeller should turn in opposite directions. The apparatus sits to the left of the engine, counterbalancing its weight, and has a wooden lever in each hand. The left hand lever racing or lowering the forward elevation planes, and the right hand overhaving a double movement, forward and rearward. To turn there are vertical rudder, thus jiving lateral movement to the machine, and to left and right in order to bend, thewing tips to facilitate turn and maintain lateral balance. The apparatus is mounted on long wooden runners, slide over the ground on aid being made and by their friction bring the apparatus to stop. Starting is generally accomplished by a catapult system, the aeroplane being mounted on a bogie running on a long grayland shot down it by means of falling weights, accord answerable arrangement of pulleys. Each wing of the Wright aeroplane measures 41 ft, from tip to tip, and is 6 ft, gin, from front to rear, thus giving a total bearing surface of approximately 538 ft. The two main sustaining surfaces are united by 9 pairs of stanchions, each 5 ft, L-oin, in height. The sustaining surfaces are a composed of a wooden frame built upon the main members of American spruce, each 41 ft. In length, the front member having a thickness of about 2 in, with its foredge rounded off to for less resistance. The main frame members are distant one from the other 4 ft, 3 in, and are united at their extremities bite across members off the same thickness, and also rounded. Across the frame thus formed are placed 32 curved ribs, with a curve of 1 in 20, each shown flush with the front frame member butte overhanging there are one. The ribs, which have a total length of 6 ft, 6 in, are constructed as shown in Fig. 115, namely, off to curved members separated by wooden blocks gradually tapering towards there are, where they are united by a steel cable. Each of the curved frames thus formed is covered on both its upper and lower surface by rubbered cloth nailed at front edge and sewn at her rear. 106. 19 wooden uprights uniting the two bearing surfaces are not all rigidly fixed. All the front once and the middle rear once are secured in aluminium sockets to the main frame members, but 6 off the rear owns 3 8-end area attached by a system of hook and illustrated in Fig. 119. The bolt is secured to the extremity of the stanchion, fits on the hook of the frame, and is prevented from slipping off by means of a split pin. These hooks at some time serve to see the ends off the wire stays with which the structure is strengthened. A feature of the staying off Wright aeroplanes that there isn't a provision for regulating the tension of the wires. The end of the wire is doubled back toppus into copper 2, the hole being soldered, and the loop this formed fitting on the hook off the frame member. The reason for this pivoting structure is to low off bending there are extremities off viewing tips in a manner and for a purpose that will be explained later. A V Fig. 109. The Wright aeroplane, elevation and plane. The main planes, V the forward elevation planes, Z there are vertical rudders, S the forward fixed rudders, D the starting grail, the machine being mounted on its trolley, M the motor, C the driving chains, HH the propellers, PP the seats for driver and passenger. 107. Big 110. The forward elevation planes and the fixed vertical rudders, the machine on its starting grail, about 10 ft. Ahead off the main having the elevation rudder, which may be roughly considered a reduction off the main bearing surfaces. The elevation rudder is composed of two superimposed horizontal planes, each 14 ft, L-oin, from tip to tip 2 ft sin, in depth and 2 ft tin, apart, between the two surfaces and 6 ft, apart. Area couple of half-moon-shaped vertical planes, free to pivot slightly on their axes. At her rear and distant 8 ft, gin. From the main planes is the lateral rudder, composed of two vertical planes 5 ft, L-oin, in height and 2 ft, in width. The two planes are united by cross members and are distant from one another 19 in. The entire apparatus is mounted onto long wooden skates which commence a little to the rear off the main plane, and it therefore wardened air curved up to attach to the elevation rudder. Sets off wooden stays connect the forward end of the skates to the fore edge of the upper plane, thereby considerably strengthening it. On aids being made the skates come in contact with the ground, and be there friction bring the para to stop. Under favorable circumstances, as, for instance, on smooth, wet grass, the apparatus can be driven over the ground on its skates and made to rise in the air without any external aid. The more common way of starting, however, is by use of the catapult. The mechanical portion of Wright aeroplane consists of a 4-cylinder motor built by Blériot and Mar from the Wright brothers' own designs. It is what may be designated 108 medium-weight motor, not Solidates the special aeroplane engines recently developed in France, viewed considerably lighter than the standard Kerngen, which it resembles in all main features off design. Thingen escarried near the forward edge off the lower plane, viewed about 2 ft, to the right off the longitudinal center. The pilot occupies a seat off the left off the engine, thus counterbalancing its weight. The passenger seat is between the pilot and the engine and almost in the center line off plane. Thus, whether a passenger is carried or not, the lateral Fig. 111. Rear view showing engine, propellers, and transmission. The skate's aerial saw clearly seen. Balance off the Aeroplanes not disturbed. Thingen drives a couple off wooden propellers in the rear. Those generally employed have a diameter of 8 ft, 3 in, and they're geared 33 to 9, giving 450 propeller revolutions a minute. In this respect, Wright machine differs from most oft French machines, where the propeller is mounted direct on the engine shaft and turns at from 100 to 500 revolutions a minute. During 1908 trials in France, the propellers and the gearing were frequently changed, the longest flights being made with propellers of 9 ft, 2 in, diameter. The supply of cooling water for Thingen is contained in a radiator composed of plain, flat upper tubes attached tune off the forward stanchions off the aeroplanes. The quantity of water carried is a little over 2 gallons. The petrol supply is contained in a cylindrical reservoir, at first placed horizontally, but no hung vertically between the two main planes. The flow is begraviter the petrol pump within the crankcase, from which the petrol is directly injected into the cylinders. It has already been stated that, under favorable circumstances, the aeroplane can be started from the ground on its 109 runners. The general method of getting into the air, however, is with use of and falling weights. It is a method that has been much criticized, the critics maintaining that so long as this apparatus was necessary, the Wright aeroplane could never be employed for cross-country flights. The catapults is Fig. 112, the struts and stays off the latest form. Fig. 113, the primary warping mechanism with its lever to warp the upper plane. Fig. 114, the secondary warping mechanism to warp the lower plane. Turn, however, isonly a means for getting into the air, and so long as operations are confined to flights over a specially prepared ground, it is a most convenient method, and on that is successful in 99 starts out off 100. It will be soon enough to burden the apparatus with wheels when cross-country flights are attempted. The wooden starting rail, the upper face off which is bound with metal, is 68 ft. in length. A wheel wooden bogie, formed off to lengths of wood placed at right angles, is laid on it and receives the aeroplane, which, immediate live for the start, is supported at her right-hand tip trestle. This side, of course, being heavier by reason of the motor being out off center. To the rear off the aeroplane, a citrus on the starting rail is a pylon, to the summit off which are hoisted a number of metal discs weighing about 14 cwt. The rope securing discs passes over a pulley at the summit off the pylon, under another pulley at head base, then travels forward underneath the 110. Fig. 115 showing construction off the curved ribs forming framework off the main wingstove covered with rubbered cloth on both surfaces. Airplanetopoli at the extremity off the rail, returning along the rail to the aeroplane, to which it is attached by means of a hook. When the aeroplane has been placed in position on its rail and the weights mounted, it is temporarily attached in the manner shown in Fig. 116. Here the pilot seat is shown at S. Beneath him is a bar, hinged at B and secured in a notch of the plate P. Around the bar, A is a short wire cable secured to the starting rail. Thingen having been started and the trestle under the extremity off thewing replaced by an attendant, the pilot leans forward and pulls the bar, P, out off engagement with A, with the result that this letter falls, the cable, C slips over its end, and the aeroplane is free to shoot down the rail. Under the combined influence of the falling weights and the revolving propellers, the 68 ft off the rail are covered in 3 f-sec, which gives a speed at head end off the rail which may be estimated at 35 miles an hour. While running down the rail, the front elevation rudder has been kept in a position to hold the aeroplane down, and it is only as the end off the rail is reached that it is raised and the apparatus rises somewhat rapidly into the air to perform its wonderful evolutions. The pilot hastes to operate 2 different steering levers in order to preserve the machine at the right altitude. He'll maintain longitudinal and lateral balance and to make his turns. He has in no way to occupy himself with Thingen, which is indeed unprovided with any other control than an appliance for relieving Fig. 116. The method of attaching the aeroplane to the starting rail and off releasing it. The compression and stopping when it is desired to send. The point of ignition is fixed, the throttle does not exist, for the supply of petrol is mechanical, and lubrication is assured by a pump. The lever in the pilot's left hand has a simple movement forward and backward. If pulled towards the pilot, the front elevation planes are slightly raised and the tendency of the aeroplane is to rise to higher altitude. If pushed ahead, the 2 planes are made top point towards the ground, and the direction of the aeroplane is then downwards. Reference to Fig. 117, front elevation rudder and its method of control. The lever fish held in pilot's left hand, Fig. 117 shows how the movements area obtained. Fist lever tion lever pivoting at G and having attached toit by a bolt thebar, a connected up to the short lever B and controlling 3 connecting rods C, operating on the tubes D and inclining the planes. Thea per tinglever, F is in its normal position. The elevation planes have a slight curve, but be reason off the difference off length between the front and the rear por tions off the connecting rod C, as well as the front and the rear portions off the planes. When the lever is carried full ahead, the rear off the planes are carried upwards, as shown in the dotted line. When the lever is per the forward edge off, the planes is raised but slightly and the rear is fully lowered. The control off the elevation rudder is first given top pupils learning to handle the machine. Whenever the aeroplane has a tendency to if the lever is pulled back, if the machine is going too high, the rudder is pushed forward. The movement is only slight and is very difficult to follow by an observer on land. The right handlever is more complicated in its operation and more difficult to maneuver than the just described. There's 2 distinct movements, forward and backward, and toe left and right. If the lever is merely carried ahead, it will direct the vertical rudder over to the left and cause the aeroplane to turn to the left. How this is accomplished will be immediately understood by reference to Fig. 118, in which is the right hand lever, B the forked and connecting rod, C the pivoting crossbar, and Fig. 118, the combined rudder control and wing warping mechanism. D thetwo cables connecting to thetwo extremities off the vertical rudder. If instead of being carried forward, the lever A is moved over to the left, it will naturally at the same time shift the short lever F in the same direction, tightening the cable G and slackening the cable H with their salt as shown in Fig. 13p. 21, off-lowering the right-hand wing tips, and the being interconnected, as shown, racing the left-hand tips. This, of course, is made possible by reason of the pivoting joints off the rear stanchions already described, and Javes helicoidal torsion necessary for modifying thingles off incidents at which things off the wings are represented to the atmosphere. The outcome off the movements off the rudders and off the warping off the planes require to be carefully studied, because off the conflicting forces at work. The wings are so warped to tear rear corners, for the front edges remain always under form, that the left-hand end, assuming that the spectator is standing behind the machine and looking at the direction of travel, is depressed and the right-hand end is raised. The left hand end presents the greater angle of incidence to the atmosphere, and will rise because the pressure of the atmospheric action on this part is increased. The right-hand side, offering a lesser angle of incidence, will tend to fall. This permits the lateral balance to be maintained, but it also has the effect of causing the machine to turn on a vertical axis towards the left hand. Thus, as the angle of incidence increases, the tendency to rise is gained at expense of forward speed. Consequently, 113. The angle of incidence on an side is increased, and, on the other, decreased. The machine will tend to slow down on the outside off the curve and thus produce opposition to the desired turning movement. To overcome this action, their rudder is employed in combination with a fixed rudder forward off center of gravity. The right patents covering also a pair of rudders, one forward and one at rear, operated simultaneously. The right patents also cover a pair of vertical vanes, one attach end off the machine and situated between the horizontal planes. These vanes are mounted on a vertical shaft, which has a pulley at its lower end, and these shafts are connected up picables with the steering apparatus so that they can better tupos the secondary movements which tend to become produced. Fig. 119. Constructional work on the right aeroplane, showing method of hinging struts and off-securing eyes off-state. A quick turning movement off the right machine is shown off its distinctive features, and is in strong contrast to the slow turning ability of almost all French machines. Naturally, a very wide turn can be made on the right machine by the vertical rudderly, but in practice the wing serialways flexed a slight degree at Hassam at time. In reality, turning is only a secondary object of the flexing off the wing tips, most important being to maintain lateral balance. Such an unstable element as the aeroplane has a constant tendency to oscillate in all directions. The tendency to plunge or is corrected by the manipulation of the elevation rudder through the left-hand lever. The tendency to roll is overcome by the flexing off the wing tips. Should the aeroplane take allus towards the left, the vertical rudder would at Hassam at time be inclined. If it is brought back to a vertical position, this tendency would be corrected. The contrary, of course, applies if the heeling movement off the aeroplanes towards the right will be noticed that, with the exception of the operation off the vertical rudder, which requires the lever toe pushed ahead for often underwards for a right turn, all controlling movements are natural. Thus, Toadsend, the operator, leans forward and carries his left-hand lever with him. Toadsend hepels on the same lever. Ta make a sharp turn to the left, he carries his right handlever in that direction, at his same time, of course, moving it forward. If the machine is inclined towards the left, he leans over with his right handlever in the opposite direction, thus causing the aeroplane to right itself. There is a certain analogy between the operation of a right aeroplane and the controlling movements of a cyclist. In both cases, the movements Aeroslight and are performed, after the apprenticeship period, almost unconsciously. The cyclist, for instance, who feels his machine skidding under him, cannot say exactly when he began the correcting movement with his body, nor when he left off. The aeroplanist who corrects the aerial skidding of his machine would have equal difficulty in saying just when he begins and ceases his correcting movements. The voice in aeroplane. The voice in type of aeroplane, often spoken of fast Farman type reason off the success of the aeronaut with a machine built for him by the voice in brothers. A roughly considered as a Hargrave box kite with a horizontal planane front and a vertical rudder in their cell. Originally, it consisted of a couple of superimposed planes, with a vertical rudder in their and a horizontal elevation rudder in front. In 1905, the cellular tail-added anthem planes were fitted with vertical divisions. Since then, the machine has undergone many minor changes, but its main features have remained unchanged. The aeroplane may be divided into 5 distinct parts. The chassis, an entire lineal structure carrying two wheels by means of which the aeroplane runs over the ground prior to tacking the. The fuselage, or forward framework, carrying the engine, pilot seat, and all controlling organs. The main forward planes divided vertically into 3 distinct cells. The tail cell containing a vertical rudder, and the framework connecting the. On the earliest models, the wings were plane surfaces, united, as already described, by 4 vertical planes, and was, in fact, nothing more than a huge box kite. Experience soon showed, however, that this form, though possessing remarkable stability when used as a kite, weighs all told they're lacking in this quality when built to travel through the air under its own power. The surfaces were, therefore, given a slight curvature, both in length and in width, the exact degree of curve being determined after numerous experiments. The 2 main surfaces measure 32 ft, 9 in, from tip to tip 6 ft, gin, from front to rear, and are distant from one another 6 ft, 6 in. The framework of wing is composed of 2 long hickory members 32 ft, 9 in. In length, united by a series of slightly curved cross 115 h2 members flush with the wooden frame member at front, but exceeding the neat the rear, thus giving a rigidity to the which meets the air, and a certain amount of flexibility at her rear. The skeleton thus formed is covered with rubber-proofed cloth. The upper planes applique of the lower one, and is jointed to his ladder by 8 pairs of bamboo stanchions suitably secured by metal joints and strengthened by wire stays. Eans are enclosed by a canvas covering stretching from frame to frame and stanchion to stanchion, and to their vertical divisions are fitted, dividing the struck 3i Fig. 120. The voice in straining screw with wire loops to prevent turning. Fig. 121. The voice in I at thin wire stays, ture in to 3 distinct cells, the central one being the largest. The depth off the vertical planes is less than that off the horizontal planes, the former being attached to the stanchions. There are cellar tail designed to fulfill the same functions as the tail of a kite, namely, to give stability to the main member, is much smaller than this latter, the measurement from side to side being 8 ft. 9 in. It is constructed, like the forward cells, off a wooden framework, covered with canvas and strengthened by wire stays, but its stones are completely closed in. Between the 2 horizontal planes is a vertical rudder operated at will with a pilot and table illuminator that will be described later. The distance between there are off the forward planes and the front edge of third planesis, 13 ft. The connection being made by 4 frame members united by stanchions and suitably strengthened by stays. All the mechanical organs off the aeroplane are mounted on a special framework known as the fuselage, and are presented by Fig. 122. It is roughly the form of a flat-bottomed hydroplane boat and is formed of longitudinal members united by vertical members suitably trussed. In order to for less Fig. 122, the fuselage or main body of the voice in aeroplane. H6. Fig. 123. There are off fuselage off voice in aeroplane. Resistance to advancement, the framework is covered with rub-bird cloth. The fuselage may be regarded as the main framework off the aeroplane, for it attached the fixed wing synthesis scurrying two wheels, while mounted at its rear is the engine and propeller, and immediately in front of thighs the pilot seat. At front off the fuselage is the elevation rudder, consisting of 2 horizontal planes, each 6 ft. Gin, in width and 3 ft. From front to rear pivot ashone in Fig. 122, so to vary thingly off inclination and determine the rise and fall off the aeroplane. The chassis is an entirely metal structure mounted on pneumatic tiered wire wheels and secured to the fuselage. It is fitted with powerful shock absorbers, and the wheels are mounted in the same way as casters, being free to turn in any direction. This is necessary to prevent breakage when landing. Fixed wheel always buckling up, whereas these orientable wheels, as the French term them, allow off-sealing down without any damage. Farman has made over 300 descents with this type of wheel without a single breakage. The tail-off apparatus is also fitted with a pair of wheels, free to turn in any direction, of much lighter construction than those in front, there and lyric being to kept their ourself from touching the ground. A single steering wheel, mounted at extremity off an almost horizontal steering column, controls all the movements of the voice in biplane. It carries a drum A-fig 124, round which is wound a flexible wire cable carried along the frame members to the rear vertical rudder. Thus, adern off the steering wheel, the right will shift the vertical rudder in the same direction and cause the aerostatics to the right. Adern off the wheel to the left will have the contrary effect. In addition, the steering wheel can be pushed away from or pulled towards the pilot the shaft on which it is mounted, having a squared section to low off this movement. On being pushed ahead, the front elevation rudder is lowered, as can readily be understood from /a fig. 124. The steering shaft off the voice in aeroplane. Examination off the diagram. A pull towards the pilot raises the front edge off the rudder and lowers their edge. The effect of this displacement off the plane being in the case tacos the aeroplane send, and in the other to raise it. On a versal joint, N, allows the plane to be operated whatever the position off the steering wheel. Although the most important flights off Farman and Delag Grange were made with an 8-cylinder Antoinette motor, there isn't a standard type of engine for voice in biplanes. Essentially, a number of comparatively heavyweight 4-cylinder engines have been employed, while the voice in brothers them fig. 125. A asterisk voice in aeroplane. Selves have a special 4-cylinder motor off their own design no under construction. In every case, however, the motor is mounted on the rear off the fuselage, O'Neill vel within near there are off the lower plane. The Antoinette engine said be Farman and Delagadroved atwo-bladed steel and aluminium propeller having a diameter of 7 ft. Gin. And a pitch off 4 ft. Tin. The propeller waskied directly to the main shaft off engine, revolving at 1050 revolutions a minute. 118. REP monoplane. Robert S. Nault Pelterius flying machine, commonly known as the REP. Isown off the few that they've been entirely designed and constructed by Oman. The machine is a monoplane with paraflexible wings capable of being warped by means of cables. There are horizontal surface ordale, fulfills the conditions of elevation rudder, and between it and the main wingsis a vertical fin to assure lateral stability. A flying machine is mounted onto wheels placed tandem fashion, and an allied wheel at extremity of each wing, the latter being brought in tausion when a start is made. The main wheels are shod with pneumatic tires and fitted with powerful pneumatic shock absorbers, the chassis to which they are attached being off steel tubes united by oxyacetylene welding. The motor is at the front of the apparatus and drives a fur-blade propeller mounted direct on its main shaft. A feature of REP Aeroplanes its compactness, the length from wing tip to wing tip being 31 ft, and its length from front to rear 26 ft. Frictional resistance had been reduced to a minimum, and excellent construction has allowed the weight of reduced to 9,251 b, for a total bearing surface of 163 sq.ft. The wings are constructed off a wooden framework with steel and aluminum joints, covered on their upper and lower faces with rubbered cloth. By reason of their flexibility and for flat steel stays, 2 under each wing, it can be raised and lowered in opposite directions, the right tone being raised and the left tone lowered, or vice versa in order to assure lateral stability assist in making curves. The pilot's position is an small cockpit between the two wings and behind the motor. There are members consist of tail, a plane surface capable of being raised or lowered at heel off the apparatus in order to determine the rise or fall off the aeroplane. The balanced vertical rudder is placed under the horizontal elevation rudder, and at the rear of the chassis, in its neutral position it constitutes, together with the vertical fin above and slightly ahead off the horizontal plane, a powerful equalizer imparting lateral stability to the aeroplane. The entire framework of the machine is covered in with rubbered cloth. The engine employed is a twin-cylinder air-cooled REP, the features of which are set forth in the chapter devoted to aeronautical engines. It develops 35 HP, and being right in Thebo off the apparatus receives a sufficient current offer to keep it cool so long as a speed of JZ miles an hour is maintained. Control off the aeroplane is combined in 2 vertical levers to the left and right of the pilot. The left-hand lever, mounted on a versal joint, is capable of being moved in any direction, a lateral movement operating the wings, raising one and lowering the other, while a movement ahead or astern lowers or raises their elevation rudder. Lateral direction is assured by the right-hand lever, that turns being made in the direction in which it is desired the aeroplane should go. An illustration of REP machine appears on 72, 119. Henry Farman's Aeroplane No. 3, designed and built by himself, is similar in general features to the voice and biplane heifer Merle piloted. The two main planes measure 34 ft gin. From tip to tip, and the length of the apparatus from front to rear is 42 ft. Gin. The two planes are united by 8 pairs of stanchions strengthened by wire stays, and a son the first biplane used by Farman at without vertical planes. Lorenz are fitted to the rear of each wing, a suitable arrangement allowing off their manipulation at will off the pilot. The peculiarity of the rear cell is that it does not contain a lateral rudder, movement tolft and right being obtained by warping the extremities of the two vertical planes. In front is a single elevation rudder in place of that was at rudders on the voicing machine. The framework known as fuselage on the voicing machine has been abolished on the new Farman motor. First cylinder vivinous of comparatively heavy weight, being carried on a suitable base and attached direct to the center off the lower plane. Yon piece two-blade propeller, having a diameter of 7 ft. Gin, is mounted directly on the end of the propeller shaft, revolving in the space between the main frame members uniting the front enderplanes. The pilot's position is immediately in front of the engine, seated on the forage of the lower plane. A combination of skates and wheels has been employed for starting the machine and settling down towards. Under the forward planes Aerotwapper soft pneumatic shod wire wheels, inner one o fatchbear being slightly smaller than the outer one. Between Thetwo is a long wooden skate stoutly attached to the planes, just clearing the ground at the front, buting contact with it at the rear. The tail is prevented from touching the ground by a couple of small wheels free to turn in a direction. The Aeroplane. Aeroplanes AV, Ro's latest type of Aeroplane, AV Ro plane. It is equipped with Atwo cylinder LOPJAP, air-cooled engine, which drives a fur-blade propeller of 7 ft. diameter. The machine weighs no more than 2,501 b, which with 1,501 b for the aviator makes a total weight of 4,001 b. This works out at 401 b per HP, which is in excess of 251 b, Fig. 126. The system of warping the wings off the row aeroplane. 120. ITFM % PJ Fig. FZ. 727. The AV row airplane or Aeroplane per HP usually carried by the successful French aviators. From tip to top, the main planes measure 20 ft and they are 3 ft 7 in deep. The tail is 10 ft. Wide and off the summit depth as the main planes. The planes are set 3 ft 2 in apart. The overall length of the machine is 23 ft. The total surface is 320 sq. ft, which works out at just LLB per sq. ft. The machine has several novelties, of which the chief are steering gear and the method of bracing and twisting the main plane stock control the vertical and lateral course of machine. There are vertical rudder istern by rotary movement off the heel. There are plane swordale being fixed from lido, the body off machine. Edelting and twisting off the main planes is carried out entirely through levers and rods, without thusiophonic cords or pulleys whatsoever, thus removing one source of danger in an aeroplane. The central main plane, A, Fig. 126 is braced from end-toe and bithuire braces, B, soffit aggerter unalterable and chape secured. Vertical struts can D, carry upper and lower planes and cassethum toe warp similarly to the main central plane. To permit this movement, which would not be possible with stiff struts forming part of the girder, the struts marked dare all thinned in the middle soffit the may bend as indicated by the dotted lines. The struts C, of course, donatrek wire toe otherwise than stiff. Connections are made between the middle planetits edge, through rids and levers, to the column off the steering wheel. A rocking up and down off this column moves the main planes and alters the angle of incidence. Turning the steering wheel twists the main planes and moves the rudder at his summit time. Mr. Roe has not yet succeeded in making flights of any length, wherefore that his airplane is underpowered. 121. Antoinette monoplane. The body of the Antoinette very closely follows the lines of a boat, the transverse section of which is triangular, and the planking replaced by a light canvas covering. The boat has a fine bow, and even at its greatest section isonly sufficiently wide tolo off a narrow cockpit for the pilot, about 1/3 from Thebo. There are gradually narrows toe fine taper. The bearing surface consists of dwellings tolft and right off boat-shaped body, and slightly raised so's to form of a open V, 42 ft. From tip to tip. The surface of the wing is slightly Fig. 128. The Antoinette monoplane used by Mr. Herbert Latham, curved, thick-sect form having been decided up and after numerous experiments with AVU toe determining the greatest sustaining power with the least resistance. Both surfaces of the wings are covered with fine varnished silk. Rear extremity of each wing are carried what are known as ailerons, or supplementary bearing surfaces, pivoted to the rear off the main wing with the objective assuring transverse stability when making turns or when flying in a wind. In their normal position, the ailerons area prolongation off the main wing surface. They are connected together, and by means of a suitable lever can be made to occupy a position perpendicular to the wings, one of the ailerons being raised while the other is lowered. The same effects are procured with this system as with the flexing off the wing tips on the right type of aeroplane. On the Antoinette monoplanal rudders area rear. For the purpose of turning, the fin E, Fig. 129, is prolonged by another vertical plane pivoting round this ladder, and in the illustration shown slightly to the right, this being the position it would occupy when about to make a turn to the right. This vertical rudder H is duplicated by on the summit plane, but separated from it by the elevation rudder G, being a prolongation of the fin F. when in a horizontal position. The driver's position has been selected to maximum security. Small cockpit within the frame, and oval with the rear off-viewing tips. In case of accident, it would be necessary for the whole forepart of the apparatus to be demolished before the pilot could be reached. Toe is right and left, and mounted on a horizontal axis. The pilot has an ordinary type of motor car steering wheel. On the right controls there are horizontal plane forming the elevation rudder. Thus, if the wheel is turned ahead, the plane is lowered and the aeroplane descends. Similar wheel on the left controls the ailerons. 122. Fig. 129. Vertical and horizontal rudders of Antoinette machines, raising one and lowering the other, thus jiving lateral stability in winds and assisting in making turns. The vertical rudder at there are operated by a horizontal foot lever and connecting cables. The pilot has a smaller wheel mounted on the end of a horizontal shaft running forward, immediately in front of him, this controlling both the petrol pump, regulating the supply of fuel to the engine, and the position of the spark when running on accumulators. The engine, naturally an Antoinette, is carried in thebo off the apparatus, with its dual-bladed steel and aluminum propeller mounted direct on the forward end of the main shaft. The radiator for the engine only weighs 261 b, and a cooling surface of 130 square feet. It is composed of a number of long, fine-section aluminum tubes placed on the side of the boat-shaped hull. As shown at Rin Fig. 128, in which position the tubes receive a strong current off air while offering practical and assistance to advancement. Antoinette monoplane is mounted on a skate, with a couple of struts under the center O-fatch wing and a strut under the tail. The skate extends about 3 ft, a head-off apparatus in order to protect the engine from shock in case of a violent descent. It is connected to the body of the aeroplane with shock absorbers, one of them being placed exactly under the center of gravity and the other further forward. The Cody aeroplane. Cody aeroplane is the result of the designer's experience in kite work embodied in a design accepted lines. The Cody is a biplane, each plane being 52 ft, long and about 6 ft, 9 in, wide and presenting a sustaining surface of approximately 1000 ft. Super. The framework is largely tubular. Thetwo planes attached to each other by 12 uprights and covered with 123. Fig. 130. The Cody aeroplane on fans plane 1909. Rubber-proofed canvas era quite flat. Since it was first brought out, the Cody machine has undergone many changes. It had time off writing, it has just undergone some further alterations, and no haste the writing planes, horizontal at hurry instead off in front as formerly, while it also has writing planes, vertical 8 off the plane. Rudders are replaced both fore and aft. The power is provided by an 8-cylinder water-cooled Antoinette engine of 50 h.p. The radiator is composed of copper tubes. Ein engine of p. is to be installed as soon as possible. Howard Wright aeroplane. Both monoplanes and biplanes have come from Mr. Howard Wright, but it is with that Wodecker the experience has been gained by this designer. On his restricted flying ground at Fambridge, it machine has frequent life the ground in small area available. Two unique feature as distinguish the design. The tubular steel framing and that one propellor volving in opposite directions on the same shaft. The main surfaces off the machine present a lifting area of 520 sq.ft. The tail offering an author 100 sq.ft. with a 50 hp. 4-cylinder metallurgic motor running at 500 rpm, the soaring speed is 25 mph, and the flying speed 36 mph. A peculiar gearing which baffles description and at first deceives even the eye of that trained engineer. Vides the 3-to-1 speed reduction to the propellers and the reverse motion tune of them. Only 3 gear wheels are necessary, although a fourth is added for balance, and be a seemingly paradoxical movement 2/3 off the torqueways transmitted tune a screw and 1/3 off the torqueway to the other screw. With the same diameter for both propellers, the double thrust on is obtained by offer blades, each off the same area as either of the 2 blades off the second propeller. Elevation is obtained by means of a horizontal rudder in front. Lateral stability is governed by the ailerons, attached to theffer after corners off the main planes, theffer ailerons being simultaneously 124. Fig. 131. Mr. Howard T. Wright's aeroplane, Mr. Malcolm Kersamer pilot, controlled by a single movement on the part of the aviator. They have this distinction from other ailerons that they have as much upward as downward movement. The machine runs over the ground onto a wheelsonly, one under the aviator, the other under the tail. 2 grounding wheels are fitted under the extremities off the lower main planet to preserve the wings from damage. An advantage of this bicycle mounting is that the budding aviator learns to obtain lateral balance before leaving the ground, and is this at an advantage when he first rises in the air. The Blériot monoplane. Blériot Roman 12. Most recent of Louis Blériot's series of monoplane flying machines, appears to be the most successful of them all, for it has proved capable of carrying 2 passengers with ease. Thewings, which appear to measure 42 ft. Round-tip pan to about 6 ft. From front torier, the builder wishes to withhold thicksec dimensions at present have a considerable curve from front torier, have their angles widely rounded off, and are covered on both upper and lower faces with fine canvas. Below the main wingsuret was small horizontal planes attached to the lower frame members. At there are horizontal planes, and upper one fixed, mounted on hinges that thingly off inclination can varied as found necessary, and a lower one a little further to rear, pivotable at heel off the pilotform elevation rudder. Above the framework, and about 1/4 from there is a large lateral rudder, being a square with thingles rounded off. An addition made to the machine takes the form off a jib shape fin placed ahead off the lateral rudder, this having been found necessary to increase the lateral stability of the ability. 125, Ingenation 8-cylinder E.N.V. Mounted on a light steel chassis and attached to the lower frame members amid diatelian front off the apparatus. It drives Avery large diameter all-wood propeller, built by Chauvier, by means of a pinion on the engine shaft and single chain to the propeller shaft, the speed of the propeller being reduced to about 600 revolutions a minute. The pilot's seat is across the lower frame members, behind the engine and under thewings. This position M. Blériot declares that he is better protected than in any other, for in case of a fall it is the motor, which receives the shock and net the pilot. While being placed near the ground, heisable to make his descents with greater certainty than when mounted higher. The seat is of sufficient width to accommodate 2 persons, but it has been found that a passenger by the side off the pilot alters the center of gravity. Better results being obtainable with the passenger sitting on the frame a little ahead, off the pilotan facing him. Silver Dart. 11 Silver Dart was the first flying machine made by the Aerial Experimental Association. She was built adequate at little watering place called Badek on Bras d'Or Lakes, NS she is a biplane, the planes being bowed so that things converge towards one another. They are also arched, and are placed with the concave sides facing each other. Each plane is 6 ft, wide and covered with vulcanized silk. The planes are rigid, the exception of small triangular wings at the extremitips. At her rear is the rudder. The elevation is controlled by a horizontal rudder, 2 planes fixed in front. The power is obtained from an 8-cylinder cooled Curtiss engine, V-type, developing 50 HP. This drives 8-bladed wooden propeller by means offer V-leather belts. With Silver Dart J.A.D. McCurdy Haysqualled the feats of Farman and Blériot in flying across country. His best record in this respect is 20 miles. On that occasion, the course lay over us, across the town of Badek, over woods, etc. McCurdy, after this flight, stated that the no reason why 10 times the distance should not be accomplished soon. It was only a matter of getting every detail perfect. He also stated that texture off lifting weight was a problem they had solved. What they wanted no was a propeller that would give greater forward thrust. Short brothers. Besides the dozen machines which they are building in this country under the Wright bros, patents mess, short bros, of Battersea, London, and of Sheppey, Kent, are devoting attention to aeroplanes off their own design. At the Aero Show of 1909, the main framing off these machines was exhibited, but during the intervening period many alterations have been made in the details. Messrs. Short bros, Aeroport suing policy offerticents, and up to the time when this book has gone out of press, have asked us not to make public any information about their aeroplanes. 126. Aeroplane spars, rigging, and fittings. The structure of an airplane consists of 3 principal portions, in addition to the propelling machinery, and these 3 may be termed. 1. The struts or members of the framework which are under compression, torsion, or cross-strain. 2. The tension rods or wires, and 3. The material of which plane surfaces are made. In the case of first portion soft structure, aeroplane constructors might do worse than turn to the builders and designer soft light racing sailing boats and canoes. As in these little craft, piano wire stays and low spars have been brought to high state of perfection for some years. Probably, every possible variety of spar has been tried in these vessels at some time or other, from the original solid stick to the modern hollow spar, which has superseded everything else, next in value being the bamboo. For these kinds, the aneno in use consists of a piece of perfectly clean-grained Californian or Nova Scotian spruce, cute and half-length ways, and after the center has been scooped out, glued together again. The C-spars are only about 30%, off the facilid spur off the sawmill sizing material, yet they have about 75%, off the strength of the solid wood, thus showing a great advantage, of which more than counterbalances their high price. After Thetwo halves are glued together, they are screwed up between 2 planks by means of a series of cramps, as unless the glue is under great pressure, a good joint cannot be obtained. The 2 principal makers of hollow spars in this country are Messrs. G. Holwey and SRNS of Dublin, how are the first firm in Great Britain to take up the manufacture of hollow spars, and Messrs. A. Burgoyne of Kingston-on-Thames, who have made several hollow frames for the Clark aeroplane. Many people think that a bamboo is as light and strong as a hollow spar of the same size, but this is by no means the case. Accessories oft is carried out by Ussomiers ag-approved the hollow spar tobe 15%, lighter and nearly 20%, stiffer than a bamboo off the same length and diameter. In the larger spars, the difference in favor off the hollow spar is then more marked, as the shell can be kept thinner in proportion to the outer diameter. Steel tubes have often been tried in place off wooden spars, but the are not so good, being heavier for a given strength, and moreover they are prone to buckle and in. Wire stays. Quite as important as the wood frame is the wire used for the stays and the method of attaching it to the frame, as lightness and neatness are essential on the aeroplane. It is oft now set a fasten off things off the wire in such a manner that 124. They will slip or an any they way weaker than the rest of the wire. Before going further into the details of the fastenings, it will be well to consider the nature of the wire employed. This should be the best silver-plated piano wire, which may be between 50 ft. Coils of various gauges, no 26 is about 0.6 diameter or say 0.02 askew. In sectional area and as breaking strain ice over so all. The tensile strength is about 125 tons per. Askew in. Thenix size smaller has a breaking strain off about 5,201 B, and is quite strong enough for many of the lighter parts of the machine. The weight off the no 26 wire is approximately 2 lb per 100 yards, and the smaller size about ifl for the same length. This piano wire is no tacit to obtain off the best quality, and unless it is absolutely reliable, it is off now set of maker of aeroplanes. Although the wire is very stiff, it is not empered, but is merely drawn hard and not nailed. This makes the wire very strong without being brittle, and so soft is it that it can cut with any ordinary wire cutters without damaging the cutting edges. It can also be filed toe point with a fine file, but their own thing tobe carefully avoided, and that ishi tingitin anyway. For this reason, it must never be soldered, as that will greatly reduce its strength at the point where it is being heated. Nadition tobing izataka, this wire can bent flat upon itself and then straightened out tagging without breaking, and it can fig. 132. An ordinary twisted off twisted upus tightly aspicible round wire itself without difficulty or damage, but so flexible is it that, when under great strain, that twisted portion will pull out straight. Therefore, it is not a safe way to fasten the ends unless several turns are first taken round some fixed object. Fig. 132 shows an ordinary twisted iron-themed ofa piece fig. 133. Wire taken through athambol. Of piano wire which, although it is the simplest and lightest way of making ani, is, as I have just said, not trusted. Fig. 133 shows a somewhat similar eye, but in this Cassithu wire is taken round a light heart-shaped thimble, and when twisted it heened, solder is run in a twisted portion 128, and round the thimble with ablo pipe. This will prevent any possibility of the wire slipping, but it will also reduce the strength at that point, so neither of these two methods is tobe considered satisfactory. Figs. 134-138 show a simple form of which we have devised for this wire, and which we have found quite satisfactory after 2 years hard testing. The drawings show front and back view, section through the center of its length and plants off the top and bottom. It will a fig. 134. Rear view. Fig 135, front view. Fig 137, view from top. Fig 136, sectional view. Fig 138, view from bottom. The hope rigging eye. Be seen that theshu consists of a small stamping off steel or gunmetal with a flattened conical end through which the wire passes. Thyson taste wo holes off the same size as the wire, drilled at a small angle so that while the start side by side underneath. Fig 138, they both come out off on hole at head top. Fig 137. Another method in the smallest shoes when the aramade often metallist to drill a central hole and drift it out at head bottom tot with its width or a little more. The lower part of the shoe may have any shown in the foregoing figures, or it may be on off things off a rigging screw ass in fig. 139. In all cases, the method of attaching it of wire is the same, and can easily be understood from the illustrations. In the se figures ace the wire be the shoe with an e at lower end. This that apert hole in the upper part of the shoe, and sistined off the wire. A bent round up in itself and driven up in the tapared hole in the shoe. The method 129. Of fitting the shoe thined off the wire is as follows. The wire is passed down through the shoe from the small end or top. It is then bent slowly over until thined is turned back upon the main piece at a sharp angle, but before it is bent far in order to touch it, the point is filed off on the inside toe long bevel, so that, when the two parts are close together with the pliers, they form a reverse taper, which fits closely into the tapered hole in the shoe as in D. Fig. 135. The wire is full of filed and bent. It should jam tightly in the shoe, and the strain on the wire will then close it up tighter and cause it to grip the inside off the shoe end itself. It should be noted, however, that, although the wire is very kind, in bending, yet it is fairly hard steel, and if bent too suddenly may break and nip. One great advantage of this form of shoe is that it can be removed with the loss of only in. Off-wire. Civitas cut at head point, where it is doubled over only the short PCs wasted. The best method of tightening the wires is by use off the rigging screw, Fig. 139, or turnbuckle. As Fig. 139, a turnbuckle or rigging screw. It is called in America. It consists of a right and left-handed bow nut, the center of which is skewed away in a pair of screws, one with a right-handed thread and the other with a left-handed thread, fitting that ones off the nut as shown in the figure. One of these screws has in its outer and dash exactly the same in designates that already described and illustrated in Figs. 134-138, while the other end is fitted either with a knee shown or with a pair of shiklelugs as Fig. 140. A simple rigging screw made out of a short cycle spoke and nipple and two strips off metal may be most convenient. With a screw off this description, any degree of strain can be put on the wire, but great care must be taken in selecting the screws. A sunless they are of the very best quality. They are very apt to break it hind off thread. For this reason, it is always safest to have the screws nearly with the diameter of the piano wire, and the threads should be carefully examined, while nuts should be as long as possible. Screws of a size suitable for the fine wire required can be bought ready-made, and not out. As the demand for airplanes increases, both shoes and rigging screws will soon be obtainable as a stock article. 130. Covering materials for aeroplanes. Of the various kinds of materials used for covering the aeroplane softling machines, fine quality canvas, treated or untreated, is generally used. Several firms supply it covered on one or both sides with a refined coat of fine dia rubber. The material thus treated will weigh anything between 4 to 9 ounces per square yard. The joints are solutioned and sewn, making a waterproof joint. It is rather expensive, costing from 4 to 7 square yard. Santos Dumont Isu Singoiled Japanese silken his latest aeroplanes. This is naturally costly, but it is very light. Fine canvas covered with pegamoides like litobcum popular with some aeroplane builders. It has a smooth surface and is about the same weight as rubber-treated material, but considerable less in price, costing from is 6D to 3s a square yard. Unless canvas is treated with some damp-proof solution, it will be found to alter considerably with the other. Ordinary untreated aeroplane canvas will slacken to very noticeable extent during wet weather. Kept damp-proofing for canvas is boiled oil, which can be applied by an amateur with a large size paintbrush. This, of course, does not make such an smooth surface as rubber or pegamoid. The most difficult part of which covering material hastob attached is the underside or concave parafribs. The material is usually sewn on, but a simple way is Staus's special big-headed Nailson grips, which are being made specially for this purpose. Some experimenters use a paper backed with muslin, or then varnish the planes after the are made up. This method lends itself to easy repairing. Blériot has used a strong paper parchment for some office machines. A.V. Rowe has recently been using Akaton oil paper covered with muslin, weighing only 2 ounces per square yard. This can be bought prepared and is aptly damp and gluten, when drieth is a smooth, drum-like surface. I've experiments are like lidobe carried out in rainy weather, thed joints, or indeed. The whole surface should be covered with a thin coat of oak varnish, or boiled oil. This natural not the strongest canvas, but can be easily repaired with theod off the glue pot, and is a suitable and rich sheet covering material for beginners. Aluminium cloth woven with very fine threads of aluminium wire has recently been discussed, but with an aluminium sheets would be no heavier, and would have a very smooth surface. Another material of rather different construction is manufactured by Hutchinson, the French maker. It is made of finest grade Egyptian cotton, the outer diagonal being dyed yellow with chromate off-lead to protect the rubber proofing from the sun's rays. The material used by Farman, Voisin, Wright, in one instance, and others is made by the Continental Tire Co. 131 I2. Propellers. Of propeller sand propelling devices there is a great variety, each the object of the supreme belief of its inventor. Some have reached the experimental stage, others have not got this far, but up to the present time it has generally been found that some type of screw propeller is most suitable for practical work. The aerial screw propeller differs little in its action from its marine prototype, each depending for its action on the part in sternward velocity o column, in the case, off air and in the other off water. When the propeller screws itself forward, the air slips past the blades, so that the propeller does not move forward so quickly as if there were no slip. The distance moved forward every revolution off the propeller if Fig. 141, there were tobna slip is called the pitch. Thus in Fig. 141, neglecting slip a point on the propeller bladder tip, instead of merely revolving in circle BCDE, fall so advances the pitch distance AB. The resultant path which the tip actually takes is therefore BGHKL. The pitch multiplied by the number of revolutions per minute is the distance moved forward per minute. This will be the speed off the machine if there were tabino slip. If slip better can in toe count, speed off machine inft per min equals pitch FT. X revs per min, slip FT per min. The slip velocity is that which is imparted to the column of air upon which the propeller acts. The thrust that is obtained from thiction off this column offer is qualto weight off mas offer acted upon per second x slip velocity, ft, per sec. In the case of a stationary propeller there is no forward movement, so that there is an little slip velocity to consider, which is then much greater. At first it would appear that the thrust at starting would be much greater than when the propeller is traveling through the air, owing to the slip velocity being so much greater. It is found experimentally that this is not the case. In Sir Hiram Maxim's experiments, the thrust with propeller traveling at 40 miles per hour was the same as that when the propeller was stationary, their revolutions per minute off the propeller remaining constant throughout. The reason for this is that, although the slip velocity is decreased, the propeller acts upon undisturbed virgin air, the equivalent of acting up an aggregator quantity of air. 132. Wright claims area of an advanced astotha thrust per p that can be obtained with a given propeller. This quantity the thrust per p cannot exceed a certain figure for a given pitch and number of revs per min, as the following will show the thrust multiplied by the number of revs per min, and b the pitch gives the work done per minute. This figure divided by 33,000 gives the p required to do the work or thrust xr, pm x pitch hp equals 337,060. The maximum value of the thrust per p for a given number of revs per minute and pitch in feet is the ref or 6 L alt 0 thrust 33. 000 HP, pitch XR PM. If the propeller is a good one, the thrust per P will almost coincide with the amount calculated from the right-hand side of the equation above. This holds good for a stationary propeller, but if the propeller travels through the thrust that will be obtained is H, P, X 33,000's efficiency of propeller speed off machine, FT, per sec. The whole blade off the propeller has to move forward the same amount. Apart's nerthebos will the shave tobe set at a stepper angle, since the distance they move through circumferential useless. Fig. 142 shows this more clearly. The outside tip A off the propeller moves round a circumference equal to 2 of x reverie revolution. At a point on the blade where the radius is the distance moved through per revolution is 2r. In both cases the point A or B must advance at distance equal to the pitch. Thus in Fig. 3. Own B or at the distances 2 *r and 2 TTR respectively through which the parts revolve, and both move forward the same distance OC. The outside point A moves along AC, but the point B moves along a steeper path BC. By setting off points E, F, G, Fig. 143, corresponding to the circumference says through which the points at E, F, and G, Fig. 142, move thingles at which the parts off the blade at E, F, and G must be set or obtained. Fig. 142, Fig. 143. 133. Determine with accuracy the thrust that a propeller will give in the P. That it will absorb requires a great amount of experimental work. Maxim tested his screws when stationary by mounting them on a shaft driven by built from a steam engine. The shaft was free to move in its bearings and tune end off the shaft was fixed a spring balance, measuring the Fig. 144. Capt Ferber's road carriage for testing the values of propellers. Thrust due to the propeller when revolve. Oats them when moving through the air. The screws were mounted at hind off a long arm, and the latter was rotated. By various ingenious means, he measured the thrust when moving at a given speed through the air and at a given number of revolutions. Captain Ferber carried out tasseries off disc on propellers by making them drive a small chassis. This arrangement ran along the road under its own power, and various measurements of thrust and power were made. 4 helicopters where vertical screws arrows. The pitch is made small and the diameter large. There is then a large column offer acted upon and a low velocity imparted to it. From a consideration of the equations given above, it will be seen that Thyssenger's a larger thrust per P. 134. Aerial motors. From the earliest stages of the flying movement, it has been recognized that a power-producing plant of flower weight per horsepower than anything employed for land or marine travel must be procured for successful navigation of air. Long before the petrol engine was sufficiently developed at Toboff service, special lightweight steam engines were constructed for early flying machines. 2 important examples of their use being on Langley model airplane, probably the first power-driven, heavier-than-air machine to leave the ground, and in the Adur and Maxim, the first man carrying aeroplanes to accomplish flight. But the petrol engine offered distinct advantages over the steam engine of Russian airplanes, and during the active period from 1904 to the present day, has been used almost exclusively. French engineers, in particular, recognized that, for flying to successfully develop the petrol engine, as used on motor cars, must be made lighter, and generally more reliable. Thus, in France, experimental work in lightweight petrol engines is being carried on concurrently with researches in the best form of sustaining surfaces and methods of securing equilibrium. Until at present, there are at least a dozen successful aeroplane engines, all of the internal combustion four-cycle type, but differing considerably from their predecessors built for Russian motor cars. Now, certain aeronauts maintain that thesearch for featherweight and genesis labor lost. That flights can be made with annual constructed Kerngen. Facts, however, array against this theory. For all flights, up to the present, have been accomplished by special engines. Even the Wright motor, the Anuhich most closely approximates the car type engine, being specially lightened and distinctive in low weight per horsepower is undoubted Liniton lightseer able, but essential for driving an aeroplane. Smoothness of running, reliability and regularity are equally important, and it remains to be seen whether the newer lightweight engines, with 6, 7, 8 or 13 cylinders, can be made as satisfactory in this respect as the standard Buthavier type of engine with only 4 cylinders. The Walsally engine. The Walsally Co. has taken up the construction of light engines for aerial work. The firm has reduced the weight of its new type to 81 per horsepower. This figure being inclusive of flywheel, ignition, water pipes, gas pipes, etc. Everything necessary to running off the motor being weighed. Although there are many lighter engines, the Walsally Co. has 135, big 145. The Walsally aerial engine. Not being led to reduce wholly the several working limits, its principal consideration being to produce a motor that can relied upon to work for long periods at full load without breaking down. The cylinders are set V fashion, 4 on either side off the crankcase at 90 degrees to each other. The cylinders are cast in pairs, with jackets and liners in one piece, the metal being close-grained cast iron ground to gauge, the bore being 3 fin, and the stroke 5 in. Sheet aluminium is employed for the order jackets, which are screwed to the cylinder castings. This method of construction allows the thickness of the metal to be uniform throughout and offers advantage in the matter of cooling. The pairs of cylinders are staggered in relation to each other, the 2 connecting rods throwing on the Salme crankpin and the bigens being off, 136. Fig 146. The Walsally aerial engine seen from above. Phosphor bronze white metal lined. 3 large bearings are provided for the crankshaft, and the lubrication ice-affected under pressure to the main bearings and connecting rods. All the valves are side by side facing the center and are operated by a central camshaft, lifting shoes being interposed between thecams and tappets. Exhaust and induction pipping is therefore situated between the cylinders over the top of the crankcase, the carburetor being mounted in the center. Thermosiphon cooling has been adopted. For the ignition, their isonate cylinder high-tension magneto running at crankshaft speed, a separate distributor being fitted and driven off the camshaft. One of the many good features of the engine is that the position of the carburetor enables asymmetrical induction system to obtain. The distribution of gas to the cylinders being uniform. The Gobron engine. Within each cylinder of the Gobron engineered pistons, the upper one having its head turned downwards and connected up to an overhead beam, which in turn is connected to the main shaft of the engine. Instead of the explosion taking place between the piston and the cylinder head, it occurs between the heads of the pistons, which command their on the compression and exhaust strokes and leave one another, one ascending and the other descending, on the intake and power strokes. The principle will be understood by reference to Fig. 147. On the aeronautical engine there are 8 cylinders and consequently 16 pistons. Instead of being mounted vertically in the crankcase, as in the car engine, the cylinders form an X. 137. Engine may be regarded as Satwin double opposed motor, the pair of cylinders on the upper left-hand side being opposed to the pair on the lower right-hand side, while the pair on the upper right-hand side are opposed to the pair on the lower left-hand side. There is obviously a great saving off weight with this design. Fourth even torque off the 8 cylinders allows the flywheel to be dispensed with. The crankcase is a remarkably light organ, and the crankshaft for the 8 cylinders is off practically the same design as for the Gobron 2-cylinder engine. As all their reciprocating parts are opposed, there is an absence of shock and dangerous off running specially desirable for flying machine work. The cylinders are cast separately, are turned inside and out, and are fitted with copper jackets for the circulation of cooling water. The bore is 3 in, and the total stroke 6 in. This comparatively long stroke in relation to bore is only made possible by reason of the double piston principle. The valve mechanism is remarkably free from complications. The inlet valves are automatic, while the exhaust valves are operated without use of any gearing. The only gearing employed on the engine is that for driving Thetwo high-tension, magnetoscurry 12 and right-off, rear extension off crank. The same gearing is also employed for driving the lubricating pump. Naturally, the tendency of the oil is to send to the lowest point of 4 cylinders with their heads downwards. The pump, Fig. 147, the Gobron aerial engine. A crankshaft, B connecting rods 4 outer pistons, C connecting rods 4 inner pistons, F inner pistons, 7 overhead beam attached 2 outer pistons, raw combustion space. 138. Therefore, ice employed to carry the oil from this point to heads off the cylinders that are upwards and to the bearings off the main shaft, thus establishing a complete circulation. Complete weight off Gobron engine is about 4,401 B, At 200 revolutions a minute Thingen develops so. P. Butane being accelerated to 800 revolutions will furnish 90 h.p. A need for lightness of details led to the development of multiple cylinder engines, the cylinder soft which radiated from a central circular crankcase, and the piston soft which were all connected up to a point. This type of engine has almost invariably 7 cylinders, for it is only with any number of cylinders that the explosions can be obtained 8 qualities chances. This can be best explained by means of a diagram of Fig. 148. Why 7 cylinders make a smooth-running engine. 6 and 7-cylinder star engine. In Fig. 148, the explosions take place in their natural sequence from cylinder 1 to 6. This, of course, would give us explosions per revolution of Thingen shaft and further equal distances, but for a whole revolution no power would be developed. The next method appears to fire alternate cylinders, but this would be no better for us followed out in Fig. 148b. The distance between 1, 3, 5 would be shorter than the interval between cylinder 5 and 2, while there would be a very short interval between cylinder 6 and 1. With a 7-cylinder engine, these difficulties disappear, for it is necessary to fire own alternate cylinders 1, 3, 5, 7, 2, 4, 6, to have the explosions equal distances. This is shown clearly in Fig. 148c. An engine of this type having 3 power strokes per revolution, or 7 for every 2 revolutions off the main shaft. The REP engine. The first successful engine produced on this principle was REP, named after its inventor Robert S. Noel Peltery. Although, for special reasons, the inventor of REP has * preferred to mount the cylinders on the proportion of crankcase only, the method of operation does not differ from those engines having the cylinders placed 8 equal intervals around the periphery of the crankcase. It being impossible to 139. At such a large number of cylinders on the upper half of a circular base of moderate dimensions, the designer has slightly staggered them, 4 being in an plane and the 3 others slightly in the rear end in another plane. For such an engine, the crankshaft Fig. 149. JFCV must have 2 main gel M arms or throws connecting fa to Q and E off with the connecting rods off or pistons will be Fig. 150. The piston and gudgeon pin bearing attached, and to the other will be linked up the 3 remaining pistons. As is shown in Fig. 149, their isone main connect ingrid receiving 3 separate rods, 2 being on an side and only on an other. The circular crankcase is an aluminium casting to which the cast iron cylinder seriatch secured by 3 bolts, nuts, and lock nuts. Very light steel pistons are employed. Uals being south and that it would be impossible to attach the gudgeon pin in the usual manner by bearing synth off the piston. The central portion of the head off the piston is, therefore, threaded to receive a special bearing. This piece, shown in Fig. 150, is screwed into the head off the piston, being prevented from turning by means of a countersunk screw, and carries, integral with it, the 2 bearings for the gudgeon pin. On the REP engine, there is butane valve for both the intake off the fresh charge and for the exhaust off the gases. It is carried in the head, and isoprate in a special manner by an overhead rocker arm. The manner in which Thetwo functions at fulfilled by an organ is both simple and effective. The rocker arm, operated by the camshaft, can maintain the valve in 3 distinct positions. On full opening, the valve is lifted off its seat in the usual manner, allowing the aspiration of explosive mixture. In another position, a steel collar surrounding the valve stem uncovers a number of holes within a cylindrical cage, thus giving communication between the pipes and the combustion chamber and allowing the spent gas to be driven out. In its third position, these holes are closed and the valve face is resting on its C-ating, thus a tingle connection with both inlet and exhaust pipes. The valves are operated by a single cam, or, more correctly, by a single disc, the face off which has 3 pairs of bosses, the 3 larger ones corresponding to the lift off the valve for intake and the 3 smaller ones to the lift for the exhaust. The 7-cylinder REP engine has a bore of 3 sin and a stroke of 3.5 in. It is rated at 30 HP, at 500 revolutions a minute and weighs complete ready for running 1151 B. The Gnome engine. The 7-cylinder soft Gnome aeronautical engine irradiate from a circular crankcase. Unlike the standard type of engine, on which the cylinders are stationary and the crankshaft is driven round by reason of the power strokes on the piston, the Gnome engine has a fixed crankshaft, with cylinders and crankcase revolving round it. With such a type of engine, air cooling Fig. 151. The 7-cylindered Gnome engine. 141. Is naturally employed for the speed off the cylinders through the resample for dissipating the excess of heat. Practically every portion of the Gnome engine is machined out of nickel steel. The cylinders, for instance, are produced from a solid bar of steel, machined to the required shape, with their radiating fins, then burned out until fuels are ever much thinner than would be possible with a cast iron cylinder, and yet possess even greater strength. They are mounted around the circumference of the circular crankcase. The axis of the wheel thus formed is the crankshaft, having gasingle crank, or throw, secured in bearings in center off that wound plates, or hub caps, bolted to the face off the hub. If each off the pistons is connected up to the single crank pin off the crank shaft, it is obvious that, on the heel being revolved, the pistons will ascend and send. In their cylinder just the same manner, as on the standard. Type often, Jinuher, the crankshaft revolves and the cylinders remain stationary. The head O-fetch cylinderized NX hose valve, operated by a rocker arm. Instead of being in the head off the cylinder, the intake valve is in the head off the piston, the charge passing from the crankcase to the combustion chamber, barab of the piston. The carburetor Fig. 152. I piston, which may be of any ordinary type, is main connecting rod and carried on the outside off inlet valve off the no mixture obtained from it passing through the hollow crankshaft into the crankcase, and from there, as explained, into the cylinders. Lubrication is suitably provided for. One of the most interesting features of the homogeneous the method of attachment of the 7 connecting rods to the single crankpin. Their ISO main connecting rod, its lower end terminating it wo steel discs, through the center of which the crank pin is pissed, and around it being 6 holes in each of thetwo discs torsive thenes off what are known as the secondary connecting rods. Within the hollow face O-fetch disc is mounted a large ball bearing carrying gall the connecting rods on the crankshaft. The gudgeon pin for each connecting rod is carried in a separate piece screwed into the head off the piston. Thingen, which is rated at 50 HP, has a bore of 4 sin, and a stroke of 4/7 in, the total weight being 1,651 b. 142. A yard Clement. In principle, there is a similarity between the Gnome air-cooled rotary engine and the 7-cylinder water-cooled engine produced at Heb Bayard Clement factory. This latter has 7 cylinders radiating from a circular crankcase, thexes off the cylinders being placed horizontally, with thexes off the crankshaft vertical. Here the cylinders are fixed, the explosions Fig. 153. One off the cylinders and the valve Garofa Bayard Clement engine. Driving round the crankshaft, as on the standard type of engine. Water cooling guys employed, the water circulating through a copper jacket surrounding the cylinder walls. The cylinders, which are off steel, are bolted to their seating in the usual way, and have a bore of 3/9 in, and a stroke of 4/4 in, the power developed being 50 HP. Each cylinder has a spirit dome-shaped head screwed in top position and then brazed. The combused tion chamber is hemispherical, this form giving the greatest efficiency, there being no pockets in tow which the gas can become lodged, and but small loss from radiation. There are separate intake and exhaust valves in the head off the cylinder, that being operated by a single rocker arm with blade springs, with off-course butone horizontal tappet rod. One position off beam opens the inlet valve, while the opposite position operates the exhaust. In the proportion off the crankcase area housed the valve operating mechanism and all the timing gear. It is within this casing that is lodged the central cam, receiving its movement from an intermediate gear and turning 8 times slower than the main shaft. The single cam carries 4 bosses and 4 hollows, corresponding to the position off the rocker arm for the exhaust and the inlet. Explosions take place in alternate cylinders 8-hatch revolution, there being consequently 3 explosions per revolution off the engine, or 7 explosions 4 revolutions. The commutator is mounted on a vertical spindle and driven off the main shaft, as if the speed off this ladder. The carburetor is carried at head base off the engine, outside the crank chamber, but feeding its mixture into a receiver within. 143. Case from which the intake pipes lead to the different cylinders. The carburetor waistslip. The vertical crankshaft in 2 parts bolted together and carried on ball bearings has a single crankpin tow hitch 7 connecting rods area attached. There are no flywheels either internally or externally. Thexis off the main shaft being vertical, it is necessary for aeroplane work to drive through bevelgering to the horizontal propeller shaft. This movement is obtained by a pinion on the extremity off the main shaft meshing with a vertical crown gear wheel on the propeller shaft, the latter being geared down in the proportion 1:5. Pipe. Avery Light engine has been produced by Pipe Co. This engine, which develops 50 HP at 200 RPM and a maximum of 70 HP at 950 RPM, has 8 cylinders off 100 mm, bore be 100 mm, stroke. The cylinders are mounted V fashion and Fig. 154. The 8-cylinder pipe engine elevation. Staggered in the usual manner off the aero-engines, but from this point the designates quite a departure. For the trunks of each pair of cylinders there is a light metal hood, a single long hood extending over the combustion, head and valve, chambers one each side off the crankcase. These hoods form jackets through which not water but air is circulated by a blower mounted on an end off the crankshaft. The exhaust and inlet valves are united in one detachable piece set concentrically in the hemispherical combustion dome. They are set in the cylinders at an angle of 45 degrees to the cylinder axis, and are therefore vertical. They are operated by overhead rockers worked off a single centrally enclosed camshaft, which runs in ball bearings. The carburetor is placed between the 2 rows of cylinders and is entirely automatic in action. It delivers 144. The gas and Tothefer pipes are stad fashion, each branch leading tow pair off inlet valve chambers. High-tension magneto ice employed for ignition. The Farcot, Lilienthal engine with multiple cylinders radiating from a circular crankcase is Farco-tight cylinder air-cooled motor. Fig. 156. The feature off thighs is that the cylinders are alternately staggered on the crankcase, 4 off them being in one plane and 4 in another. The vertical crankshaft has 2 pins placed at 180 degrees in relation one to the other. One throw receiving galthaconic tingrods off the cylinders in the upper plane, and the other those off the cylinders in the lower plane. The method of firing the cylinders: first, all 4 cylinders in one plane, alternate cylinders being fired until the circle is completed, then the 4 cylinders on the opposite plane in the same order. The cooling off the engine is assured by a powerful fan mounted on the extremity of the vertical shaft, and throwing a strong current off air onto the cylinders. Power is transmitted from the vertical shaft to the horizontal propeller shaft, through bevel gearing contained within an extension of the crankcase housing. One of the distinctive features of Farcot engine is a valve performing the functions of both intake and exhaust. The valve is carried in an outstanding pocket, as in the standard type of Kerngen, with this difference, however, that here the valve stem is horizontal. A cam off special profiler raises the valve to Fig. 155. In view of the cylinder pipe engine, C 145, 8 Fig 156. \% the cylinder Farcot engine showing firing order. 2 distinct open positions, in the lower one of which the host ice opened and in the higher the intake ice fected. This is shown distinctly in Fig. 157. The completed weight off engine is declared Tobe 1251B. This is for the 50 HP engine with a bore of 4 in and a stroke of 7 in, delivering its full power at 1/600 revolutions a minute. Exhaust, inlet, Fig. 157. The Farcot valve mechanism * 146. Vivinus. In the Vivinus engine, a great feature has been made of accessibility. In Themane, the design follows that which has been used for many years in the firm's productions. Butalot off metal has been saved, and through it has been reduced to about SLB per horsepower. All the exhaust and induction piping, which ison on a side off the engine only issued biffer boxes. The camshaft is an small box outside the crank chamber, and can be removed by removing 6 screws. An equally easy manner the camshaft can be drawn through on and without touching any part of the engine. The base chamber isone barrel, the front cover being in piece with box covering the gears. Thermosiphon cooling guys employed in high-tension magneto ignition. The tappet guides are held down by dogs and can be very quickly removed. The Wright bros. There is very little departure from standard practice in the Wright aeronautical motor. It has 4 separately cast cylinders of 4 in, boring 3, 9 in, stroke fitted with separate water Fig. 158, the Wright bros engine. Jackets and mounted on an aluminium crankcase. All valves are in the head, the exhausts B. Fig. 158, being mechanically operate B simple vertical spindle and rocker arm, and the inlets, A being automatic. The only really distinctive feature about 147 E2. Ingenes that there isn't a carburetor. The petrol being pleed by direct injection by means off a pump on the right-hand side off the engine, worked through worm gear off the camshaft and be a short shaft across the interior off the crankcase. On same side off the Ingenes lubricating oil pump, also worked off the camshaft through worm gear and be a short shaft across the crankcase. The base, C, off the crankcase forms a oil reservoir, from which the lubricant is pumped up to the main bearings and drips down into the reservoir through pipe D, being filtered on the way. Ignition off the Ingenes by means off a high-tension isemen magneto, carried on a platform near the base off the crankcase, and worked off the forward end of the camshaft. The water for cooling the Ingenes circulated by a rotary pump E, mounted on the forward end of the main shaft. The radiator consists of a series off-plane, flat copper tubes attached to off stanchions off the aeroplane. The petrol tank is a cylindrical vessel carried in a vertical position and also secured to the stanchions. Engine has free exhaust and has also auxiliary exhaust ports at the end of the stroke. The Antoinette engine. The most generally employed Antoinette engine has 8 cylinders, though larger models Ariel saw made with, respectively, 16 and 32 cylinders. The aluminium crankcase, having the form of rectangular prism, receives 2 rows off cylinders on each of its faces inclined at 45 degrees. Angle between the 2 rows off cylinders, this being one off 90 degrees. On the earlier models, the cylinders were cast separately, had separate heads, and were copper jacketed. The 1909 models have been entirely changed in this respect, the cylinders being off steel, in one piece with their heads and valve pockets. The Mechen in Goff's Chapis really a work of a metallic sculpture, the justification for which is found in the decreased weight, 110 less than LLB, having been gained 1 each cylinder, or a total off more than 121 B, over the entire engine. The main shaft off the engine has 4 throws and is carried in 5 bearings. The 2 rows off cylinders are slightly offset in relation one to the other, thus allowing that we're connecting rods off opposed cylinder stobe connected up to the somac crank pin. The camshaft is carried above the main shaft and driven directly off this ladder, the valves being side by side and in pockets in thingle formed by that rows off cylinders. One of the distinctive features off Antoinette engine is the absence of a carburetor, the petrol being supplied by direct injection. I means off a jar-driven pump. A supply off petrol is fed towage off the distributors at head off the 8 cylinders, where it is stirred until thane take stroke. Thane take valve is automatic, and on its opening, the petrol is drawn out off its lodging place, finally sprayed and mixed with Aerostatics carried into the cylinder. The petrol pump has a variable stroke, thus allowing more or less fuel being fed to distributors according to the speed required. There is little if any saving in weight by direct injection. For in place sofa C148, carburetor a pump special piping, and distributors have tobe employed, but advantage claimed for the system is more reliable carburation under all conditions. Lubrication off the motor is assured by a jar-driven pump. The propeller, which is built up with forged steel blades, is generally mounted on the forward extension off the main shaft. The green engine. The green motor patents syndicate of 55 Berners Street W. Produced a special engine for airplane work. The design is not new, an engine off this pattern having been constructed 7 years ago, and the fact that it is now being constructed by the Astor Engineering Co. vouches for its quality. The reduction in weight has been affected by the employment of pressed copper water jackets, overhead valve gear, and sheet metal bottom to the crank chamber. One advantage of using detachable water jackets is, of course, that the cylinders can be machined inside and out of uniform thickness. Water jacket joint is made with aerobearing, which after a few runs on the bench, subject to the heat off the water, becomes partly vulcanized, remaining soft only at contact with the copper. The inlet and exhaust valves are set in cage in head off the combustion chamber, and provision is made to prevent a valve dropping into the cylinder should it break. The overhead camshaft is made in one piece, but the cam boxes are swing-backed insets offer, excess valves. The rockers actuating the valves have rollers at nearance running on the face off the cams, and each is contained in its own oil-tight case. Forced feed lubrication is employed, and ignition is high-tension magneto. A feature off the mounting off the cylinder is that the holding down bolts pass through pillar synth crankcase casting, and some off these bolts are used for the main bearings, which are a 5 number. This enables the crank chamber tobe closed underneath by a metal tray. The engine shown is a 4-cylinder Go P, developing its power at 000 RPM, and weighing 2,351 b, only including piping, carburetor, etc., but excluding flywheel. A bigger engine off the same general design with 8 cylinder set V fashion is set in baby, the War Office dirigible off 1909. New Engine Motor Co. Thingen made by New Engine Co. Limited. Satwo stroke motor that differs from others off its kind in that special scavenging arrangements are provided. 8 stroke an enormous volume off air is swept through the cylinders. So that, besides driving out all products off combustion, enough cooling effect is produced in the pistons and cylinder walls to render any external water or air cooling superfluous. To attain this end, some departures from ordinary practice are, of course, necessary. The exhaust port is very high up. In fact, it opens halfway down the stroke, and the inlet is just below it. Both ports are exceptionally large, and often driven off the engine, forces a large volume off air through from inlet to exhaust. 149. Early scavenging and at Hassam at time cooling. This action continues during the rest off the down stroke and for part off the stroke, but before the inlet valve is closed, a very rich mixture is introduced, which mixing with the already in the cylinder forms agas off the right strength, which is compressed and fired in the ordinary way. The compression used equals 801 b per square inch. To introduce the rich mixture, a pump is required working at slightly higher pressure. The scavenging fan and there is a distributing arrangement in the induction piping. The bore off the engine exhibited last week is 4 in, stroke 4 in, and 40 HP. Is developed at 500 RPM. A feature of this very interesting motor is high speed at which it can run. These features combined naturally make it possible to obtain a high power for a given cylinder capacity, and it is stated that for a given size, 1/3 more power can be developed than is obtained from any ordinary 4-stroke engine. The ENV engine. The ENV engine is a French production from English signs, having 8 cylinders off 3, 9 in. Borbies Lin stroke set at an angle off 90 degrees tuning author. The cylinders are cast separately without water jackets, are machined inside and out, and provided with copper water jackets, which are neither riveted nor held with adjunct ring, assist the usual method, but are a thorough result of flectro deposition. This method of construction allows off-cylinder off accurately the same weight and fig. 159. The ENV engine. 150. Thickness off wool. While the system off depositalos thecapar tobes a closely jointed the cast iron off the cylinder that itis, impossible to say where the copper leaves often the cast iron begins. The enlitis advantagathat can be brought against it is that off increased cost. All valves are carried in thingle formed by thetwo lines off cylinders, and are operated by a single camshaft, machined out off the solid antilode for lubrication purposes. A distinctive feature off the camshaft is that it is slidable in a longitudinal direction at heel off the operator, thus varying the lift off the valves. The crankshaft is a fine piece of workmanship, with 4 throws and circular webs which have the effect of aiding the flywheel action. The shaft is mounted in plain bearings of exceptional length, while the crank pins are off the same diameter as the bearings, each owner receiving 2 connecting rods side by side. The Duthale-Chalmers aeronautical engine is aerial horizontal, and constructed with 2, 4, 6 or more pairs of cylinders, the most commonly employed types, however, having respectively 2 and 4 cylinders. Were specially lightweightest sired, thinginus air-cooled, but for all the larger 4-cylinder engine water cooling guys employed. The cylinders are opposed and slightly offset in relation one to the other tolo the connecting rods, tobe attached to different pins off the crankshaft. There is every complete circulation off water around the cylinder head, the part that most needs cooling. The inlet valve on this model is automatic, though we understand that a special model is no being constructed with mechanically operate inlet in conjunction with the exhaust. The exhaust valve is operated by overhead rocker arm and is placed immediately in the head off the cylinder. The valve is guided for a considerable length and allows the gas to exhaust free in the air. A baffle plate is, however, fitted to prevent hot gases coming in contact with the valve spring. The camshaft is carried above the crankshaft and parallel to it, there being butone cam fortwu valves. The high-tension magnetoise generale carried on the upper portion off the crankcase and is carried off the camshaft. Double ignition is provided by accumulators and coil, and every ingenious system is adopted on these motors, by which spark plugs can be changed while the engine is running. The device consists of a movable plate carrying for plugs, to receiving their current from the magneto and to from the accumulators. By turning the plate round, any on-off the plugs can be brought into communication with the combustion chamber. All the engine have a bore of 125 mm and a stroke of 120 mm, the normal engine speed being 200 revolutions per minute. The cylinder engine weighs 1,651 b and gives 20 HP. The 4-cylinder engine weighs 2,641 b and develops 40 HP, while the 6-cylinder model develops p for a total weight of 3,751 b. 151. Aero Motors Limited. The Aero Motors Limited, which is under the guiding power of Mr. F.R. Sims ha brought the original Daimler engine at this country, has produced a 6-cylinder engine which develops 50 HP, ATL 000 RP9, weighing only 2,201 b. This weight being exclusive off the flywheel and exhaust piping, but including water and induction piping, magneto, etc. Cylinders are set at 120 degrees to each other, on opposite sides of the crankcase, and slightly staggered, in order to bring 2 bidgens 1-inch crank throw. They are 110 mm, bore be 110 mm, stroke and are cast separately with superimposed valves in a pocket facing the center. All the valves operate from a single central camshaft on the top of the crankcase, the exhaust valves being operated by a direct push, lifting shoes being fitted between the cams and tappets. The inlet valves open automatically, but are closed mechanically by a spring-rotated rocker arm on top of the engine. Permit the valve to open. This rocker arm is drawn down by a tension rod operated by able crank fitted on a spindle above the camshaft. One end off the rocking lever carries a shoe which runs over the face off the cam. Gas is uplead from a carburetor situate centrally above the engine, and delivering the mixture through 2 branches toe pipe along the topo-fatch set-off cylinders. Forced feed lubrication is employed for the main bearings and bidgens. For the gear wheels, gray fiber is used. With magnolia cheeks, the magneto is mounted on a bracket above the cranks at a forward end. A rather neat fitting is used to secure the 2 side plates off the mixture chamber on which the air and mixture throttles are mounted. The fastening is a simple blade spring attached to the main pipe pressing on the center off the plates, which can, of course, then be quickly detached. The Renault. Air cooling is employed on the Renault 8-cylinder aeronautical engine. The cylinders, which have a bore of 90 and a stroke of 120 mm, are mounted in the form OFA, V, on an aluminium crankcase. Thetwo lines off cylinders are slightly offset, these allowing 2 connecting rods tobe attached side by side on a single throw off the crankshaft. The main shaft is mounted on FV bearings. All the valves are worked off a single camshaft, the inlets being in outstanding pockets within thingle formed by 2 lines off cylinders, and exhausts immediately above them are operated by rocker arms. The arrangement off the carburet Tarrant inlet piping is somewhat original. The flow chamber and nozzle are carried quite in the outside off the engine and very low down, the top of the carburetor being oneilval with the base off the cylinders. This is being done in order to make it possible to place the tank in a convenient position to feed by gravity, instead of by pressure, assist done on most aeroplanes. Probably the most distinctive feature of the engine is that the propeller is mounted on the extremity of the camshaft, and not 152 on the main shaft. It is no generally recognized that greater efficiency is obtained from a propeller turning at 600 to 900 revolutions a minute than from owner running at 200 to 800 revolutions a minute. A suitable reducing gear has been difficult to find, and it needed the daring for Wright to adopt the somewhat clumsy transmission by chain. On the Renault engine and reducing gear is required. The crankshaft and aft the speed off the main shaft, having 900 revolutions per minute off the propeller with the engine running at full speed. The camshaft is specially constructed for Thurk ithostoper form and is mounted on ball bearings. The engine is enclosed by a light aluminum housing at both ends and on theta, and even the small amount of space between the cylinders has been closed up by aluminum plates. Fig. 160. The 8-cylinder air-cooled Renault engine, at her rear off the engine and mounted on the end off the main shaft, is a powerful centrifugal ventilator, also partially housed, which draws a strong current off air into the V-shaped space formed by the cylinders. Everything being closed up, the only possible escape for the air is between the fins of the cylinders, with the result that these latter are kept at a normal temperature. Ignition is by high-tension magneto, which is carried within the angle formed by the cylinders. Lubrication is assured by pump circulation, the supply of oil being carried in a reservoir forming the extreme base off the crank chamber and delivered under pressure to the main bearings of the engine. Under brake test, the engine gives 55 HP. At 800 revolutions and in full running order, but with tanks empty weighs 3,751 b. 153. Light ignition apparatus. For special requirements, it is possible to produce ignition system components much below Th8 standard employed for cars. Although it is improbable that the coil and accumulator system of ignition will become a standard part of aerial engines equipment, as the high-tension magneto is in every way better suited, it may be stated that inefficient trembler coil can be made LLB in weight only, whereas the ordinary patterns weigh from 41 b up to, in extreme cases, 81 b. For a multiple-cylinder engine, a high-tension distributor and contact tow work in conjunction with the specially light coil would not weigh more than lib. The minimum weightina coil is only obtainable by use of materials of the highest quality. The soft iron wire core, the insulating material, and the copper wire for the primary and secondary winding shave tobe specially considered. The core is tobe most carefully annealed and kept to the smallest proportions, compatible with obtaining sufficient magnetized effect. Insulating material is paraffin silk. This also forms the insulation for the copper wire. On ordinary coils, cotton insulation is largely used, which takes up more space and necessitates a greater weight of wire being used to obtain a good spark. The use of the fine possible gauge wire for the secondary coil is an important factor in making a light coil. On ordinary coils, NAS 36 or 38 gauges commonly used, whereas 42 or 44 gauges required for the light coil. Such wire necessitates extremely careful handling to avoid breakage in the course of winding it. But acetinables every larger number of turns tobe made with a given length and weight of wire, and upon this largely depends the strength of the spark from the coil, and the difficulties amply compensate for. The condenser in the ordinary coil accounts for a good proportion of the tinfoil interleaved with paraffin paper is used. For a light coil, the condenser is built up from a kind of metallized paper, a material mainly used in telegraph instruments. The terminals have tobe reduced over small proportions, and the case is made of molded vulcanite. Wood may be used, but being necessarily very thin, it is fragile as compared with vulcanite. Accumulators of the ordinary pattern do not permit a very appreciable reduction in weight from the standard ignition patterns, except at her risk of proving unreliable. The weight can, if need be cut down to half the usual weight by using very thin plates, but there is no strength to resist the stress of charging and discharging. Such plates easily buckle and go to pieces. This defect can be minimized by jiving extra support to the plates by means of special bridge pieces. The thin plate is also at a disadvantage, in that it lacks the depth of active material necessary to give a good working capacity. Extra light shall be made by dispensing with the usual 154 lead grid in tow-hitch thick material. The lead oxide is pressed. A skeleton lead frame with a series of pockets or ledges is formed which supports loose granulous effective material. This is mounted in a perforate celluloid envelope. This cell is about 1/2 the weight of the usual plate pattern. The Schmidt, a French-made cell, is constructed on this principle. Another cell of specially light construction is lithanode, in which thick material is formed in blocks and the amount of inactive lead in the plates is considerably reduced. In for cell, one of the electrodes consists of a press pot containing lead peroxide instead of the usual positive plate. This makes a Leitzeloff high capacity. High-tension magneto machines, suitable for firing a single-cylinder engine, can be obtained at Aerof 41B, exclusive off the driving sprocket or pinion. And for a 6 or 8-cylinder engine a special type, with distributor can be had at 71B. The Ruthart machine special lightness is obtained by eliminating usual iron pole pieces and a number off the inner fittings, besides using aluminium fourth basin frame off machine. The magnets consist of flat steel rings with the polar space bored out. Thebsense off-pole pieces give us a good magnetic circuit aerodastrong, field off-force at minimum weight. It is not possible to save much weight in thermature. There must be definite amount of wire and soft iron to produce a spark of sufficient firing intensity, and there is also the condenser, which must have a given capacity, to consider. Modification in the mechanical parts and is no longer much scope for weight saving. In Sims Aero Magneto, a light machine of high power is obtained by use of aluminium where practicable and the employment of the highest workmanship throughout. The Newport machine is of the specially light, simple, and compact type, and is distinctive in that it has no high-tension distributor, a ordinary lifted. The current is drawn direct off collecting rings on the armature shaft, and a peculiarity is that when sparks occur simultaneously in the engine, one in a cylinder concluding its exhaust stroke and the other in a cylinder completing its compression stroke. These machines range from 4 lb. For a single cylinder upwards, and the absence of the distributor makes the machine considerably simpler in construction than the ordinary type. Bosch and Nillmeyer, Bassi Mitchell machines are made in small and light models, the former being 4 FLB, and the latter 61B. There is considerable difference in the magnet system of the various machines. In one type a single magnet is used, whilst in others there are retwo pairs of double magnets, one placed over the other, and in a few other machines there are 3 pairs. A powerful magnet system is an advantage for starting by enduring a strong spark at low speeds, but necessarily. This entails extra weight in the machine. 155. Cycloplane. The cycloplane is the invention of John Gaunt, of Cycloplane Works, Gargrave, near Leeds. It is advis forfeiting to cycles or boats, and is claimed to give certain lifting power when driven through the air, though not sufficient to lift the bicycle off the road, or the boat out off the water. By this reducing the frictional contact off the cycle with the road or the skin friction off the water in the case of a boat, it is claimed to reduce the effort or power required for propulsion. It is regarded by the inventor as a stepping stone to aviation, and Tolford would be aviators' experience by half riding and half flying. In design, the cycloplane, which is constructed of 3-ply birch wood about 1-16 in thickness, resembles 8 in, with the ground sheet cued away in the center, the section being like an inverted V with a V-shaped planane side. It is about 5 ft. In length. It is attached to a bicycle by a steel mast above the rider's head. It can be at an angle within certain limits. It will tilt sideways and veer round in either direction, also within certain limits. On the cycle being driven forward with the cycloplane set at an angle giving the best results, determined by individual experiment, a lifting effect occurs. When the speed of the cycle plus velocity of a head wind amounts to 25 miles per hour, liftoff that is calculated to 541b, with a drift of 541b. This gives 541b, 121b, its own weight and 421b, gliding on the air and 421b, reduction of the weight on the tires. An area wind is its obvious advantages, and can be tilted at an angle that will to the greatest advantage of the head wind, but not increase the lift. The chief point of its practicability is ability, the lift is of more assistance to the cyclist than the extra resist ants in head wind, and this the inventor claims to have proved to the case. Canvas has been tried for the planes and abandoned in favor of wood. The invention was shown Fig. 161, the cycloplane, at Aero Exhibition 1909, 156. 13-28-9-8413-1216-4019-6822-9729-5382-81, 157. Telegrams Gaunt Gargrave. John Gaunt aeroplane engineer Gargrave via Leeds. Cash they improved cycloplane ready to fold. 330 weight 12 ibs created 21 ibs. 5 superior finish export packed price 3 cubic feet. Wanted in all parts off state size off depend bottom 2 best when ordering. I also build gliders and manufacture propellers, supply all makes of model aeroplanes and make a speciality off model sundry. All estimates given, the commercial motors conducted by Edmund Dangerfield. Editor Edward Shrapnel Smith. Manager Ernest Perman. THIS Journal fosters, represents and chronicles commercial motoring in all its branches. It has the largest and best circulation throughout the United Kingdom, the colonies, India, and foreign countries general ally. The commercial motor is officially recognized by the Commercial Motor Users Association and is the official organ of the Society of Road Traction Engineers. Fully illustrated. Printed and published by Temple Press Limited, 7-15 Rosebery Avenue, London, BC. For the proprietors, Commercial Press Limited. Every 2-phone Thursday. Penny. The M010R wrote Ev $Rye Thursday, 1 penny. Page 181. Arel Return T. Author Circulation Desk, Offany University of California Library, Ordoth Northern Regional Library Facility, BLDG. 400. Richmond Field Station, University of California, Richmond. A 94,804-4698. All books may be recalled after 7 days, 2-month loans may be renewed by calling. 510. 642-6753. 1-year loans may be recharged by bringing books. To NRLF renewals and charges may be made 4 days prior to due date due stamped. Below APRA 181,994. IB 70,008, 7Z6. A3 University of California Library. Well-known aeronautical experts who have gained most encouraging success with machines built with them, and whose wide experience proves of immense assistance/aerocraft. 1st July 1909. Do ya want /tobbled a flying machine? We supply every part *ariao desirous of having your inventions carried out. You build exactly to your specification *area requiring PRO peelers. Hanley Page is lightest and strongest. Guaranteed thrust and HP absorb. Area requiring any accessories. Wesupply wire strainer 6s. Partisan bamboo tubing wires WH Bay, and we specialize in gliders and all types of aerocraft. House for all things pertaining to aviation. Hanley Page Limited. 72 Victoria Street, London, SW Works, Woolwich, SE. W *Tef Entgen, Bridgwa and W. Motor Co. BRLD Swatter.